Alright, good morning, mother lovers. Have a look at what I've got. I've gone through every one of the Edexcel past papers, all the pure ones, not the mechanics, and got every single calculus question. So 105 altogether. I'm going to sit here and do 105 calculus questions for you. So any other ones you want me to do, email them across to me. I don't know if I'm going to do this all in one go. I've got work at 3, so I probably won't be able to do 105 questions in 105 minutes, pretty much. Do you know what I mean? So there's probably be 2 takes. Hopefully it will be short enough to fit into one video, but we'll see. So let's get going. So first one, we've got given some equation here. We want to find dy dx. So let's go through term by term, differentiate them all. X squared gives us a 2x. The minus 2x gives us a minus 2. And this 24 root x, if we rewrite that as 24 x to the half, then what we can think about, 24 times a half is going to be 12. Drop that half to a minus a half, and the negative is just still a negative. So that looks good. For the second derivative, we just do it again. So this 2x, that's going to be a 2. This 2 is just going to go away. And up here, we take this minus 12, times it by minus a half. That gives us a positive 6. And this minus a half, we're going to drop by 1 to minus 3 over 2. All looks good to me. Verify it has a stationary point when x is 4. So if we plug in 4, we should get 0. So as we do that, 4 square rooted is 2. This is 1 over that, so 1 over 2. So it's going to be 6 over 2, or negative 6 over 2. Negative 12 over 2 is 6. So here, 4, that's going to be 8, take 6. I'm going to faff that up. Let's do it properly. So we're going to have 8, take 2, take away 12 over square root of 4, which is 2. So 8 minus 2 is 6. That's a 6 as well. So we do have 0. Find the nature of the stationary point. We want to take that value of 2 again, or 4, sorry, and plug it into the second derivative. So we'll have 2 plus 6 over. When we think about this one, what happens? Well, we square root the 4 and get a 2, and then we cube it and get an 8. What this number is, I don't care. All I care about, I know this is positive, this is positive. I'm adding them up. It is positive. So that tells us that it is a minimum. So positive, minimum, negative, maximum. If it's 0, you need to have a look either side. I mean, look at like 3.9 or 4.1. Lovely jubbly. Let's keep going. So we've got quotient rule with trig now. So 3 sine over 2 sine plus 2 cos. We want to find the derivative. So we're going to use the quotient rule. We need to have, we've got u over v. That's going to become uv minus uv. That is on the outside, and a v squared on the bottom. So what is our u? Our u is 3 sine, and our v is the 2 sine plus 2 cos. So differentiating u, we're going to get 3 cos. Differentiating v, we'll get 2 cos minus 2 sine. So cos differentiates to minus sine. And now let's stick this all together. So dy dx. What we're going to have, well, we need to have a u dash. That's a 3 cos. We need to have a v. That's a 2 sine plus 2 cos. Then we're going to take away a u, which is 3 sine, times by a v dash, 2 cos minus 2 sine. And that whole thing gets divided by v squared. V was 2 sine plus 2 cos. And then let's square that one. Lovely. So this is looking good. What we can see from like to show that, isn't it? So we should end up with just being a number on the top. And it should be 1 plus this. I'm going to guess that should be theta written in there, Jimmy. So the top should just be a number. So let's have a look at that first. What are we going to get as we expand things out? We've got 3 cos and a 2 sine. So it's 6 sine cos. And then look over here. 3 sine, 2 cos. 6 sine cos. So as you expand out, this term just goes away with this one. And then if we look at the other ones, what we're left with, 3 cos times 2 cos, 6 cos squared. And then look at the other side, minus 3 sine minus 2 sine makes positive 6 sine squared. So this bit gives us 6 cos squared. This is positive 6 sine squared. So what is that all together? It is simply 6. That will look good. From here then, what do we need to do? We need to faff around with the bottom. As we expand those out, we're going to get 2 sine squared, that 2 sine all squared, so 4 sine squared, plus the 4 cos squared, and then we'll times them together. So we'd have a 4 sine cos, but we'd double that to an 8 sine cos. This is looking good. This bit is very much the same as the top. So that bit is just 4. So we've got 6 over 4 plus And if you remember our double angle formulas, when we have sine times cos, that's a half of sine 2 theta. So 8 of them is the same as 4 lots of sine 2 theta. And that's a very good sign as well, because if we look up at the show that, both of the terms on the bottom, the constant and the sine, have the same coefficient. They both have a 1. The fact that we have down here 4 and 4 is most likely a good sign. All I'm going to do now is divide top 1 by 4 so that I have a 1 down there. So 6 over 4 is the same as 3 over 2. So we've got 3 over 2 plus 3 over 2 over 1 plus sine of 2 theta. Now to 1. Nope, all looks good to me. Yeah, so A is going to be 3 over 2 on that one. I will start circling all these answers. That's an answer, that's an answer. They're all answers, aren't they? So next one, what have we got? Some integration. We know that k is a positive integer. Show that when you do this integration, it's independent of k. So what that means is our answer is not going to have any k's in there. No power of k, no log of k, no e to the power of k, nothing like that at all. Not a single k will be written down. Similarly on here, inversely proportional, it's going to be like 1 over k, doing something times 1 over k. So let's walk through this one. What do we need to do? Well, this is the log formula, where we integrate a fraction where we've got a function and a function, but the top one is the exact derivative of the bottom one. When you do that integration, what you're left with is the log of that function. This should be modulus, but we don't need to worry about that at A level. So think about that. Is that set up correctly here? Basically, as we differentiate the bottom, k is a constant, it goes away. 3x will become 3, but this is a 2. So I want to get rid of that 2 and put a 3. So if I factorize the 2 out the front and then put a 3 on the top, we can think, well, what have we done? We've just moved the 2, that's okay, but I've times by a 3 to put that there. So I also have to divide by a 3. So what we should see is that this is 2/3 of the log of this, of the integral of this thing, which is the log of that. So this will give us 2/3 log of 3x minus k. We have limits, they were 3k and k, so we can plug in all of those as well. So let's do that. The 2/3 I'll whack out the front, and then we're going to have a big bracket with a log of, well, 3 times 3k will be 9k, take away k is 8k, so log of 8k, and then 3 times 1k is 3k, take away a k is 2k, so take away log of 2k. And now using our log laws, when we have a subtraction between different logs, that's a division inside the log. So it's 2/3 of log of 8k over 2k. K's cancel out, 8 over 2 is 4. So that is not, well, it is independent of k. It doesn't care about k doing, that's just a number. Whatever k is here made no difference, it was always this. So part B then, let's have a look at that one. This is different. This is not, it's not the log stuff, do you mean? This is a function, yeah, but this is not the derivative of it. What we have here is a reverse chain rule, because it's the derivative, but only of the inside part. It's not of the entire bracket. So if we actually rewrite this, we still got our limits of k and 2k. If we have it as 2 times by 2x to the minus k, all squared, this is reverse chain rule in exact, oh, sorry, minus 2 for the power. Yeah, this is reverse chain rule. So if we were to make a guess, where do we think that guess would come from? Well, it's going to be something like 2x minus k if we add on a power, minus 1. But I don't know exactly how many of them I'll have, so I'm just going to call it alpha. And I know when I differentiate this, it should equal the thing inside my integral, the integrand. So 2 times 2x minus k to the power of minus 2. As I perform this integral, then what do I get? Alpha's still there, the minus 1 comes down. The inside of the bracket gets differentiated to give us a 2. And then we have that bracket, but with the lower power. So we can see a lot of things cancel out. That's going to cancel with that bit. This is going to cancel with that bit. All we're left with then is minus alpha is equal to 1. So alpha should be minus 1. So the actual integral we have then, we can plug that in with alpha as minus 1. So it should be minus 2x minus k to the power of minus 1. Obviously, we need to put the limits into that still as well. As we go and do that, if we say that's just equal to I, so therefore I is going to be, as we plug those limits into here. So we've got the negative of 2x, which is, well, x is 2k, so it's going to be 4k minus a k is 3k. And then we're going to subtract, but we're going to actually subtract a subtraction. So we're going to add 2x minus k, x is k, 2k minus k is just a k. So if we just write this a little bit neater, we've got minus 1 over 3k plus 1 over k. So we can factor out the 1 over k. What are we left with? We've got 1 minus a third, i.e. 2/3 of 1 over k, which is proportional to 1 over k. Don't know if I bother writing that down, but that looks good to me. We've shown that the first one didn't care about k's. The second one, add a k on the bottom. Lovely jubbly. Let's go on to the next one. So what have we got? Some implicit things. We've got this oval ellipse thing, whatever shape you want to call it. Show dy dx is this. Okie dokie. So when we've got implicit, we're going to go through everything that's just an x, do it normally. So that x squared is now going to be 2x. Anything that's just a y, do it normally, 6y. But it's the wrong letter. What wrong letter was it? We used a y. What should we have used? An x. 50 is just a that's going to go away, and it's just a constant. When we have the combination x and y, we do the product rule. So I will do it individually here. We're going to have u is minus 2x, so u dash is going to be minus 2. We'll have the v is going to be y, and the v dash then is dy dx. So what we're going to see is this thing's been replaced by kind of the cross multiplication. So we'll have minus 2x dy dx, and then a minus 2y as well. Lovely. You can obviously do that individually. Just imagine like you're going to ignore the y for a second, do that, what do you get? Minus 2, and then just times it by the y that was there. And then the other way around, you do that, what does that give me? Dy dx, and then just times it by the 2x. So either way you want to do it is all good. We need to now rearrange for this dy dx. So we've got some terms with it, some terms without it. How many negatives? Kind of the same amount. So I don't think it really matters which way we go here. So I'll just leave the dy dx where they are. So we're going to have 6y minus 2x, lots of dy dx. And then we will take the other terms over, i.e. like these two are going to the other side. So we'll have 2y take away 2x. If we divide this bracket over and also divide by 2 at the same time, what are we left with? On the top, we'll have a y take away an x. And on the bottom, we'll have 3 y's take away an x. And that is exactly what they wanted, which is always a good sign. So that's some marks, that's 4 marks so far. What else do they want us to do? Cycle track, they're the furthest west and east. Using part A, find the coordinates of P. P was the furthest west. So when we're the furthest west like this, what's actually happening? And they've kind of guided you into it. I mean, the tangent there is a perfect vertical line. What's the gradient? I don't know if you can say it's infinity, but like it's infinite. I mean, it's going straight up and down. How many steps right do I take? Or how many steps up do I take for every step right? I never take a step right. So I don't know if you can answer the question. But what we want to do effectively for P, we know that the gradient should be infinite. But we could think about, instead of having like dy dx, have dx dy, which would then have a gradient of 0. So if we look at that, what is dx dy? Well, it's just the reciprocal of what we found. So 3y minus x over y minus x. And if we set that equal to 0, then what do we get? Well, the top row will be 0, so y is going to be a third of x, or like 3y is equal to x. That's good. That's given us an equation that we can then also sub in to the original function. Because if we were to draw this, it's like y is a third of x, yeah? We basically get some line that's going to have a gradient of a third that goes through like this. And that shows that whenever the red line and the line that they gave us originally, whenever they cross over, that's happening at a point when it's going to be like a vertical tangent. So we'll take our expression now and we'll sub it into the original. So doing that, I'm going to replace all the x's with 3y. So this x squared, 3y squared is 9y squared. Minus 2x times y. So 2 times 3y is 6y, times another y, 6y squared. Plus a 3y squared equals a 50. This is nice. So sometimes this could be a quadratic, isn't it? But here, all squares. so a little bit nicer to deal with. 9 take 6 is 3, plus another 3 is a 6. So 6y squared is 50. So y squared is going to be 50 over 6. So y itself is going to be the square root of 25 on 3. So 5 on root 3. So 5, is that 5 root 3 on 3? I think. This should be plus or minus, obviously, because of the square rooting. But when we look at here, what we have, P is in the fourth quadrant, yeah. So the fourth, P's down here, well, whatever quadrant this is. So we know it's negative, negative. So P implies that y is negative. Therefore, y is equal to minus 5 root 3 on 3. And that tells us, think what we had earlier on. 3y is x. So x is 3 times bigger than y. So the x-coordinate should be minus that thing times by 3. So just get rid of the third, 5 root 3. So actual answers for P then, where is P? It is at minus 5 root 3 and minus 5 root 3 on 3. All looks good to me. I have got the answer. I've got all the markings up to me. I just actually check what we've done is correct. 3 over 2 is good. What question number is this? This is number 9. The last one, were they all good? Yeah, 2/3 and 2 over 3. Yep, that's good. We got the right answer to the first one. This is right as well. Lovely. All looking good. For the next part C, how to find the coordinates at this point that's furthest north, or yeah, no, furthest north. So we do exactly the same thing we've just done, but instead of doing dx dy, we do dy dx. Nothing changes. Like, what does it mean to be north or south? It's instead of being vertical, you have horizontal. So we need to have the y not changing, i.e. the dy dx is 0. Whereas this one, the x doesn't change, so the dx dy is 0. Whatever's on the top is the thing that's not changing, basically. So that's good. Let's keep going. What have we got now? Some differential equation. So we've got the height of passengers on a roller coaster, blah, 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 time in seconds. Given that they start 5 meters above the ground. So all you really need from these questions is the equation and the point. So we have a point 5 meters above the ground at the start. So we know that TH as coordinates, we have a value of 0, 5. That looks good. Show that H is equal to this. Okay, so we have a differential equation. How do we solve that? You only get taught one way instead of maths. We'll bring all the H's to the left, all the T's to the right. We've got one H there. Let's bring that over. So we'll have a DH over H. You can write that as like 1 over H DH. That's multiplied together, so you can put it on one fraction. And I'll leave everything else alone, I think. Actually, no, I'll bring the 40. Let's put the 40 up there, make it 40, not 1/40th. And then that's going to equal to, we still have the cos of t on 4, or a quarter t. And nothing else. I think the h and 40 went away, so it's just that bit left over there. But the dt must join it. So also dt, and then we can integrate both sides. So all the h's, all the t's, let's do them separately. 1 on h integrated is going to be log of h. And on this side, integrating cos gives us sine. But we need to kind of divide by the differential of this. So that's a quarter. Divide by a quarter is 4. We will have a plus c as well. And the plus c is what we're going to have to find with our coordinate. All looks good to me. So let's do this. What do we need to do? We'll plug in t is 0, h is 5. So when t is 0, this whole thing is, well, that's 0. Sine of 0 is 0. So all that's gone. So let's plug 5 into there. And what we're going to have is that c is equal to 40 log 5. Which doesn't look too bad. So let's rearrange this now for h. What I might do actually, let's rephrase this. So log was in, h is in terms of logs. So I'm going to very slightly just change what we've done. Instead of having c, we'll have straight away the natural log of c. Similar process now, we'll plug in the 0. This goes away. This is going to be equal to 40 log 5 again. But now this is log c. How does that change it? So we could find out what c is if we wanted to. But as we go and do the actual steps now to get h by itself, it's a little bit easier to do the cancellations. So let's do that. Yeah, I'm going to divide by the 40 again. So I'm going to have log of h. We should have really just left that 40 alone. Sometimes it's nicer to make it a whole number doing not a fraction, and then just have to move it back later. So there's no harm in like moving it here, just make it a little bit easier to deal with, and then moving it back in a second. So it's going to be 1/10 of the sine stuff. plus log of, well, what we just found. So we know log c is 40 log 5. So 40 log 5, or log 5 to the 40. Something feels a little bit wrong with that being such a big number. I don't think it should be so big, so let's just double check. Did we do anything slightly wrong? As you can see here, we should end up just with a 5, not a log 5. Let's double check what's going on. Where did that thing happen incorrectly? This is correct, this is correct. Not too sure. We'll walk through and see if it fixes itself. Maybe it will. We will find out. This should also... Ah, no, this is fine. Yeah, this is fine because the 40 there divided off, so that 40 should have gone. Yeah. So do trust your intuition. If something seems too big, seems wrong, 40 to the power, 5 to the power of 40 is a massive number. I don't think my calculator can even handle that number. It can, it just about can. 20, that's 10 to the 27, 10 to the 28, basically. That's too big, do you know what I mean? That's way too big of a number. So if things feel wrong, if they feel too big, just have a look. Have you done a little error like that? We just didn't divide by 40 on it as well. Lovely, all looks good. Let's combine this into one thing then. So we'll raise both sides to the power of e. E to the log goes away, left with just the h. This side is one big term, so it needs to go in one big, that's all going to be the power of 1/10 sine of t on 4 plus the log 5. But where we have a plus in the powers, we can separate that into two different powers. Like we can get rid of that and put another e there. And then e to the log 5 is just 5. So this whole thing is going to be 5e to the 1/10 sine of t on 4. Is that what they wanted? That is indeed. Lovely jubbly. State the maximum height. So obviously the word state, there's not much math to do. What's going on? The only thing that's actually oscillating is the t in it. But that's inside a sine. Sine is always in between 1 and -1. Biggest there is 1. So this is going to be 0.1 in the power. E to the 0.1. So 5e to the 0.1, basically. So h max is 5e to the 1/10. Looks good to me. Passenger reaches the maximum height for the second time. T seconds after the start. When does that happen? So thinking about that, when is sine A maximum? It goes from 0 up, down, and back up again. So it has that maximum there at 90 degrees. But we want the second. So it's going to be the second bit where it goes up, and that is 540. But we've done differentiation, so we can't use degrees. Sometimes it's easier to like plan it in degrees, do you know what I mean, and then transfer over. So this is pi on 4. It's not, it's pi on 2. Add that to 2 pi's, and we end up with 5 pi's on 2's. 2.5 pi's altogether. So that's what we need to set the inside of our sine function to. So t on 4 equals 5 pi on 2. So t is 10 pi. That all looks good to me. Let's check that is correct with the mark schemes. Yes, exactly that. Lovely jubbly. All looks good. Let's keep going. So another one, integration here. We've got some limits and we have a product inside the integral. So that tells us it is by parts. Let's just write down the by parts formula. If we integrate u dash v, that's going to be uv, take away the integral of uv dash. So these just need to swap. This is the product rule. Add this over, differentiate both sides. You have uv, uv plus, well, u dash v plus uv dash is equal to the derivative of uv. So it is just the product rule. We've just rearranged it to make it work for integration. So let's think about that then. What's our u going to be? This is a big choice to make. We want things to disappear. So ideally, if u can go away, that's good. So we can differentiate a 2x and get just a 2. So it's no longer a product because it won't have like an x times the square root of x's. So let's do that. We'll have u to be 2x. So u dash is just a simple 2. V dash is that bracket of x plus 2 to the power of a half. So we raise that, what do we have? X plus 2 to the power of 3 over 2. But we need to divide by that new power. So 2/3 and divide by the differentiation, the derivative of the inside. That's just 1, so no much change there. This looks good. I'm going to slightly rewrite this. The brackets are big, they are bulky. They're horrendous to write and keep doing and can become very messy very easily because they will be in every single term here. So this is v dash. I'm going to call it something. I'm going to now just call it, let's call it z. This thing up here, then what is it? Well, that's been cubed, and it's 2/3. So I have 2/3 of z cubed. So let's stick this all together then. The integral should be equal to u times v. So 2x times this thing. Well, I've mixed up with the product rule. We don't need to worry about doing that. So product rule, you know when you get the bits on, like you have the 2 bits there and the bit on top, on the bottom, often you'll see that this term is just everywhere, do you know what I mean? And it'll all cancel out. So it's easier to set like this to be z squared. This is 2/3 of z squared. Oh, cube, sorry, not squared. And then you just end up having lots of z's everywhere that cancel off, instead of having this bracket all over the place. Slightly different though this, yeah, we're not using product rule like we're doing by parts. So u times v, so 2x times this stuff, so it's going to be 4/3 of x plus 2 to the 3/2. We have limits of 2 and 0, and take away the integral of these bits times together. We can, if we want to, do this step by step, but because we know it's just going to be this thing integrated times by 2, let's just integrate this thing again. What's going to happen? We're going to get an x plus 2 to the power of 5/2. We've got the 2/3 out the front, originally from the v up there. We need to divide by this, so that's 2/5. Divide by the differential of that, which is 1, and then also times it by this 2. So let's stick all these bits together, and they are also inside the limits, so we can work that over there. What's going to happen then? Let's plug some stuff into here. Let's plug a 2 in. So we're going to get 8/3 times by 4, square root is 2, cubed is 8. Take away when we plug a 2 into here. 4, square root is 2, the power of 5 is 32. Times by all of these things, we've got 2, 4, 8 over 15. Now, let's put in the zeros. 0 into here, that's a 0. The whole thing goes away. 0 into there, that's a 2. Square root of 2 is not nice. So 2 to the power of 5 on 2 times all these as well. So 15th we'll put on the bottom. We've got 1, 2, 3, and another 2.5. So this would be 6 halves. That's 5. That's 11 halves of 2. Let's leave that as a 1, and then 2 to the 11 halves. This is not so nice. I'm going to steal those 11 halves. I'm going to steal 10 halves of them, i.e. 5 of them, and make a 32. So this should be take away, but this whole term here is minus 32 on 15 root 2. It should be plus, because when we do the second one with the 0, we take it away. So we took away this one, which was positive, but then this one we take away a negative to make it positive. How did I know I'd made a little mistake there? When we look up above at the show that, it's positive root 2. There's no root 2's anywhere apart from here. Nothing else is going to happen to this apart from I'm going to factorize the 32 on 15 out and leave me with a root 2. So I very much hope this thing, this should hopefully be 64 on 15 as we work it out. Let's have a look at it. What bits have we got? Well, we've got 64 on 3 there. Let's write this in the calculator. Yeah, 64 on 3. Take away 32 on 15 times by 8. And that is 64 on 15. 64 on 15 plus 32 on 15 root 2. Let's factorize out a 32 on 15, and there we're left with a 2 plus a root 2. We circle that, we give it a big tick, double check is exactly what we wanted. We get our 7 marks, and we move on to the next one. Lovely. Let's keep going. So that's all of one paper done. I think, yeah, that's all of the 2018. Yeah, that's all of the 2018 calculus. So now 2019 for paper 1. So what have we got? We've got a fraction, so we're going to be doing the quotient rule. And again, ended up with something on the top that is just a constant. No x's, no nothing else in there. What's our u going to be? Our u is going to be the top thing, so 5x squared plus 10x. If we differentiate that, what do we get? I'm going to get 10x plus 10. I'm going to factorize that, 10 lots of x plus 1. For the v then, what do we have? X plus 1 squared. Differentiate that, what do we get? We get 2 lots of x plus 1. This is exactly what I was saying about these brackets being everywhere. This bracket is just everywhere. So I'm going to say that z is equal to x plus 1. And now let's do the quotient rule. So as always, uv minus uv, that is on the outside, v squared on the bottom. So d by dx, let's stick all these bits together. U dash is 10x plus 1, so it's 10z. The v, what is that? That's z squared. So now we have z times z squared, so z cubed. And then we need to take away u. So this is the only bit without that, without the z in it really. 5x squared plus 10x, all times by v dash. 2 lots of x plus 1, i.e. a z. On the bottom then, we'll have v squared, that was z squared, so squaring that already, z to the 4. This is what I mean, you've got z's everywhere. Z, z, z. Every term in this, when you do the product rule, will contain some, like, if this is a bracket you're doing like this, it's going to contain that bracket everywhere. And now we can see we can cancel this out. The 1 on the right hand side, we can get rid of that one. We've got cubed here, so we can make that a squared. 4 on the bottom, make that a cubed. This looks good. Now from here, I think what's going to happen is we expand the brackets and things should start cancelling down somewhat, because we have, there's an a on the top. This is looking good for the 3 on the bottom. Should we be negatives? Yeah. So again, how do I know something's gone wrong? This should start cancelling out to make numbers. Obviously, this is going to be like, this is positive, positive, positive. So I need that to be a negative. It should be from the formula. So you're going to make mistakes. You're always going to make mistakes. You have to be aware of, like, okay, why is this not doing what I want it to do? What little thing is slightly wrong? So let's do this. We're going to actually expand these brackets now. So what is z squared? Might be worth just doing that separately here. So z squared is x squared plus 2x plus a 1. So 10 of those will be 10x squared plus 2x plus 20x plus a 10. And now this times x plus 1. So this, well, times it all by x. No, ignore me. It's gone in. It's gone there. Yeah, ignore me. So we're going to take away. Should we have a 2 somewhere? We should have a 2. This is 2v. That should be 2. So again, how is something wrong? Because we should have a 10 there and a 10 there to get rid of each other. So we know something is missing. So that looks good. Let's expand that out then. What do we get? We get a minus 10x squared, a minus 20x, and then we times that by, and that's it. That's all we have. So when we look at all these bits, what's on the top then? The squares have gone. We've got 20x's, they're gone too, and we're left with just a 10. So 10 over z cubed, and the z was x plus 1. And then that is exactly what they're after. So a is 10, n is 3. Lovely. So you see, it's a bit of awareness, knowing what you're looking for, knowing what things should happen. You're going to make mistakes. You're going to miss off negatives. You're going to forget to put squares. You're going to do all sorts of things that will slightly change it. Knowing how things should be going as you walk through the questions makes your life a lot easier. I'm aiming for this. Things must go from the top. They must. No other options. So I'm going to have them somehow cancel out at the end. This is all good. Find the range for when this is negative. Well, this doesn't make a difference, does it? It's just about whether this is negative. So when is x plus 1 cubed less than 0? Well, whenever x plus 1 is less than 0. So whenever x is less than minus 1. You see that, yeah, cubes refer, like, what's it called? Maintains? No, what's the word? When you keep the negative. Like, if it's negative, it stays negative. So here, if we plug in a negative, this will be negative. But like, we need to make that the inside bracket be negative. So yeah, x is less than minus 1. Yeah, all looks good to me. Is everything correct? Let's double check an actual mark scheme. Question 3. Yeah, x is less than minus 1. We have a 10 on the top and a 3 on the bottom. Lovely. Right, sorry about that. I went to the toilet very quickly. So let's have a look at this question then. So we've got some curve given over here, R1 and R2. So the exact area of R1 is this. Okay, so first thing to note, like, we've got the factorized form. They've done that nice for us, just so we can write down the roots. That's minus 2, and that's a 4 over there. Oh, not there, sorry, over there. So when we integrate this, we need to expand it first. Just doing the double brackets, we'd have an x squared times by the x makes it cubed, minus 2 plus 2 minus 4 is minus 2, and then minus 8 on the end. So we effectively want to integrate that thing between minus 2 and the 0 to find R1. So R1 is going to equal the integral from minus 2 to 0 of that thing, x cubed minus 2x squared minus 8x. So as we do that then, what do we get? We'll have x to the 4 on 4 minus x cubed times by 2 on 3 minus x squared, so 4 over 8. 8 over 2 is going to be 4. No plus c because we have limits. The zeros won't do anything. They'll all just be zeros. So as we plug in the minus 2, what we're going to get, that's 16 over 4 is 4. We're going to have this stuff goes in here. That's going to be, again, 16 on the top over 3. And being very careful about the negatives. So we have negative 2. Cubing it keeps it negative. With that negative, makes it into a positive. Last one then will be a negative 16. This looks good. As we whack that on the calculator, what are we going to get? So 4 takes 16 plus 16 on 3 is negative 20 on 3, but we want the negative of that. So positive 20 on 3. Was that what we wanted? It was. Lovely. That's all good. What's going on now then? R2 is also shown. There's R2. Blah, 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 blah. Area of A1 is the same as area of A2. Okay. So what we want to do then is integrate R2, which we know is the same. Yeah, it's going to be, it's just this thing, and it's exactly the same thing as we've just had. But we want different limits. What limits do we want? Well, from 0 to b. And what should that equal? Whatever R1 equaled, i.e. the 20 on 3. So let's plug everything in. It's going to be quite simple for the b's, isn't it? Because it's x is just now b, so it's going to be b to the 4 over 4 minus 2/3 of b cubed minus 4b squared equals the 20 over 3. My lowest common denominator is a 12. Let's times it by 12. So I'll have a 3b squared, so to the 4. Times this by 4, so 8b cubed minus 48b squared is equal to 80. Let's actually subtract that over and say minus 80 equals 0. From here now then, like, I think they gave us, yeah, they gave us what it should look like. Your calculators, I think, can just factorize that, can't you? But from here, like, I think it's very hard to actually do this step to go from there to there. So I assume that they're just letting you be like, that's okay. You can just, once you're here, you're just here. Do you know what I mean? I don't know if they'd let you, if it would make a difference too much. Yeah, I don't know. What's the mark scheme say? It says attempts to factorize. Attempts to factorize. That gets you 1 mark, and then you just say, yeah, with no errors. I think this you just whack it in your calculator. Do you know what I mean? That should be okay. Yeah, should be okay. The other way to do it is like slowly expand this out. Do you know what I mean? Like if we just times this by, like times it by b, what are we going to get? 3b cubed minus 20b squared plus 20b, and then times it by 2. So you'd have 6b squared minus 40b plus 40. We can expand that, like collect those terms. 3b squared minus 14b squared minus 20b plus the 40. And then it should be like this times by b plus 2. Do you mean? That's the first row that we'd get as we factorize this sort of stuff would be that. And then the next one would be the one we've got underneath. So sometimes it's easier here where they've given you to show that you actually just work backwards to get what it was like factorized, instead of thinking too much about like, oh, how do I actually factorize this quartic equation they've given me. Lovely. That all looks good. We do get exactly the show that we've got. I think if you expand that back out, hopefully it should be fine. If we pick a random one, let's just do like the squares and see if they match up. Let's do the numbers. Do the b's disappear. So I get minus 40 there, and I get positive 40 there. So that's all good. Lovely jubbly. B starts like that. The roots of the equation are blah blah blah. Therefore b is 1. What is the significance of this one? So that one is over here, yeah? So what that's showing, because this is still B, it's still going to be B, we're just moving it over. So the area would like contain all of this area and then like some of this. So what we're going to see is basically like we filled in this whole little lumpy bit down there. And then we've also filled in like some of this, doing some amount up here. And what we're basically saying is like, obviously this bit is going to be negative and this bit is going to be positive, but kind of vice versa if you think about area. So it's getting to the point then where, I'm trying to think how to phrase it. Yeah, where the combined area, if you think this being positive, this being negative, what are we going to get? Yeah, so the difference between this area and this area is this area. That's what it's referring to. Because when you add up these two, you get that one, is what they're saying basically. Yes, yeah, that looks good to me. Double check that is correct. Doesn't really say. So what they say states that between x equals -2 and x equals 5.442, the area above the x-axis equals the area below the x-axis. Yeah, okay, what we're saying, these two bits equal that bit. Lovely jubbly. Number 13. Don't know what number this actually is or how long have we even been sat here? 40 minutes? I don't know. We've got some curve, blah, blah, blah. Constant pass through the point 3.5, has two vertical asymptotes with equations 2 and -3. Why do we know that Q is 4? Well, it's got an asymptote at 2, so we need to have some bit to plug in. This one's already the -3, do you know what I mean? So yeah, it's going to be from that asymptote. Shows P is 15, passes through this point. Let's plug in the X then. So as we do that, what do we get? P minus 3 times 3, P minus 9, over 2x minus Q. So 2x is going to be 4. We know the Q was 4, so that's going to be, sorry, 3. 6 minus 4 is 2. So you see, yeah, that divided by 0, so something was wrong, wouldn't it? And then when we do 3 plus 3, we get a 6. And we want this to equal to 1/2. So thinking about that then, what's going to happen? We could times this over, that will be a 6. So P minus 9 is 6. So P is going to be 15. Lovely jubbly. All right, me again. Make sure you don't do the, if you're integrating, make sure you do by parts, not the product rule. So let's try and do that again. We need the thing from above, so let's just write it down. P is 15 minus a 3x over 2x minus 4 and x plus 3. This is partial fractions. So it's going to be a over 2x minus 4 plus b over x plus 3. So think about that. How are we going to rewrite that? We can have that the 15 minus the 3x, the numerator on the left, is going to be a lots of x plus 3 plus b lots of 2x minus 4. If we make x b -3, we get these times together, it's going to be +9. So we get 24. X is -3, so that's going to be -6, -10. So it means that b, we got -10b. So b is going to be -2.4. Does that seem right? -12 and 5. Does that seem right? Maybe it's right. We'll keep going. See at the end. So using that, let's have a look when, if you make x be 2, what do we get? 15 minus 6 is 9. So 9 is equal to 5 a's. So a is going to be 9 on 5. The fact they're both on 5 is a good sign, but the 9/5 and 12/5 doesn't seem so nice. But we'll keep going and I'll check the answer at the end. So integrating now. The limits we had were 3, and whenever this hits the x-axis again, which we know should happen at when it equals 0. What am I doing? 5. It's going to be 5. Yeah, when this thing equals 0, that's 5. So from 3 to 5, the integral of a, which is 9/5, of 1 over 2x minus 4, plus, we'll take away 12/5 of 1 over x plus 3 dx. As we go to do all these bits then, what's going to happen? Can I shrink everything a little bit? Yeah, I'm going to just raise everything ever so slightly. I'm going to try not to use second pages for things if I can, just to keep it all in one page, so you can always kind of see everything. So this is all good. Yeah, we need to plug our limits in now. I'm going to do a bit of reorganizing, I think, before I do that. Don't be afraid to take a step just to like make it a bit nicer with things. So fifths and stuff, can I take fifths out? I can take 3/5 out if I really wanted to. So let's take 3/5 out. So we've got 5 and 3 there. This, I can also take a 2 out the bottom. So I've got a 3 there and a 2 on the bottom. That's 3/2. And then I've got x minus 2 on the bottom and 1 on the top, which is good because then that's an exact, like, the log integral form. I can do it straight away. Same here, that already is, so it's good. I can just take out, like, I've taken 3/5, so I've got 4 of them left over, yeah. So 4, don't integrate yet. Now then, when we do the integral, we'll have 3/5 of log x minus 2 minus 4 lots of log x plus 3. Don't forget about the 3/2 on there. Plug in these numbers, what do we get? Plug in a 5. So 3/2 log of 3 minus 4 log 8. And then that whole thing is going to be take away. Log of 1 is 0, and then take away is plus 4 log 6. This looks good. Log 6 doesn't seem good. I don't know what else could happen instead of the log 6. Well, we'll have a look. We'll keep going. So, log 8 is actually log 2, but it's 3 of them. So this is 12 log 2. And log 3 plus log 2, isn't it? Yeah, this is 4 log 3 plus 4 log 2. So inside the brackets, what have we got? How many log 3s? Well, I had 4 and 3/2, so that's 4 and 1.5, that's 5.5, that's 11/2. Log 3. How many log 2s do I have? Minus 12 plus a 4 is minus 8. Spanning these brackets out, what have we got? 33 on 10 log 3 minus 24 on 5 log 2. Those numbers aren't so nice as they go, but they are correct. They're the exact numbers they wanted. Lovely. So yeah, you can see, like, my intuition of being like, these numbers just don't seem very nice. Like the ones we're getting out, like these lots of fractions flying around. The A's coming out being like not so nice with like normally whole numbers coming out. So intuition of just like double checking. Nothing seemed wrong that means we were going through. I think felt like something seemed a little bit iffy, but I wasn't quite sure when. So like if I got this number out in the exam, I'd be going back through and just double checking like all the little bits, haven't done any negatives, that sort of stuff. If I have enough time at the end, I'd do the whole question again and then see if I can do it, or like maybe take the thing I have for the integral and differentiate it, see if I do get back to what I started with. Because if you can do that mostly, then it's going to be fine. So this looks good. 8 marks. It's a lot of marks for that. Let's keep going to the next one. We've got x is 4 sine 2y. So we have some parametric stuff. So implicit, not parametric. Let's find dy dx, and we want that at the origin. So differentiating the left-hand side is 1. The right-hand side will become 8 cos of 2y. But it's the wrong letter, so dy dx. We want to find this when it's at the origin. So let's plug in the value of y. What we're going to get, well, cos of 0 is 0. So this is going to be that this left-hand side is just 1. This side is 8 dy dx. So the origin implies that dy dx is equal to 1/8. I would make that actually like 0, 0 implies that. Lovely, that looks good. For the next one, small angle approximation. It's not calculus, I'm not going to skip that. It's just 2y, do you know what I mean? Like sine is 2y, so it's just like x equals 2y or something. But yeah, not really too focused on that stuff for today. I will do another one in the future where I do like trig bits, we can do that. But now, yeah, we want to like rearrange this. So we have an expression for dy dx, but it's only got y's in it. This one we want to have just x's. So what we're going to do is use this and this to basically eliminate the y's and replace them with x's somehow. So let's think about doing that. First thing I'm going to do is just rearrange that. So dy dx is going to be 1/8 cos of 2y. What I'm aiming for, obviously, is to have some square roots down there. So whenever you've got cos and sine going on, it's always going to be the same idea of like cos squared plus sine squared is 1. So if we very quickly rearrange this one, what do we get? Sine of 2y is x on 4. So sine squared is going to be x squared on 16. So cos squared is going to be 1 minus that. And therefore, like the square root, that's just cos squared, yeah, so we can just have that little bit of it. But the square root will be the square root of that then, yeah. So 1 on 8 times by 1 minus x squared on 16, all square rooted. This is obviously not so nice. What we could do instead of putting it in there straight away, going back with it a bit more here, do you mean? So go up here, let's take out a factor of 1 on 16. And then we've got 16 minus x squared in there. And now when we square root this, what do we get? Well, the 16th is a quarter. And then this thing just becomes the square root, basically. So we can have that instead of cos. Instead of trying to like work with it once we've already subbed it in and do some stuff, just do the rearranging here when it's a bit simpler, and then take the fully rearranged form in there. So 1 over a quarter is 4, yeah. Yeah, get it ready again. And then that bracket will be on the bottom. So the 16 minus x squared, all square rooted. But what we can see, that's going to end up being 1, well, the 4 and the 8 will make a 2. So 1 over 2, 16 minus x squared. Looks good to me. Does the mark scheme say the same? What number are we on? Does it say the same? It does, which is always a good sign. Lovely jubbly. Let's keep going. So it's these things. This faff, yeah. So what is it? 2 over x dx. Do we have limits? Yeah, 2.1, 2.1, and 6.3. That is 1 mark, is it? Yeah, 1 mark for that. And show that it's equal to this. Okay, so do the integral. Notice that these are 3 times bigger than this, so I'm going to guess that this is going to be a 9 off my head because of that 2. This being a 3, so it's like 3 squared, you mean? But let's have a look. What we can do is take out the 2, just to, if it's a show that, I mean, we'll do all the sets. 6.3 and 2.1. So then 1 over x dx. So this is 2 times by the log of x with these numbers subbed in, 6.3 and 2.1. So doing that, 2 lots of log 6.3, take away log 2.1. Difference in logs is a division inside the logs. So it's log of 6.3 over 2.1. So it is log of 2 log of 3. Or, like I said, log 9. Lovely. That all looks pretty good. That's a nice simple 3 marks just to get going on the paper. Make my 9 look more a 9ish than a flying random thing. Is that actually correct? Let's find out. Hopefully it is. This is 2022 paper on now, by the way. What question is this for? Yep, log 9. Let's keep going. Number 6. What have we got then? Some curve, blah, blah, blah. Pass through the origin, max here, minimum turning point there. Write down when is the gradient negative. So when is it going down? Yeah. When is the function falling? So we can split it in terms of the turning point. And then you can split it into separate regions, and you can just answer the question for each region. So, region on the left, are we going down? Nope. Region in the middle, are we going down? Yes. Region on the right, are we going down? Nope. So we only care about the middle one. Do we want to include the numbers 2 and 6? Depends on whether this is including the 0 or not. It's not. So we need to think about the fact that it's going to be between 2 and between 6. Well, between 2 and 6. Lovely. Line equals y equals k. Intersects here only 1 point. Okay, these are not quite. Yeah, these are not quite calculus, but I'll show you quickly what we're going to do. So y equals k intersects at only 1 point. So you can think like all that it's fixed here, and you have different angles that go out. So these ones you hit it here and here. So basically, what you can think about is any time that you go have a positive gradient, anytime you go from here to there, you're going to hit this curve because this will eventually become steeper than you. Eventually, no matter what your gradient is, eventually this will become steeper than you because you're a straight line. This is a cubic line, so it will become steeper than you eventually. So every time you go to the right, you will hit that one. The only way you can do it is if you don't hit any of these. So you'd have to come out at such an angle that like you don't hit those ones. Do you mean? But I think you're going to get a point where like you always hit this one again. Do you mean? So the same argument, you always hit that one that way. You always hit this one this way. So anytime you're in this quadrant, not allowed. You have to be like in this quadrant, and then just having a point where you just hit it once. Do you mean at the origin? I think that's what's going to happen. Yeah, I think that would be fine. And then just actually find the equation of C. So this is the bit that we want to do. Yeah, okay. The equation of C. So what do we know? Well, we have a few things. If I write x, y, and then I'm going to have like dy dx as almost a coordinate, do you know what I mean, but with dy dx in there. So what do we have? Well, we know we have 2, 8, and 0. And then we also have 6, 0, 0. So it's like we have 4 facts there, really, in a weird way of putting it. We already know some things, though, do you know what I mean? We can figure out some bits, I think. Yeah, we don't even need it anywhere near as much as what we've said there. We know that we have y is going to equal to x because we've got a root at x. We then have a double root at 6. So x minus 6 squared. But we need to make sure we go through 2, 8. So we did need, I suppose, that 1 point. As I put in a 2, what do I get? That's a 2. This is a 4 squared is a 16 times the 2 is a 32. So I need to be a quarter of that. So it should be 1/4. Is that correct? Let's double check. Number 6. 1/4 of x minus 6 squared. Yeah, lovely jubbly. Next one. Scientists are doing some faff with bees and wasps, islands and things. You've got this equation for bees, number of bees. In thousands. T is years, blah, blah, blah. Find the number of bees at the start. Okay, T is 0. E to the 0 is 1. 220 plus 45 is 265,000. Part B. Show that exactly 10 years after the start of the study, the number of bees was increasing at a rate proportional, approximately 18,000 per year. So we want to differentiate. What's going to happen? Well, this is a constant. It's going to go away. This is a 20th. So what we're going to have is that d and b dt is going to be equal to a 20th of 220, so 11 e to the t on 20. This is why fractions are your friend. It's much easier to do that. And then we want to sub in 10 into that. So if we do 11, yeah, so dnb dt evaluated when t is equal to 10 gives us 11e to the half. What number is that? It is 18.1. So that does tell us, yeah, there's roughly like 18,000, was it 136? That's roughly what it's telling us. So that's good. This is roughly as well. Nice. Number of wasps now. Little evil buggers, aren't they? So measure in thousands again. Number of years. Oh, find when there's an equal number of bees and wasps. So we want to set those two equal to each other. We're going to have a 45 plus 220 e to the t on 20 is equal to 10 plus 800 e to the minus t on 20. So this is a hidden quadratic. If you ever have only constants and then terms with powers where the powers are completely the opposite of each other, positive, negative, or one's double the other one, that is a quadratic. So here, what do we need to do? Well, I can make that to 35 just to begin with. So make that a 3. Make you go away. And now then, could we do some numbers? We could do numbers as well, but yeah, we'll do numbers. So divide by 5, what do we get? 7 plus how many 5s in there? Not too sure. 45, 44? 44, yep. So 44. And I'm just going to do no, I'll do that in a second. T over 20. And then how many 5s in there? 800 divided by 5, 160. Yep, 160. And now I'm also going to times by e t to the 20. So this one will be squared, this one will go away, this one will gain 1. So we'll have 44 e to the t on 20 squared plus 7 e to the t on 20 equals 160, or just take 160 equals 0. We want to solve this quadratic. It doesn't look like that could have nice solutions. Let me get a calculator to solve that one. I don't have one of those fancy ones. I just have to use like a Wolfram Alpha or something. So let's see what it's going to give us. We have 44x squared plus 7x minus 160 equals 0. Is it going to be a nice one? Let's find out. No. So the fact that this is so horrendous tells me something's probably wrong. So t, what they want, well, this would be e to the t, blah, blah, blah. E to the blah, blah. This is saying minus 7, yeah, minus 7 on 88, plus or minus 28209 on 88 square rooted. That's not so nice, not so nice at all. Let me do it with the original numbers. Does anything change? That is a plus. They're all pluses, aren't they? Yeah, they should be equal. That's good. Yeah, I'll change my numbers up. Did I do some dividing wrong? That is a 35. Oh. 220. That's a 35, and this is a 800. That's not an 8. That's a 9. That's an 8. No, I get the same. I get the same. So my division wasn't the issue. Have I just copied this wrong? 45. No. Yeah, I took the 10, then I took the 10. I took the 10. Everything looks fine. And this is just is okay, do you know what I mean? And this is fine. So it should be like, we would take log of this, yeah? Is that thing bigger than that thing? Maybe. One thing to note as well, the square root's only on the top. So what is that thing? Square root 28209 divided by 88 is 1.9. So that's bigger. It's definitely bigger than this, and it's bigger than this thing. So we need to add it on. We can't go negative at all. We have to add it on because e must be positive. So e to the stuff is positive. So it tells us that e, what was it, 220, is equal to, yeah, the positive of that. So 28209 square rooted minus 7 on 88. So t equals 20 log of that. 28209 minus 7. That bit square rooted. This bit over 88. Well, this is not so nice, is it? Let's see then. 20 log of root 28209. Take away 7. All over 88. I get 12-ish. Do you know what I mean? 12.08. Is that good? What question is this? 10. Doesn't seem so nice, does it? 12.08. Yep, lovely. Well, so that is good. These numbers, that's a horrendous thing. Most of the time, you will have nice numbers popping out. I mean, they set it up so it's nice. If you go to university and do maths, you basically won't see any numbers. You just don't hardly see any numbers bigger than 10. I mean, they don't exist anymore. So why they're doing this, I do not really know. Why they're making you work with such horrible things. Why can they not just pick nice quadratics and work with it? Who knows? But yeah, this looks all good. Everything's correct. Gives us the correct answer. So let's keep going. Show that this is true. So inside here, we have an integral that is a product. So that is by parts. The integral of uv dash is equal to uv minus the integral of u dash v. What is each bit? Well, we really want the stuff to go away. So ideally, we'd like to set x cubed to be u. But we cannot integrate log by itself. You can do it by doing by parts with log by itself and then setting u to be this and differentiating it. But that's long-winded. We may as well just set this to be u. So u dash is 1 on x. B dash x cubed. V then, raise that up to a 4, divide by that 4. So if I call this I, let's stick this all together. U times V. X over 4 to the power, x to the power 4 over 4 of log of, I don't know why I've called it u, log of x. Limits of that thing are e squared and 1. Take away the integral of these things times together. So this is going to be x cubed on 4. Raise that power x to the 4, divide by another 4, so 16. So x to the 4 on 16. Let's just move my limits over there a little bit. And that's it. That looks good. You can take the x4 out if you want. Let's factorize a bit. So let's take an x to the power 4 over 16 out. What we're left with is 4 log of x minus 1. So let's plug in some values. First thing to note, the e squared is quite nice to me, so that's the e to the 8. E to the 8, that's good. So we're going to have e to the 8 over 16. Lots of, when we put in e squared into there, it's just 2, yeah? Because you have, the 2 comes out the front, log of e is 1, so that is 8 minus 1 is a 7. When we put in the 1, what do we get? We're going to have 1/16. Log of 1 is 0. So this whole bracket is just minus 1, but we had the negative already, so it turned into a positive. So we should have that we're going to end up with 7/16 e to the 8 plus 1/16. Does that look good? Let's double check. Number 12, 7/16 e to the 8 plus 1/16. Yep, lovely jubbly. Give that a big circle, a big tick, and let's move on. Now we've got a big block of cheese. Making a toy for children. Looks like, yeah, it looks like a piece of cheese. Lovely. They modelled that, so it's a sector with a radius r and centre a, blah blah blah. It's just describing the shape. I always think, like, if you're blind, you have to be able to do maths if you're blind still, so they have to be able to give you every single bit of like the diagram basically. But I feel very sorry for people that are blind trying to like visualize the slice of cheese they've given you from that stuff. We know the volume's 240, so the surface area is given by this. So this is rates of connected changes. It's not rates of change, but we're talking about the actual, like, we're changing the shape of the cheese. We're not having like a container that's cheese shaped and we're pouring things into it. Very different thing. So these are not rates of change. Not rates. There's no kind of over time here. Do you mean at no point has time been mentioned? So it's not rates of change, but it's kind of a similar topic. Do you mean? So yeah, find the surface area of that thing. Let's find the volume of it. How do we find the volume of it? Well, volume of a cylinder, which is what this is, yeah. We need to find the area of the surface, like the cross-sectional area. So doing that, we would have a sector here. So r squared theta on 2. So half of this is 0.4 times r squared. So 2/5 of r squared. Times by the height of this thing, which is just h. The surface area, if we were to work all that out, we'll have something very similar for the these bits. I mean, these are still the 2/5 r squared, but we have a bottom as well. So we'll have 4/5 of r squared. And then we need all of like the other faces. So what's that? That's r times h. So is the other face. So we've got plus 2rh. And then we will also need this kind of like curvy bit on the back. So it's h high. How long is that? Well, it's however long the arc length is. So that is r times 0.8. So 4/5 of r times h. Plus 4/5rh. So now we have an expression for the volume and for the surface area. Down here, we want surface area, but without any h's. So what we effectively need to do is use the volume formula, because we know that's a value of 240. So we actually need to set this equal to 240. And then divide by the 2, 120 times by the 5 is 600. So r squared h is 600. So h is 600 over r squared. And that's what we're going to use then to eliminate h from this equation and give us this thing. So let's do that. Wherever we've got an h, we're going to whack 600 over r squared. So the first one, 4/5 of r squared, that's all good. 2rh. So the h is going to go away. So the 2 times 600, 1200. R times r, 1 on r squared is 1 on r. And then this bit here as well. Oh, we could have really just combined this together. So what is that? That's 14/5. Let's actually not, yeah, let's do this from scratch again. So that bit, yeah, what is that bit? That is 14/5 RH. So 14/5 times 600. What number do we get? 1680. And same idea for the r's, isn't it? So it's going to be 1 on r on the bottom. So 1680 over r. Is that the number they wanted? That is indeed. That looks good to me. Find the value of r, for which this is a stationary point. So we need to do dsa dr. We're going to get 2 times 4/5, which is 8/5 of r, minus, if we think about this thing being 1680, r to the minus 1. So the minus 1 comes out, times by the 1680, drop that minus 1 to minus 2. and we're going to set that equal to 0. So effectively, like 8 over 5 r cubed equals 1680. So r is the cube root of like 5/8 of 1680. 5/8 times 1680. 1050 cube rooted. I don't think that's going to be a nice number, is it? No, not at all. I can see it's way too close to 1,000. Lovely. That looks good to me. Prove that it is a minimum of the toy. Okay. So yeah, we need to differentiate again, don't we? Taking this thing, what's going to happen? D2 SA dr. So 8/5 r becomes 8/5. Well, times by the negative to make it positive, times by the 2 to make it 3360 minus r cubed. What we had originally, like our value for the r is positive. So it's the same idea, like this is just going to make something that's negative, but we can't actually, positive negative is not going to work. We do need to plug in the number in this case. So as we do that, we can just use the fact that this is actually cubed. Do you know what I mean? So this is really 8 over 5 plus 3360 over the 1050, because r cubed is 1050. This is 1 over r cubed. So what number is that? I don't know. I don't care. All I know is it is positive. Oh, what's it? Yeah, we could have done that earlier. Sorry. It's always positive all the way through. So therefore, minimum. Lovely. All looks good to me. Let's keep going. So parametric. Oh, first parametric one, I think. So parametric not been too common so far, unless I'm being silly and I've just forgot one. But I don't think we've had one thus far. What do we want to do? Find the area of R. So how do we do that? Well, ideally, the area of R is just like the integral of y with respect to x from 0 to 4. But y is in terms of t, not x. So we're going to use the chain rule. We're going to know that we need to have a dt. Everything's going to stay the same. Oh, these were all. No, that's fine, yeah. Everything's going to stay the same there for now. But the y will stay the same. But the dx is going to go. We want to have a dt. How can we do that? By having a dx dt. So that the chain rule makes them cancel out to just dx. I will reorder that. And one thing to note now, we're now integrating with respect to t. The limits that we started using were x. So we need to find out what is that in terms of t. If you've got them written here and you haven't changed it yet, just write like, oh, this is like at x equals 4. Or at x equals 0 for both limits. So a few bits to work out then. Let's start with the limits. If I make x 0, t is 0. If I make x be, was it 4? Yeah, 4. Then I have sine squared as a half. So sine squared is a half. So sine's 1 over root 2. So it's 2 root 2, no, root 2 over 2. So that's 45 degrees, yeah. But we are integrating. So it has to be radians. So it is going to be pound 4. We also need dx dt. So let's differentiate that. What we're going to get? 16 sine t times by the differential of sine, which is cos. That's dy. That's dx dt. You can write this. This is 8 sine 2 theta. 2t. Yeah. Whether we need that, different question. So let's plug all these bits in together. What are we going to get? The integral from 0 to pi on 4 of y, which is 2 sine 2t plus 3 sine t, times by dx dt, which was the 8 sine of 2t, all with respect to t. Lots going on. Let's expand these brackets out. What we're going to have, pi on 4 and a 0. We're going to have an 16 sine squared 2t. And in this bit, we're going to have 24 sine t sine 2t. dt. Does that seem nice? That doesn't seem too bad. It could be much worse than it is. So the sine squared we can't actually do, yeah? Like there's not a way to really do sine squared. So how do we deal with it? We need to use some sort of double angle formula, like with cos 2 theta, to get it to pop out. So as we do that, oh, do we even need to, okay, we just need to rearrange this. Okay, that's good. That's good, yeah. We need to do it for the next bit. Okay, but they've given us a middle step, that's okay. So we know what we're aiming for. What bits have we got? What bits have we not got? So some things to spot are where we have like the sine 2t. I'm pretty sure that's just the first bit. Like this being like the 24 goes nicely with the 48. The 16 does go, but with a 3, you very rarely see like 3s appearing here. Do you mean? All the formulas you get for the double angles are 2s. In it, like 2 sine cos or like 2 cos squared minus 1, that sort of stuff. It's not going to be 3 ever. So like, yeah, 16 and 48 are nice, but via 3, which is not good. But 24 and 48 via 2, 16 and 8 via 2. Lovely, looks good. So over here as well, like we've got the sine t, and there's one sine t. Sine 2t is sine cos, so it's just the remaining bits. So that bit is exactly that. If we expand out this thing into 2 sine cos, this will make that squared and times by the 24. So we'll have that this is 48 sine squared t times cos t. For this bit then, the double angle formulas, you can go and double check exactly what they are for cos. If we have cos of like 2 theta, what do we get is cos squared minus sine squared, don't we? But then we know that cos squared plus sine squared is 1. We only want sine squared, so cos squared is 1 minus sine squared. 1 minus 2 sine squared. But we started off with 2 theta, or 2t. So effectively, and now we rearrange this for sine first as well. So sine squared cos 2 minus 1 over 2. But we need to double that, make that a 2, make that a 4, and then make this a 16 out the front. So times this by 16, i.e. get rid of both of those, put an 8. So yeah, 8 cos 4, and those bits negative though. Oh yeah, 1 minus sine squared. Yeah, I got this the wrong way around ever so slightly. The 1 and the 4, the way around. But that's all good. That is exactly what we're looking for then. I mean, this thing is just precisely 8 minus 8 cos 40. Beautiful. So that's part A done. Part B then is to go and do the integral. I will steal this and like do it, but there's a bit more space down below. I think they've given this little like kind of like halfway step. Should help quite a lot because now we should be able to recognize most of these integrals. Let's make sure I've got the limits right. It's pound 4, wasn't it? Yeah, pound 4. So the 8, nice and simple, 8t. When we've got no powers but high operands, we can simply just do it normally, like cos integrates back to sine, doesn't it? So it should be minus sine 4t, but dividing by the 4, so 2. This is reverse chain rule. The derivative of sine is cos. So you've got some function to a high power next to its derivative. So if I was to guess sine cubed of t, what does that differentiate to? 3 sine squared t cos t. So I'm just 16 out. So it needs to be 16 lots of that. Sorry, 16 sine cubed t. That looks good. All of these then, we need to plug in pi on 4 and a 0. Pi on 4, that's 2 pi. So sine of pi is 0. Sine of pi on 4, sine pi on 4. Make sure you're in radians. It's root 2 on 2, isn't it? Yeah, I'm not being silly, am I? Yeah, root 2 on 2. So let's do that to the power of 3. And then times that by 16. 4 root 2. For the 0 then, 0, 0, 0. So I think we should be done there. 2 pi plus, let's take a factor out, 2 plus pi plus root 2. Is that good? Let's double check. Seems quite nice. Seems very simple, doesn't it? It's always a good sign it's that simple. 16, let's find out. 2 pi plus 4 root 2. Lovely. Lovely jubbly. 9 marks for all that. So a bit fiddly. Yeah, very fiddly. This is not, probably the worst one we've done so far, I'd say, like with this. Yeah, not so nice if you didn't see exactly what to do there. Yeah, not so nice. We'll do a couple more, and then I'll have to go and start getting ready for my next lessons, make sure I've eaten and stuff like that. But I'll put it, I think it should be all in one video. We'll find out. How many questions have we done? We've done 16. We need to do 105. So maybe it won't be one video. Maybe it's going to be a little bit longer than one video. Here then, we're going to do this little integral. How are we going to do it? We could just expand the brackets. I think that's the easiest way, actually. So what we're going to have, 2/3 x to the 3 on 2 minus 5/3 x to the 1 on 2. Integrate all of that stuff. Raise the power, 5/2. Divide by that power, 2/5 with the 2/3. Take away x to the raised power, 3/2. Put 2/3 there, alongside the 5/3. Whack a plus c. 2 times 2 is 4. 3 times that is 15. X to the 5/2 minus 10 on 9. X to the 3/2 plus c. Does that look good? Let's double check on this next one. Seems all fine though. 4/15 and minus 10 on 9. Yep. Yep, that all looks good to me. 4 marks for that. It's quite nice for 4 marks. Let's do a couple more quickly. Covers this equation. Where x is that? Given that f dash is this, has a stationary point alpha. Alpha is small. Oh, this isn't actually okay. This isn't actually. Look, you can see how I'm thinking it is stationary point like tangent. But yeah, I just very quickly scrolled through them all. But this is not. So 104 actually is how I'm doing. 104 makes it a little bit easier, doesn't it? So y is sine, x is radians, dy dx. First principles. Okie dokie. So let's say f of x is sine of x. So that tells us f of x plus h is sine of x plus h. So we can expand that out. We'll have sine x cos h plus sine h cos x. So if you think about doing those, a subtraction of those, the other way around, what do we end up getting? Well, all of these bits take this. So let's just copy all those over and take away a sine. Don't know how I missed the line so badly there. There we go. From here then, what do we want to do? Well, look at what they've given you. Like, they give you these things for a reason. It's all the h's. When you do first principles, if you have just powers of x, you want to end up where you basically don't break your calculator, is what you want to think about it. You can't plug in because right now the h is on the bottom. So we're going to basically factorize so we get these bits. So we've got that. I will actually do like the 1 on h for this stuff, do you mean? So 1 on h of these. So 1 on h of all that. And now let's factorize it. How many sine x's do we have? I've got cos h minus 1 over h. And then same idea for coses. How many cos x's do I have? I've got sine h of them over h. So that is, if we were to work out the kind of thing that goes inside the limit. So we now want this thing, we want the limit of that as it tends to 0. So we want the limit of this thing, so it's h tends to 0, not x. This thing, part of the longest thing about this is just rewriting everything. You have so much different faff to have to write down. And what we can see then, these bits are these bits. So when you do this, the sines and causes are to do with h, to do with x. They're not to do with h. They're not affected. They're basically just like constants that are going to come out here. These bits are going to do what it tells us above. So this one goes to 0. So what I'm going to write is it's 0 times sine x, and then vice versa. The other one goes to 1. So 1 times cos x. And then we can see that's just cos. And what you've done is you've shown, if you differentiate sine, you get cos. All looks good. Yeah, seems fine to me. No issues there, I don't think. Yeah, I'll stop there. I'll do the rest of these either today or tomorrow or over the weekend and try and get as many done as I can. Whether this will be one video, I don't know. We'll find out. We'll see. All right, guys. Good afternoon. I'm back again. Let's do some more of these. So first one, we've got this equation for f of x. We want to find the derivative. So this is kind of horrendous, yeah? We've got a product rule, we've got a chain rule, and we've got a quotient rule. So let's do them individually to start with. We're going to do the 7x e to the x. So if we differentiate 7x e to the x, what do we get? Well, if we do the 7x, we get 7 times by the e to the x. If we do the e to the x, we get an e to the x times by the 7x. So you can factorize out a 7 e to the x, lots of x plus 1. Looks good to me. Doing the same thing for the bottom. So the derivative of e to the 3x minus 2, all to the power of a half. What's going to happen? That half comes out the front. Along with the derivative of the entire inside, the 2 goes away. E to the 3x will have 3 e to the 3x. So not 1 half, but we're going to have 3 halves. E to the 3x times by that same bracket, e to the 3x minus 2, but to the power of minus a half. So that's all the bits that we've done. We've done the product rule. We've done the chain rule. We need to now just stick them all together inside the quotient rule. So if you think about what each bit is, this is going to be u, this is v, this is u dash, this thing is v dash. So let's start sticking them all together. What we're going to get? Well, we need u dash v minus uv dash all over v squared. So as we do that, u dash, what is that? It's 7 e to the x, x plus 1, times by v, which is going to be, what I'm going to do is just call that, yeah, v. We're going to keep calling it v. And now then, for the next part, we need u to 7x e to the x, times by v dash. Well, v dash is this thing. We've got 3 over 2 times e to the 3x. And then this thing is just that, but on the bottom. So it's 1 over v. And all over v squared. Which is looking good. So we can times everywhere by v. So get rid of that one, make this v squared. So we'll have 7 e to the x plus 1, v squared minus 7x e to the x. I will actually work out some of these numbers, so let's get rid of those little bits. 7, 3 over 2 gives me a 21 on 2. E to the x, e to the 3x gives me e to the 4x. All still over v, but now we've cubed because we times top and bottom by v. This looks good. Let's think actually what we need to aim for. Should we take some bits out? Well, yeah, 7 over 2 and then e to the x being at the front would be nice. So let's take a 7 e to the x over 2 out. What do we need? And actually, I'll take the v cubed out because this is v cubed. So let's take that v cubed out the bottom as well. So over 2 v cubed. What are we left with? Well, v cubed, don't need to worry about it. So just the top we need to worry about. We've got a 7, we've got an e to the x. Haven't got a half, so we need a 2. And then we're going to have x plus 1 and then v squared. What is v squared? Well, v squared is this thing squared. So e to the 3x minus 2. What we're doing, e to the 3x minus 2. So that's that first bit, and then just take away again, just this thing. But we've factorized out 7 over 2. So there's 3 lots of that. And we've taken away one of the e's, so there's still 3 of them left over. That all looks good to me. Let's just put this a little bit nicer then. So 2v cubed. What do we have here? Let's look at what we actually need to end up at. I'll be very close. Nearly. We want to kind of factorize for the e to the 3x's. So let's do that, and then we'll factorize everything else. So e to the 3x, where are they going to come from? Well, there's some in there. So it's this thing times all of that. So this is 2x plus 2, yeah? So we've got 2x plus 2 in there. Did we actually want the 2 at the front? No, we didn't. But then we've also got a minus 3. So it's 2x plus 2 minus 3. That makes a minus 1 in there. Does that match it? No, we've got 2 minus 1x. We'll keep going and see if we can spot that difference in a sec. For the numbers then, it's just going to be these bits. So that's going to be minus of this, so minus 4x minus 4. So we're quite close, but obviously, yeah, we're not quite exactly what we need there. So have I just got some negatives wrong every now and then? It is e to the 3x minus 2 in it. Yep, it definitely is. Have we done anything wrong with negatives? This was okay, wasn't it? Yeah, because that came out originally. It did start off at a higher power, so that's good. Subbing this in, we should have a negative in the middle. None of these things were negative, so we shouldn't have gained any negatives. We should have just the one in the middle. That bit comes from that bit, that's good. That is that one. This is correct. This is correct, isn't it? Yeah, that comes from up there. Why has this not worked out the way it should have worked? Let me double check the mark scheme. What should we have? We should have v times 7 e to the x. Yep, that thing's there. Minus all of this stuff. That's all correct. That's good. That's good. Obviously, v squared is good too. So we do that. The next line, annoyingly, in the mark scheme is just to go straight from there to the answer. What's missing then? So this is correct, isn't it? No, this is correct. That's what they've got up there. So that's good. Have I done just one thing wrong here then? What did I do first? I times by v. That became v squared. The v went here. Was this correct? X. So it's very easy to miss off one little symbol to an x in there. Because I factorized out. No, I haven't factorized it, have I? There should still be an x up there. So as we do that, that has an x now. So this has an x. So when we went to do our expansion of the brackets, I think those bits at the end are still fine because they weren't affected by that 3x at all. So they are, and they are correct. Yeah, they are correct. So what happened here? We expanded this out, didn't we? And we had a 2x plus 2 minus 3. So now it should be 2x plus 2 minus 3x. If we calculate that then, 2 minus 3 is minus 1. That is, yeah, 2 minus x. Lovely. So yeah, very easy to slip one up. If you spot it's not the same, do try and track through what did you miss. What is different than what you've got. You could also track back as well, like where do these bits come from? It's this and this. So it's only going to be the top, like this stuff is okay. Do you mean that is correct? So something's wrong here. So as we go through, like what's wrong, it's just that the multiples of e, do you mean is that all we can tell is wrong? Where do they come from is quite difficult to find, but trying to trace through and see exactly where all bits come from. Somewhere there might be a negative, or like we just missed an x, do you mean in one of these? That's all good. Is the next bit about this stuff? No, the next bit's iteration, so we're not going to do that. Oh, no, the next bit's B. Show that the x coordinates of the turning points are similar to this. Okay, so turning point, this is just equal to 0, yeah? So the entire thing we have, we just want to set this equal to 0. This bracket can never be 0. E to the x can never be 0, so it's just about this being 0. So we need e to the 3x on 2 minus x minus 4x minus 4 equals to 0. Rearrange over x. Well, you got x on this side, so it's not like we need to just completely solve for x. We just want to take kind of the lower x's. So we've got x there, expand them all out. So 2e to the 3x minus x e to the 3x minus 4x minus 4 equals 0. Let's take all of the x's to the other side and factorize and divide by that thing. So we're going to have x is equal to the bits we left over. So 2e to the 3x minus 4 divided by the bits we factorized from there. There's an x plus a 4. Sorry, not an x. E to the 3x. That look good? Looks good to me. So always nice when it matches up. Let's go on to the next one. Where were we? That was the answer. Yeah, let's go to the next one. So given that y is x squared, first principles. Okay, so if we say that f of x is equal to x squared, then that's going to tell us, let's actually do on the next line, that f dash of x is going to be the limit as h tends to 0 of f of x plus h, so x plus h all squared, take away x squared, i.e. f of x, all over h. And now we're going to expand the brackets. So to do that, x squared plus 2hx plus h squared, take away the x squared still, all over h. And now our x squareds are going to cancel. We can divide off the h as well from a lot of places. So it's the limit as h tends to 0 of 2x plus h. And then as we plug in h is 0, what's going to appear? It's just a 2x. Lovely jubbly. Same process if it was cubed, 4, 5, any power. You expand it out. The first term will cancel off with like the normal f of x. Everything you're left with is either going to have like h squared, i.e. more than one h. So when you plug in h later on, like you can do h squared over h, gives you a single h, plug in 0, it's just 0, doesn't matter. Or has one h here, cancels with that h, and you're left with things that are not to do with h. And that will be this for every type of this one, the answer that you're looking for. So that's all good. Let's keep going. Number 5. We've got more quotient rule stuff to do. So 2x minus 3, we'll call that a u. 2x minus 3. So u dash is a 2. The bit on the bottom, v, we can call that x squared plus 4. V dash then is 2x. As we stick this all together, u, v minus u, v dash is on the outside, v squared on the bottom. So u, 2x minus 3. That's not what we want though. We want u dash. So we want a 2 times by the x squared plus 4. I'm actually going to expand this all straight away. Looking at what we've got, like we're going to end up with the quadratic. So 2 times this, 2x squared plus 8. Times by u dash times by u times v dash, so this thing times 2. So it's going to be 4x squared minus 3. But we want that whole thing negative, so plus 3, negative that. All over x squared plus 4, all squared. Let's collect the top. What do we have? Something looks a little bit wrong. Yep, that should be a 6x on the end. Just to double check, it was a minus 3. We times by 2x, it should be 6x, but it was minus of that, so it should be positive 6. The reason I thought that, because we had a quadratic, but we didn't have any x terms. It could have that b is 0, but double check that if you get none out, just, okay, should I just have had one over there? So collecting this all up, what do we have? Minus 2x squared plus 6x plus 8 all over x squared plus 4 all squared. All looks good to me. Is it going to be correct? Let's find out. When I get the next one, it's nice seeing how many passages I've gone through, so I know that there's not a huge amount there. Number 5, we have minus 2 plus 6 plus 8. Lovely jubbly. Hence then, find the values for which f is decreasing. So decreasing, f dash of x is negative. The bottom that we have is always positive. So whether f dash is negative or not depends entirely on the top half. So this is equivalent to having minus 2x squared plus 6x plus 8 is negative. And again, we can now divide by 2 and also make it negative. X squared minus 3x minus 4 is positive. Factorizing this, x minus 4, x plus 1 is positive. So this needs to be either x is less than minus 1 or x is bigger than 4. So yeah, thinking about the quadratic, goes across, has roots at minus 1 and 4. We want to be outside those bits, you want to be above, do you know what I mean? So it needs to be outside those two values. All looks good to me. Double check. Yep, everything there is correct. Lovely jubbly. Let's keep going. We've got some cylinder, blah, blah, blah. Collect the rates of change. So this one has the time in it. What's going on? We have, initially the tank is full. It has 1.5 height. Leaks from a small hole. Okay, it's going out. While the tank is leaking, the depth of the water is modeled by this. Use the model to show that this is true. Okay. So let's go on for a second. We have a differential equation. We want to solve this for h. So what we need to do is bring all the h's to one side, all the t's to the other. But here, there's no h's, so it's not even a differential equation. We can just integrate the right-hand side. So h is the integral of that thing. E, when you differentiate, you times by this. When you integrate, you divide by this. This is negative of a fifth, so we're going to times by 5. I'm going to just rewrite this all in terms of some fractions instead. So this is negative 3 on 25, e to the minus t on 5. So if we times this by 5, it's negative 3/5. Oh, it's positive 3 because we times by negative. So we've got 3/5 e to the minus t on 5 plus just a constant. See, all looks good to me. Double check on the mark scheme though. What question number is this? Number 7. Yeah, looks good. Do we know anything? Initially the tank is full. Yeah, so we can find out what these are. A and B are constants to be found, so we can go and find them. We found A. How do we find B? We have the coordinate of 0 and 3/2. i.e. that is for T and H. So as we plug those in, we know that 3/2 is going to be equal to, well, e to the power 0 is just 1. So 3/5 plus C. So thinking about that, what do we have? C is going to be equal to 9/10. Lovely jubbly. Is that all good? Yep, looks good to me. Let's just write it out in one form just to make sure. So 3/5 e to the minus t on 5 plus 9/10. Part B, find the time taken for the depth of the water to decrease to 1.2. So we just want to set this equal to 1.2. Yeah, so just making sure it wasn't like we didn't need to set this equal to 0.3, like how much we've lost. Nah, this is height of the water, it's not height that we've lost. So we know that 1.2, or 6/5, is going to equal to 3/5 e to the minus t on 5 plus 9/10. This is 12/10. So we can take that away and have 3/10 and divide by a 3 times by a 5. We have e to the minus t on 5 is equal to a half. I'm going to walk through that again, just I feel like I've maybe done too many steps in one go there. So 1.2 take away 0.9 is 0.3. So 3/10 equals 3/5 of the e stuff. We can knock off a 3 and a 3 times by 5. E to the minus t on 5 is equal to 1/2. So what we're going to have minus t on 5 is log of a half. So we know that t is 5 log 2. Seems good to me. Yep, spot on. But we want it in terms of hours, minutes, and the nearest minute. Ugh. So 5 log 2, what number are you? 5 log 2, 3.46, 3.4657. Yep. So if we think about that, what you want to do, take that number that you've just worked out, take away a 3. So you left us with the decimals. That's how many hours it is, but in terms of hours, not minutes. So times by 60 to get that in minutes. So it's 27.94. For the nearest minute. Okay, so we're going to round up then. Decrease to that to the nearest minute. Yeah, we're going to round up then, yeah. 3 hours 29. Yep. 28, sorry. This did originally give like 27.9. Yeah, 27.94. So 28 is what we round up to. It's a bit weird. You can, like, if it doesn't say to the nearest minute, I think both would be allowed. Because like, this is the nearest minute. Like, if you round it, you get 328. But if you look on a clock, it would be 327. Because it'd be like 327.56 or something. Do you mean? So it would always read 327, but actually the nearest time is 328. So if it doesn't say like nearest minute, I think both would be valid. Don't see why not. They're both kind of the same idea for the nearest one or the actual time the same. So yeah, so like for time you always round down. You always do the floor function, but for like normal things you round just like generally doing round up or round down. So next part then. In the long term, the water level in the tank falls to the same height as the hold. Find according to the model the height of the hole from the bottom of the tank. Well, you can probably go up here and see a few things maybe, like when is this going to be 0? I don't think so in this case, but we can actually just do it from the equation we have as well. So what did we have? H was equal to 3/5 e to the minus t on 5 plus 9/10. That's our equation. What's going to happen as we let t go to infinity, that implies that our e to the t on minus a fifth, e to the minus t on 5, this goes to infinity, minus infinity, so you have like this is going to tend down to 0. So this goes to 0. So that tells us that our h is going to tend to 9/10. So that's the height of the hole. How far is it from the bottom of the tank? 9/10. Lovely. Always check. I did that say top of the tank, then the answer would be 6/10. Going the other way around to get 1.5. So that's good to me. 9/10 of a thing. Let's keep going. Oh, we've got this little looking TP thing. We've got one curve with this doing that sort of stuff. 8x minus x to the 5 on 2. Equals the x-axis at point A. Verify the coordinate of A is 4. Okay. If we plug in 4, you get 32. 4 squared. 4 square root is 2. To the power of 5 is 32. So, yeah, that's okay. L is a tangent to the curve at A. Use calculus to show the equation of the line. Okay. So, we need to differentiate dy dx. Let's just write that 32 minus 32. 0. dy dx, 8 minus 5 over 2. X to the 3 over 2. Plug in a value of 4. What do we get? We get 8, take away, again, 4 square root is 2, cubed is 8, halved is 4, times 5 is 20. That's minus 12. That's a very good sign with this being in there, isn't it? And now we want to do y minus y1. We know that 0 is equal to m, x minus x1, and then, yeah, expand that all out. Y plus 12x equals 48. Lovely jubbly. Line 2 has the equation y equals 8x. The region R, shown shaded up there, is bounded by the curve line 1 and line 2. Find R. Okie dokie. So what we need to do, first of all, is go and find where do L1 and L2 intersect. What is that point? So L1, we know is y plus 12x equals 48. And here we have that this is y equals just 8x, nice and easy. So what do we get? 20x equals 48. X is going to be 2.4, so what's that? 12 on 5. 12 appearing again is generally probably a good thing. Not too sure. But yeah, at this point, what is it? It is 12 on 5. And the y coordinate, we can just times by 8. So 96 on 5. I don't think there's any nicer way than that. 96 on 5. I'll double check that is that. Yeah, 96. So this is good. What we're going to do then, triangle, little curvy bit. So the integral will work out this curvy bit. Triangle will just work out the triangle. And then we'll do triangle, take away curvy bit to give us shaded bit. So triangle, what's the base? 4. What's the height? 96 on 5. So the area of the triangle, let's call this P maybe. So this is going to be a triangle, OPA, is going to be half base height. So 2 times this thing. So 192 on 5. That 9 looks very 4-ish. 9. That looks less like a 9. I can't seem to draw 9s recently. I don't know. I've lost my ability to write 9 somehow in the last couple of months. So this is good. We've got the area of the triangle. We need this bit. So we want to take our original curve and integrate from 0 to 4. So 0 to 4 of 8x minus x to the 5 over 2. For the 8x, what are we going to get? Raise the power to 2, divide by 2, gives us a 4x squared. Here, raise the power to 7 over 2, and then divide by that power. And we're going to plug in 4 and 0. 0 is nice and easy, everything just goes away. 4 squared is 16, times another 4 is 64. Here, if we square root 4, we get 2 to the power of 7 is 128. That's 256 over 7. So now then, what we want to do is take that away from the value we got up here of 192 on 5. So we need to do 192 on 5, take 64, plus 256 on 7. And hopefully, that is all correct. Everything seems quite nice. The numbers seem pretty straightforward. 7 on the bottom is a little bit like, what are you doing there? But 256 on the top is so lovely. We get 384 on 35. Is that good? It's about what? It's just more than 10, isn't it? How big is this thing? It's quite big. Like, that's nearly 20, isn't it? Like it's quite tall. So it's 20 wide 4, so that's 80. So it's 10 out of the 18. Like the whole thing, that's 80. Do you know what I mean? Maybe. What number are we on? 10. I should get the number of 384 on 35. That's exactly what I get. That's always a good sign. So big tick, lovely jubbly. So everything else, I'm guessing everything else is correct then as well, isn't it? If we've managed to get all these wrong and somehow get everything else correct, that's probably a miracle. Let's keep going. A is positive. Use this substitution. A is positive. So if x is equal to that, what can we say about x and dx d theta? So dx d theta, A is just going to do what A does. Sine, we're going to bring that 2 down to the front. We're going to lower it to a 1. We're going to differentiate sine to get cos. Whack them all together. We're going to notice we have 2 sine cos. So this is a sine 2 theta. Whether we need that, I don't know. But it's good to spot it and have it written down there just in case. Right. Apart from that then, let's think about doing some other bits in here. So you want the root of this. Okay, and we want this happening as well. So let's just plug some stuff in. Let's see what's going to happen. So, as well, the limit. So if x is 0, this needs to be 0. So theta can be 0. If x was a, this would be 1. Sine squared would be 1. So sine would be 1. So theta is going to be 90. Well, when we think about radians, theta will be pi on 2. So yeah, a lot of times it's easier to think in degrees first and then just like translate it to radians later on. Either way, it's fine. So I think we've got everything we need. You can maybe go and work this out. Should we do that? Yeah, let's do that actually. So a minus x is going to be a minus a sine squared x, theta, sorry. Factorize an a out. 1 minus sine squared theta. So this is the same as a cos squared theta. So if we square root everything there, it's the same as root a cos theta, not squared, because we square root. So that's our entire bracket there. The root of a is just going to be root a sine. So let's stick all these bits together then. What we have is that we're going to have the integral of 0 to pi on 2 of x to the half. So not that thing, this thing. So root a times by sine theta, and then times by the square root bracket, which is this entire thing. So root a cos d theta. What we can do then is we can factorize out the root a is making a. This then is the same as like what we did earlier, do you know what I mean? But we've just got half of it. So it's, if we take out an a over 2, pi on 2, 0, and then we should have sine of 2 theta left over, d theta. We should have a squared, and that should be squared, that should be squared. Why are these things not squared? So root x gets rid of a square, that's good. Sine 2 theta, this is squared. Everything seems to, I just need to square everything apart from this 2. What went wrong then? So that does get rid of it. We did this. We got that out. Is that correct? Take the 2 out. Leave the a's alone. We have sine to the 1. Differentiate sine, we get cos. If we had a minus x, it's a minus this thing. So you can factorize out an a. 1 minus sine squared is cos squared. Square root in it. Root a cos a. This was a. So we set that equal to a. So this is equal to a. So that goes equal to 1. Sine's equal to 1 or minus 1. But we'll do it positive. So it's 1. Why is that squared? Should it be squared or is it just like a misprint? Should be squared. Where's the extra square coming from? What have I missed off? Missed off the thing that you always need to put in there, don't I? This bloody thing. This big thing up here. We've missed off an a and a sine 2 theta. So why does it need to be squared? This needs to be squared too. We've just missed off all the bits. So let's sub those bits in there. We don't want to do theta, do we? That's what we hadn't done. We do want to do theta, but we don't want to just add it in. We need to make sure we've got a sine 2 theta, d theta, again times a sine 2 theta, d theta. So that gives us our a squared on 2, pi on 2 times to 0 of sine squared 2 theta. So again, you will make mistakes. You will miss things out. It's okay. You need to learn how to look back through and see what you've missed. You're never, if you want to rely on the tactic of getting every single thing correct first time, you are going to fail. Maybe not fail, but it's going to slip up sometimes. You will make mistakes. It's going to happen. So learning how to go back through and mitigating the mistakes you've made is very important. And noticing like, oh, what's wrong here? Where could that have come from? How has it appeared? And then looking back through and seeing if you did anything or didn't do something. So that's looking all good. Now we just want to actually solve it. So when we have sine squared, if it's not next to a cos, we can't really do anything with it. What we want to do is use the double angle formulas for cos. So cos 2 theta is 1 minus sine squared theta. So if we rearrange that for sine, we have the 2 sine squared theta. Sine squared theta is going to be 1 minus cos 2 theta over 2. So we can always replace the squared with this thing, but where we had 2 theta, this just gets doubled. So this whole thing is still going to have the a squared on 2 at the front, still got the limits of pi on 2 and 0, but this then is now this. So we've got 1 minus cos 4 theta and a half, but I'll make that be a quarter at the front. This looks good. A squared on 4 stays where it is. Integrating 1, we get theta. Integrating cos, well, negative cos, gives us a negative sine. But we need to divide by that integrand, well, the derivative of the integrand. So a quarter. And then plug in pi on 2 and 0. So some things to spot straight away. What's 4 times pi on 2? 2 pi. Sine of 2 pi is 0. That's also 0. So this whole thing, when we put in the 0, everything goes away. Put in the pi on 2, this goes away. The only thing left then is the pi on 2 in there. So what is this? Pi a squared on 8. Is that correct? Let's find out. Number 13. 1/8 of pi a squared. Lovely, jubbly. All looking good. Let's keep going. A balloon is being inflated. In a simple model, it's a sphere. The rate of increase is inversely proportional to the square root of the radius. There's an equation to model it. Okay, balloon is being increased. The rate of increase of the radius, so dr dt, is inversely proportional, equals k over square root of the radius. Square root radius. Yep, lovely. When it's 10 raised to 16, it's increasing at a rate of 0.9. Okay, so we get, again, we're going to have t r dr dt as a kind of triple coordinate. Let's move that over a little, it's a little more like a semicolon. So using that, what do we actually have? T is 10, r is 16, dr dt 9 on 10. This is 2 bits of information. It's 2 points, 10, 16, 10, 9 tenths, depending on whether you're looking at like t and r as an equation or t and dr dt as an equation. From here then, let's solve. It will give us 2 unknowns. We have the k already. 1 more will appear from the integration. They will then use with the 2 points we have to solve the 2 unknowns. Just simultaneous equations, just fancy simultaneous equations at the end. Let's do the integration then. It is a differential equation, so we need to bring our r's to one side, t's to the other. 1r there, dr on this side, so let's bring that over. We've got root r dr, and that's going to equal to k times t. There's no t's anywhere else. What do we get then? Let's rewrite that root r. That's r to the half. Raising that power, r to the 3 over 2. Divide by the power, 2/3 out the front. K becomes kt plus a c. This all looks good. Again, sometimes it's better to do that 2/3. That's the power of 3, 2, but I'm going to leave it alone. We know some numbers. Let's plug some bits in. What we can do then, we're going to plug in the point, because this is r and this is t. This is not in this equation. This is dr dt. I don't see a dr dt there anywhere, so I'm not going to stick that in there. I'm just going to simply, I know this is r, this is 10. They're going in. 2/3 of 16 square rooted is 4. Cubed 64 is equal to 10k plus c. So we've got one relationship there. We can probably go and look at this one and notice there's no c in it. So this has 1, this has 2. We really should have done this one first. So let's go and use that. dr dt, 9 tenths, is equal to k over r, or root r. R is 16, so root of that is 4, so k over 4. So it tells us that k is equal to 18 on 5. Yes. And now we can take that then and plug it straight into this stuff. So, or into down here, so 18 on 5. So times that by 10 is going to be 36, yeah? So we know what C is then. It's going to be whatever number this ends up being. So 128 on 3. Take away a 36. We've got 20 on 3. We had that number earlier for something, I think. So that's good. Let's always make sure we do write this out in one full equation at the end. So we're going to have, where is it? 2/3 r to the 3 over 2 is equal to k, which is 18 on 5t plus 20 on 3. We need to get these to say, that needs to be a 10, or need to get rid of this thing. So we'll times by 3 over 2. So yeah, the 3 goes, divide by 2, gets that a 10. This is looking good. We need 2/3 of this thing, yeah? So 2/3 of 18 on 5. 18 on 3 is 6, so it's 2/5 of 6. 2/5 of 6. If you think about, what's that going to be? 2/5 of 6, 12 on 5? It's not the right number, that is it? Let's double check on my calculator. 2/3 of 18 on 5. 18 on 5 is 3.6. Times 3 over 2, that's why. Times 3 over 2, not 2/3, 3 over 2. Very easy to do these, very easy. If we do that, it does give us 27 on 5, which is 5 over 4. 27 on 5 plus the 10 we have. Lovely. Looks all good to me. Hence, find the radius of the balloon when t is 20. Oh, just plug in 20. Okay, yeah, plug in 20. So if we do that, let's just do that in a calculator. So 27 on 5 times by 20 plus 10, 118. So that's equal to r to the 3 on 2 equals 118. So r is 118 to the 2/3, which obviously they want a number, power of 2/3. You get 24. Was this in millimeters? It's 24 point blah blah blah, but 0.0 blah blah blah. Is it millimeters? No, that's in centimeters. So what that tells us is it's 24.0577 centimeters. So 241 millimeters. So fiddly that, isn't it? So fiddly. Is that correct? Let's find out. 14, 24.1, 24.1. Oh, they don't. Okay, yeah. Okay. So this is all good. What's number 4 saying? Just a limitation of the model. Well, balloons burst. We don't track it bursting, do we? No. Yeah, this has radius. There's no upper limit on the radius in this. If you look at this equation, what's going to happen? We just keep. This is a linear thing, so this just goes off to infinity. Yeah. So this will go off to infinity as well. 2/3 ain't doing it, so it must be the r that's doing it. So yeah, the balloons can't be infinite size. Simple as that. Balloons will pop before they get to the size of the universe. So this is good. Go on to the next one. We've got, I'm guessing it's just, find all that stuff. Oh, just define it. Okay, just defining it is fine, surely. I think that's, I'm overthinking it. I don't think there's anything else. It's not really differentiation though. Yeah, I think is it really as simple as, do we know we don't know the equation, that's why I was wondering why things are not coming out the way that I thought they would be going. Skip for those. So yeah, we need to work out the equation. That's what we've got to do. We know that this is happening. We know it's over there. So we can say a few things like this is a quadratic. Yeah, is it quadratic? Yeah, quadratic. So that turning point tells us x plus 2 squared minus 13. So plus 13. We just need to kind of scale it up. So it's like what number is going to go here. So alpha is going to go there. But you can tell when we put in 0, we need to get 25. So this is going to be 2 squared is 4. This is 13. So we need like 12 to come from here. So we need this to actually be 3 at the front. So that's our y. That looks good. Do we need to find then this other line? L is just a line. Okay. Well, how far does it go? That's 13. That's 25. It's gone up 12 every 2 steps. So it's 6. So y equals 6x plus 25. and then we know that we're in between those. We're below the straight line and above the other one. What we'll do, yeah, and this wasn't integration, was it really? We'll just do it. We'll just do it very quickly. So we want to integrate to find r between -2 and 25. What's going to happen? We need to do the difference between the top one and the bottom one. Sorry, -2 and 0, not 25, the x coordinate. Yeah, top one is the line, so we're going to have 6x plus 25. And then we'll take away this thing. I will expand it out. So what would we get? We'd get an x squared times 3. I'd get a 4x times 3. I don't know, I should have a 25, shouldn't I? So that's good. So we want to take that one away from what we had. 3x squared. How many x's was it? 12. That's 25 dx. 25 go. We got negative 3x. 6, take away 12, negative 6. 6, that's a 0 in it. 0. 0. So doing the integral now, raise that power, we get a 3. Divide by it, we get a 0. We get a 1. We get a 3x squared there. Plug in 0 does nothing. Plug in 2, we get 8 plus 12, 20. Looks good to me. No, that's correct, obviously, because it's just one I've made up, but a little bit of practice. Let's keep going. We need to differentiate this thing. This is a product rule. So what we're going to do, let's differentiate the bracket. So it's going to be 4 lots of 2x times by the other bits minus e to the 2x. And then let's integrate the e thing. We'll get minus 2e to the 2x times by the other stuff. So that 2 would times it by 4 to make an 8. 8e that, and then x squared minus times 2. Let's factorize some stuff out. What can we take out? This is a minus 2. We'll take out a 4 e to the minus 2x. What we're left with, I've got 2x in there, and I've got these bits, but these need to be doubled. So minus 2x squared plus 4. Yeah, and I can take a 2 out. So what have we got? 8. And I will put the 4 first, but now it's going to be a 2. The x is in the middle, so that's just a single. And then like the x squared at the end. And we still have the e to the minus 2x. Lovely jubbly. Find the simplest form of the exact coordinate of the stationary points. So it's just solving this quadratic, yeah? If we set this equal to 0, what are we going to get? Well, we'll have x squared minus x minus 2 equals 0. So is that what? X minus 2x plus 1 is 0. Is that correct? Yep. So x is minus 1 and 2. So using that, we need to find the y coordinates of those things. So plug in minus 1 and 2 back in. Minus 1, square and it's 1. Take 1 is minus 1. So minus 4 e to the 2. And then if we plug in 2, 2 squared is 4, take away 2 is 2. That makes an 8 e to the minus 4. That looks good to me. Double check all of those. What number are we on? Number 9. Oh, it's another paper done. Let's keep going. Oh, we're back to October 2020 now, this one. Number 9, yeah. I get minus 1, minus 4 e to the minus 8. Yep. 2 and 8 e to the minus 4. Lovely. These are transformations, so we're not going to worry about them now. Use a u substitution. So u squared plus 1. Differentiating this, what are we going to get? Dx du is 2 times u. Also, does it help us to do anything else down here before plugging it in? Yeah, look at that. Look at this. If we rearrange for u, what are we going to get? We're going to get the u is x minus 1 square rooted, but a bit easier than that. It's that whole thing, yeah. It's that whole thing. This is u squared as well. So let's start subbing some of these bits in. Well, let's do the limits first, actually. So if x is 10, then u squared is 9, so u is going to be 3. And if x is equal to 5, sorry, u squared is 4, so u is 2. So what we should have, our integral that we were given, with the limits of 2 to 3. And we also need to think about then on the top, we had a 3. We now know the dx, which is a 2u du. On the bottom, we had an x minus 1, that's a u squared. And this big bracket, which is 3 plus 2u. That looks good to me. Let's evaluate some stuff. 6 on the top with a du. The reason we've got rid of that u is because we can go away with one of those ones down there. U and 3 plus 2u. Still with our 3 and 2 on limits. And from here then, we want to integrate, or do we need to actually do it? Yeah, we do want to do it. So that's good. That looks like everything's matching up. We've got 6s, we've got 3s, we've got 2s, we've got u. Yeah. So doing it, what's going on? We've got a polynomial thing on the bottom, but we don't have one of a lower order on the top, like the directly lower order. This is 2, this is 0. There's not a 1 difference. So partial fractions. We want to end up a over u plus b over 3 plus 2u is equal to 6 over u 3 plus 2u. So what we know, a 3 plus 2u plus bu equals 6. So what we can do, we can just look at the powers. U to the zeros, how many constants are there? 3a. How many constants on the right? 6. A is 2. U to the 1, how many are there on the left? I've got 2a plus b equals 0. So I know that b is negative 2a, i.e. negative 4. So my integral is now the integral from 2 to 3. A over u. A is 2. 2 over u. B is 4, but negative, over 3 plus 2u du. Both of these now individually are log ones. Both of them are too big. This differentiates to 1, this differentiates to 2. So let's take out a factor of 2, and then they are correct integrals. So the log of u, take away the log of 3 plus 2u, with a 3 and a 2 going in. Before working this out, I'm going to work this into 1. Nah, we won't do that. We'll still just have 2 lots of plugging these limits in. Log 3 minus, that makes 6, plus 3 is a 9, so minus log 9. And then we're going to have take away log 2. And then this is going to be 4 plus 3 is 7, so plus log 7. One thing to spot log 9 is 2 log 3. So what is this all together? 2, we'll have a log 7 at the front, take away a log 2, and then this stuff was log 1 to log 3, take away 2 log 3, so we have minus one of them altogether. So yeah, 2 lots of log 7 minus log 2 minus log 3. What number is this? 10. Let's keep going. Number 10. We say, oh, they want it one form. Oh, one log form. Okay, one log form. Let's do that one. So 2 lots of log 7 over 2 times 3. So doing that, what do we get? We get a 6 on the bottom and a 7 on the top. Squaring both of those. 49 on 36. Looking good? Looking lovely, that is. Big tick. 10 marks on the board. 10 marks on the board. That's the difference between having like a high C and a low A. If you can do this stuff. So let's keep going. Balloon's deflating now. Oh, sad balloon. Has a radius r, volume v. Model at a constant rate of decrease. Using the model, show that this is true. Oh. Yeah, okay. Show that it's that. Oh, the volume is decreasing at a constant rate. Okay. So this is connected rates of change. So that sentence, the third one there, tells us that dv dt, the rate of change of the volume, is decreasing at a constant rate. So it's equal to negative some number alpha, where alpha is going to be positive. I'm not using k simply because I'm not entirely sure if that is going to be exactly the same k. It could be that I end up with like this is half of this one, do you mean? There could be some slight variation that goes on with it. So I wouldn't use the same letter they've given you. Use a slightly different one to start. That's good. Do we have an equation for v and r to link them together? Yes, it's a sphere. So v is 4 on 3 pi r cubed. But we want to somehow get rid of this, like get rid of the v. So we need to differentiate that. So what we're going to have is that dv dr is equal to 4 pi r squared. The reason we've done that, if we look down here, like dr dt, we don't have any of those bits. We've got no relationship for r and t. So the only way you can work with this is by getting a dr dv times a dv dt. So we use the other variable, the volume in this case, as like a bridge to kind of link us between the radius and the time. I know we've got dv this is dr dv, but we can just flip it, stick it. So let's do that. We're going to flip it. We'll have 4 pi r squared on the bottom, and the dv dt minus alpha. So looking at what we've got, we can see that this is the same as minus k on r squared if k is equal to alpha on 4 pi. So exactly what I was saying. We don't want to use exactly k because it's not necessarily going to be popping out just exactly what they've said. I mean, you might have some scale factor of it. But that looks all good to me. Given that the initial radius of the balloon is 40, so we have 0, 40 as one coordinate. After 5 seconds, it is 20. 5, 20. The volume of the balloon continues to decrease at constant rate until the balloon is empty. Find a complete equation. Okay, so what we've got is dr dt is equal to minus k on r squared. You might think, why don't I use the 4 pi, like alpha on 4 pi? Why would I use that? It's more complicated than this one. I'll use the simpler version and solve for k. So as we do this, what's going to happen? I'm going to bring all my r's to the left. R squared dr is equal to negative k dt. Again, no t's here, but they would go to the right. Integrate, integrate. What do we get on the left? We raise the power to a 3, and then we divide by that power. On the right, we times by a t, that raise the power from 0 to 1. Add on a c. So we know a few things. When t is 0, r is 40. So yeah, 0, 40 straight away tells us that c is a third of 40 cubed. Actually, let's do something ever so slightly different to make it a bit easier. This c is now a third of c, because that way we can times it by 3. And actually, this k, I'm going to change it. We're going to call it like not alpha but beta on 3. So everything now is on 3. So what we can do then is just banish all of our 3's. We don't need all of these thirds. So we effectively have r cubed is equal to minus beta t plus c. So r cubed is a straight line. So doing that, what do we get? We get, in this case, our c is just going to be the cube root of 40. No, 40 cubed, sorry. 40 cubed. And when we plug in the 5 and the 20, what are we going to get? Well, we'll have 20 cubed is equal to minus 5 beta plus 40 cubed. So we know beta should be 40 cubed, take 20 cubed, all over 5. That looks good to me. Again, should probably write this down. So we know that r, find the complete equation linking r and t. At no point did it say it had to be explicit. So I will leave this as r cubed is equal to negative of that thing. So 20 cubed minus 40 cubed over 5. Lots of t. Plus the c of 40 cubed. That looks good to me. Find the limitation on the values of t and find which spot's valid. So this is a balloon, yeah? It's going to decrease. Balloons cannot have a negative radius. So at some point, this being a negative number is going to go and hit the origin. Hit the origin? Hit the x-axis. When does that happen? When y is 0, or in this case, when the radius is 0. So rearranging, we can see it should, like, in general, if you had y equals mx plus c, the x-intercept happens at minus c on m. So it's the same thing here. This should happen when t is minus c on m. So on the general m. So 20 cubed minus 40 cubed, and that on 5 I will whack on the top. That all looks good to me, whatever number that is. Find the limitation, values on t. Okay, so that is the upper bound of t. So we actually know that t is less than that. Less than or equal to, is it still a sphere if it's got radius 0? Is it? Depends how you define it. So generally they're defined as like 3D points that are the same distance away from some point. So in that way we could say yes, because it's just all the points that are 0 distance away. But yeah, it's good. This time, I'll double check that does give me the same number that they've got. So 5 times 40 cubed divided by 20 cubed to take away 40 cubed. I get 40 on 7, which is, yeah, exactly what they have. This isn't like negative 40 on 7, but yeah. Lovely. That's all good. Yeah, t has to be less than equal to that. It does say, yeah, up to and including. So they do allow the fact that a balloon could, in theory, have 0 radius. So you're allowed to include the 40 on 7. Oh, sorry, it should be positive. One about. Yeah, we can include this one. Let's keep going. Number 15. Implicit. Show that dy dx is this. We know that that is that stuff. So as we do this, differentiate x squared, we get 2x times it by the normal bit, tan y. Differentiate tan y, we get 6 squared of y, dy dx. Times that by x squared, add those up, set them equal to 9, we differentiate it, is 0. Let's rearrange this for dy dx. We're going to have, we can divide the x off. So we're going to have minus 2 tan over, make that sure it's a y, x 6 squared y. This looks good. Obviously, we don't have any y's, do we, in our answer that we're looking for. So we need to take this original expression and then rearrange it with this sort of stuff. So if we get tan y by itself, what's tan y going to be? Well, that's 9 on x squared. And if we think about in general, cos squared plus sine squared is 1. So divide over by cos. 1 plus tan squared equals sec squared. So this thing is 1 plus tan squared, i.e. it's this. Like 1 plus that thing squared. So minus 2 lots of 9 on x squared over x times 1 plus 9 on x squared squared. So 81 x to the 4. And this looks good. I think from here then, what do? We're just going to times top and bottom by x to the 4, are we? I think so, yeah. X to the 4? No, x to the 3. X to the 3. Yep, times bottom by x to the minus x to the 3. And we get minus 18x on the top. This would have been an x, but now it becomes x to the 4. This would have been x, well, 81x to minus 3, but it's now just 81. So that is exactly what they wanted. Lovely jubbly. Prove that it has a point of inflection here. They changed since I did that. So I think now all you have to do is show that we found dy dx. If we plug in, like, what number is this? Actual number, like decimal number. That's an approximation of it. Power 2.25. 2.28. So what we can look at is this idea. We can do, it's 2.279. So let's look at 2.27. We know that's less than 27 to the power of 1/4. And let's also look at 2.28. And what we want to show effectively is that where it has a point of inflection, both ways have the same gradient, like both sides of the line have the same gradient. So if you had a turning point, what you generally see is that you're going to yes, it's definitely not going to be like a turning point, is it? It's definitely not a turning point. So you plug in that, you don't get 0. The only turning point we have is at 0. So what's going on is this, like you're going to go up and carry on going, but it's kind of this weird point where you think about, like, we were falling over and now we're falling up again. So what's changed at that point? Well, the gradient is still up in both cases, yeah? Nothing's happened there. But what we have is that the second derivative, the gradient was falling. So you think at one point it was pointing very much up, and here it's pointing much flatter, but then here it's pointing flatter and again very much up. So the gradient was decreasing. Now the gradient is increasing. So what we need to have happened is that one side, the second derivative, is positive. One side, second derivative, is negative. It could obviously be the upside down of this as well. But first things first then, we need the second derivative. So we've got this. Yeah, we've got that thing. It's going to be the quotient rule. So if we say u is 18x, but with a negative, u dash is negative 18. V is x to the 4 plus 81. So v dash is going to be 4x cubed. So if we actually get the second derivative out, what do we have? d2y dx squared. That's going to equal to, we need u dash v minus uv dash on v squared. So u dash is minus 18. V is all this stuff, x to the 4 plus 81. Take away u, so plus 18 x times by 4x cubed. That looks good to me. As we look underneath then, v squared, okay, x to the 4 plus 81 all squared. So let's do some stuff with the top. What's going on there? We've got minus 18x to the 4. This is 4 lots of 18x to the 4. So we've got like 3 lots of them. So 54 x to the 4 minus some big number. 81 times 18. 1458. Let's make it work. And the bottom, still the same, x to the 4 plus 81 squared. What's going on here then? Now it's just a case of plug in both of our numbers. So what you can see is we're going to plug in effectively like x to the 4 is 27, yeah? I feel like this should have been a 27 that popped out. No, but we can do something very fancy. It should be a 27, but if we times this by 50, it's not 27, but we need to times this by 54. So what we can do, steal a 54 from both. Could we have spotted that from here, maybe? Yeah, we could maybe spot that we can get, like, there's definitely a 9 in there, definitely a 3 in there. Do you mean the 27 or 54 can appear? So 9 and a 6, 9 and a 6. So 1458 divided by 54, what do we get? 27. So this is x to the 4 minus 27 all over x to the 4 plus 81 all squared. So what we can see then in this situation, if we have that a number's bigger than x, then the power of 4 of it is also bigger than 27. So effectively, yeah, x is bigger than 27 to the power of a quarter. What does that imply? It implies x to the 4 is going to be bigger than 27. So when we were to take away 27 from that, we can see that x to the 4 minus 27 would be bigger than 0. So that would tell us our second derivative is bigger than 0. And then exactly the same sort of stuff is going to happen. That we write exactly the same line, duplicate it, but with now all of these greater thans get swapped out for negatives. I used to like when I was younger doing this, you know, have plus minus, so you can have like greater than, less than. I don't know if you'd be allowed to do that in the exam, but I think anyone that's got a degree in maths would understand what you're doing if they know that this is what needs to happen and you're doing this as both ways. I wouldn't risk it though, but anyone should understand what they mean by that. But you can see what we've done. We've shown that as we are either side of our root or of our point of inflection, one side has one side has the second derivative increasing, one side has the second derivative bigger than 0, one side is lower than 0. See, on the right, we're going up. So it's this exact example is what's happening. It's falling over, and then starts picking itself back up again. Doesn't have to go flat. So it can just be like something like that, do you know what I mean? Where this, you can see that point is like, I'm falling over, and then falling back up again. So it's always that we're trying to find. It's a point of inflection is basically when your acceleration is 0. It's when you start to like put the brakes on or put the acceleration on instead. Not the actual point that you change direction, but when you start to try and change direction. So this is looking good. Let's keep going to number 8. Scientists is studying the growth of 2 different populations of bacteria. The first bacteria, followed by this one, A and K are positive constants. There were exactly 1,000 populations at the start of the study. Okay, it took exactly 5 hours for the population to double. So the 1,000 to start with, A is 1,000, yeah. Plug in T is 0, that goes away, it goes E to the 0, which is 1, N equals A, so A is 1,000. We are 5 hours to double, so I know straight away that K is a fifth log 10, fifth log 2, I want to say. But we can walk through and get it by setting, we could set this equal to like 500 and this be 1,000, but you have doubled. So it should be log, yeah, I think I was log 2 or log 5. We've doubled, so we know that the E to the K, but 5 for T, equals 2. So yeah, 5k equals log 2. So k is a fifth log 2. You can basically, in general, like e is your scale factor, or your, what do you call it, exponential number base thing, whatever you're using. Then natural log of e. What do you want it to do? I want it to double. How long? Every 5 years. Nice and straightforward. So let's just write that all together. N equals 1000 e to the k, which is what, 1/5 of log 2. So it's going to be t times that, 5th of log 2. We could write this ever so slightly differently. It's 1000 to the power, but times by 2 t on 5. So it's doubling every 5 years. Because if you make t be 5, you've exactly doubled once. So that is good. What we're going to do now, find the rate of increase in the number of bacteria in the population exactly 8 hours after the start of the study. So we want to differentiate. What I'm going to do is do it just with these letters. Makes it a little bit easier than having all that faff. So I want d, n, dt. So my a stays where it is, my k comes down, my e to the kt stays as it was. So if I want to evaluate that one, that's 8. dn dt when t is 8. What am I going to get? A k e to the 8k. That's the answer I want. Let's just plug in the values I have. So 1000 times k, so it's going to be 200 log 2, times by e to the 8k, so times by 8/5 of log 2, or e to the 8/5 of log 2. Lovely. Have any of that, whatever number that is. Let's whack in the calculator. 200 log 2 e to the power of 8/5 of log 2 gives me a number of 420. Do we need any decimals or anything? Why is that so small? Should it not be bigger? It should be bigger than 1,000, shouldn't it? We're doubling every 5 hours. We've more than doubled here. Did I type it in correctly? 200 log 2 e to the 1.6 log 2. Well, we could do something ever so slightly different. Where's rate of increase? Rate of increase. Yeah, what am I doing, silly? So yeah, we're gaining 420 every hour at that point. That kind of makes sense. If you gain 1,000 in the first hour, in the first 5 hours, you're going to gain, so you've doubled. You're going to gain 2,000 in the next 5 hours. So you think you need to really be doing like 400 an hour, don't you? It should be the average is 400 an hour. So if you did 7.5, I think that would come out exactly 400 if we did 7.5 instead of 8. That's looking good. It might not be that. It might not. I don't know if that's exactly how it works. It seems like it seems good. It might be somewhere close to it if it's not exactly that. So number of bacteria in the second population given by this thing, where k has been found, and t is time in hours. Given that t hours after the start study, number of bacteria achievement was the same. Okay, so the one we had above, 1000 e to the kt is equal to 500. 500 e to the 7 on 5 kt. Just trying to copy that down correctly. Yes, yeah, that's good. Okie dokie. So what do we want to do? This and this. Let's make that a bit nicer. We've got 2e to the kt equals e to the 7/5 of kt. What I'll do now is divide by e to the kt. So I've got 2 is equal to e to the 2/5 of kt. So 2/5 of kt is going to equal to log 2. And now let's just rearrange for t. So t is going to be 5 over 2, or 5 log 2 over 2k. So that's good. Let's work out what number that is. Let's save k is 1/5 of log 2. Save that in the calculator. Now we've got 5. Okay, I think actually we can just do this a bit nicer, can't we? Yeah, it's 1/5 of, so that's 2/5 of log 2 on the bottom. So we've got 5 over log 2 over 2/5 of log 2. Goodbye, log 2. Times 1 by 5, 25 on 2. Double check that's correct. What number are we on? Number 8. Oh, new paper, isn't it? 2021. Nearly out of paper ones now. 8. I get a number of 12 and a half. 12 and a half. Yeah, lovely. Next one then. What we got going on here? It's a trapezium rule. Yeah, I'm not doing trapezium rule. That's numerical methods. It's hopefully no issues with that, Jimmy. It's log of x squared. They want to integrate that. Okay, so we can't integrate log straight away, let alone log squared. So what we need to do is do by parts, but we're going to be a little bit scared, not scared, be a little bit careful about it, a little bit sneaky, a little bit smart. 1 times log x all squared. So you'll do by parts. U is 1. No, u is log x squared. So u dash is 2 log x times by 1 over x. V dash is 1, v is x. So this ends up being u times v, x, log x all squared. Take away the integral of u dash v, so 2 log x. And this we have to do the same thing again. We have to go through and say that u is going to be, I'll put that 2 at the front so we don't have to deal with a 2 in there. U is going to be log, u dash is 1 on x, v dash is 1, v is x. So this bit of it, we've still got the x log x squared at the front. Take away 2, lots of u times v, so 2x log x. And then take away the negative, so plus on the integral of these 2 terms together, so plus the integral of 1, so plus x. And then plus ac. Does that all look good? Yeah, it does look good for me. But we want to find the exact area. So what we can do, we can apply the limits of 2 and 4. So 4, 2, 4, 2, 4, 2. And then around this whole thing. That plus c we don't need anymore. 4 and 2. So let's put in the 4. We're going to have 4 lots of log 4 squared minus 2 times 4 is 8 log 4 plus 4. And the whole thing take away with the 2's. So 2 of log 2 squared. Take away 4 log 2 plus 2. Delete that one. So with the log 4's, like everything can be log 2 at the end, isn't it? Yeah. So these log 4's, what's going on? Each log 4 is 2 log 2. So I square that. That's the same as 2 squared and then log 2 squared. So this is effectively, like this whole thing is 4 log 2 all squared times up with 4 is 16. This is 16 log 2 squared. Same idea here, this is 2 lots of log 2 in it, so minus 16 log 2 plus a 4, but that 4 and this 2 are going to go away, that's a 2. Then we'll take away 2 lots of log 2 all squared, and we'll add on 4 lots of log 2. So collecting everything, how many squares? We've got 14 of them. And we've got how many normals? We've got minus 12 of them. And then still with a plus 2. I would like always to write like log squared as like ln squared of x, something like that. Like you do with sine or cos, but I don't think that's something that a lot of people do. So not something I would recommend doing in the exam. I think again they'd understand you, but if you, the only way I'd ever do it is say like let ln x or like ln y of x equal ln x all to the power y, and then you've kind of like defined it. If you put this little double dot as well, that's like a definition. This one is like definition equals. So you like define how you're using some new notation if you want to do it, but whether you want to do it in the exam, different question. So is that correct? Is it correct? What number is it? Number 11. We needed 14, a 12, and a 4. We've got a 14, 12, and a 2. Why have we got a 2? Oh, I know why. 2 there. So when we did all of the next bit, this should have been a 2. So we should have doubled all the values. The first one, instead of being a 4, should have been an 8. The second one should have been a 2, should have been 4. And now 8 take 4 gives us 4. Lovely. So again, just a little thing. Hard to spot that in the exam, obviously, but so many little things are going to appear everywhere. So given this is true, show this is true. Okie dokie. So this is another quotient rule. Seems like there's been a lot of quotient rule. So uv minus uv dash is on the outside, v squared on the bottom. What is u? U is x minus 4. What is u dash? It is 1. What is v? 2 plus x to the half. So v dash is x to the half, so half x to the minus a half. Sticking everything together then, dy dx, I don't know why I've started so over there, let's start left a little bit, is going to be u dash 1 v. So 2 plus, I will write this as root x. And then minus u, so I must do plus 4 minus x, then v dash, so half x to the minus, like that. Let's change this one to be normal one. We don't need those brackets on the first bit. And now then, we can have a v squared on the bottom still. So we're going to have 1 on 4 x to the minus 1. And looking here then, on the top row, what have we got? Lots of things have to cancel out. So ideally, when we expand on these brackets, lots of things do. So let's have a look at that. We're going to have still the 2 plus the x to the half. And now we're going to have a 2x to the minus half. And we're also going to have a, so this is going to make an x to the half, yeah? This is minus x to the half. Minus a half x to the half. So things are not cancelling out there. What's gone wrong? What's gone wrong there? So we should just get a 1 on the top. Well, I should just have a number on the top. Yeah, they do not cancel out. Should that be like that? Yeah, because that's just the that's just the original one, isn't it? Yeah, that's just u. Yeah, that's just u dash times v. And this then is u, but the negative of it, times by v dash. That's true. Let's maybe go back a step and times top and bottom by root x first. So doing that, we'll have, what I'm wondering about is this 2 plus root x. Now we're going to times by, so yeah, we're going to get 2x to the half plus x plus a half of this stuff, so plus 2 minus x over 2. This still doesn't seem to be cancelling out correctly. What's gone wrong here? Oh, what am I doing? The bottom, I've done the bottom all wrong, that's why. The bottom should be v squared, isn't it? So 2 plus x to the half squared, yeah. So you see, when things are not coming into the show that, it can be this little something else, like you've just read v dash instead of v. Something that's so subtle that you might not always notice that you're going to do. Expanding this out then, what do we get? We get 4 plus 4x plus x. Ah, this looks good, doesn't it? So on the top row, let's collect some things. We've got the 2x to the half. We've got a x and a minus half of an x. So we've got plus a half of an x. And then we've also got the just standard plus 2 on there. And on the bottom row, we need to have, this actually is a half in the middle. So I'm going to write them in that order. Same order of the power as a half, plus an x, plus a 4. And what we can see then is the bottom row is the same as the top row. It's just doubled. Should I have my powers be slightly different? Yeah, I times this by 1 on 2. Yeah, it's the same thing, the top and bottom, but it's 2 times bigger. So what this is 1 over 2 root x. Just to clarify, yeah, I times top and by this, but I didn't put it down the bottom. So hence why this, look at this, and then look at this. They gained half an x. This one disappeared, so I needed to whack one down there. This stuff is all the same as this, but twice as big. So that looks good to me. Keep going, number 50, oh, number 7. So find r. What do we need to do? We need to integrate this thing. So the first bit It's just, we can just do that, yeah? What's that going to give us? It's going to be e to x. This bit, though, is product rule. It's a product, so it needs to be the integration. So, by parts. By parts is the product rule, but integration. So if we have, we're going to have u v dash, that goes to u v minus the integral of u dash v. U, we can say, is x, so u dash is 1. V dash, we can call e to the 2x. So v is going to be a half e to the 2x. So going all together, what do we have? X over 2 e to the 2x minus the integral of these things together. So it's just the integral of that, that's 1. So that's a quarter of that. That's good. And noticing that we had negative there, so it's actually like negative all of these bits combined together with the bit we found there. That looks good. What are our limits? 0 and something. Well, when is it going to equal 0? Let's just factorize that very quickly. Let's take out an e to the 2x. What do we get? I get a 2 minus an x. So it's when it's 2. So we want to actually integrate this. So the integral of y dx from 0 to 2 is going to be the value of r. And that is equal to the integral of, so the limits of this thing with a 2 and a 0. So is it worth doing anything inside the brackets? It probably is, because we've got e to the 2x and e to the 2x with just constants at the front. So I'm going to take out, first of all, a quarter and a quarter and an e to 2x. So what do I need? Well, this is going to be 1 minus a quarter. Sorry, 1 plus a quarter. So 5 quarters. This thing is going to be negative, and there's an x there, but it's negative a half, so it's 2. Negative 2x. So that is good. Find the exact value. So still we want to plug in all of these with 2 and 0. So with the 2, we'll get e to the 4 on 4, lots of 5 minus 4, so lots of 1. And with the 0, we'll get, so minus a quarter times by 5, so minus 5 on 4. So altogether, e to the 4 minus 5 on 4. That look good? Seems good. Number 7, oh, next paper. This is the specimen then now for paper 1. If it's going to load, is it going to load? No, let's refresh. There we go, what number are we? 7. A quarter e to the 4 minus 5 e to the 4. Yep, lovely jubbly. Let's keep going then. See as this equation curves by the point 1, 7. Use differentiation from first principle to find the value of the gradient of the tangent to C at P. Okay. So we need to find f dash of x. Oh, we'll call this f of x. So we want to find f dash of x. That's going to be the limit as h tends to 0 of f of x plus h. So 2x plus h cubed plus 5. Take away just normal f of x. So take away, I'm going to put in brackets, 2x cubed plus 5 all over h. 5 and 5, goodbye. If we expand this out, you'll notice it's going to be the same as earlier. We have the limit, h tends to 0. I'm going to take a 2 out. We've got 2's everywhere that we can 2's out. 2 can just come with us. So 2 can go over there. What we're going to get, x plus h squared, x cubed, x squared h, x h squared, h cubed. By Pascal's triangle, 1, 3, 3, 1. And then we'll just add them all up. Take away the x cubed we have on the end. So what's going to happen? X cubed and x cubed. Goodbye. Still got that h on the bottom. But now, as we look, like everything's either got h or a higher power. There's nothing that doesn't have a h. So what we can think about is just dividing it by h. We'll have 3x squared plus 3xh plus h squared. So now we plug in the 0. What are we going to get? 0 and 0, because 0 times anything is 0. 0 squared is 0. So it's just this bit left over. So 3x times 2 is 6x. What I'd actually probably do is write this as like 2 lots of 3x squared plus 0 plus 0. So it's equal to 6x squared, which is exactly what the answer should be. We then need to actually find the value of the gradient when it's 1. Okay. So therefore, f dash of 1 is 6. Lovely, jubbly. Is that correct? Yes, it is. I think I knew that anyway. Ooh. Okay. Show that this is true. What do we need to do? Well, we've got some sort of quotient here. So, is there anything that we're able to do to get rid of this? Let's expand the top maybe into sine 2 theta. It's not something you see really. We have this situation where you've got like this thing on the bottom. We could do a substitution. That could be a possibility. I'm wondering if we can just like times something by 1 minus cos, and does that do something that's quite nice? Does that do something quite nice? So if we times by 1 plus cos, what's going to, like 1 minus cos, we'd have 1 minus cos squared in the bottom, so that would become sine squared. So the bottom would be sine squared. The top is sine cos, times that by 1 minus cos. You'd have sine cos minus sine cos squared. This is still just sine 2, so that's okay. This is the reverse chain rule, so that's okay too. But we'd have on the bottom still sine squared. So this would become cosec squared times, cos times cosec. So that's not going to work as the reverse chain rule, and it's probably not going to be the nicest way to do things. So we're not going to do that. We're going to do a substitution. So let's do that. U equals 1 plus cos theta. So du d theta. What we're going to get? We're going to get a negative sine theta. What I'm going to do as well is think about this actually as being 2 sine theta cos theta. Because then what we can do is like using this, we can think the du or negative du, to make it a bit easier, is the same as sine d theta, sine theta d theta. So like we can steal the theta from there, group it with the d theta there, and replace the whole thing for minus du. The only other thing to think about then is the coses. We have u plus 1 is cos, so cos theta is u minus 1. For our limits then, if we had that theta is equal to 0, so theta equals 0, what does that tell us? That's 1 plus 1 is 2. If theta is pi on 2, that's 0 plus 1 is 1. This should say u equals... What's making that noise? That's me. So that looks good. I think we've got all the parts. We've got our limits. We've got our differential bit, like the d theta. We've got the bit inside the integrand. So let's stick them all together. Let's call it I. So I is equal to, instead of 0, we have a 2. Instead of pi on 2, we have a 1. Instead of sine 2 theta, we expanded that to 2 sine cos. But what we're going to do is steal one of those signs with this. So we've got 2 cos. But we don't want cos. That's u minus 1. On the bottom, and the du, and the negative. On the bottom then, 1 plus cos, it's just u. So this whole thing, what we can do as well with this negative, we can flip these limits around. So it's going to be the integral from 1 to 2 of, looking inside here, we can take a 2 out the front. We've got a u minus 1 over u. So I've got a 1 minus 1 on u du. If we perform this now then, 2 out the front is still there. Integrating 1, what do we get? We get u. Integrating 1 on u, we get the log of u. Plugging in 2 and 1, what's that going to give us? So 2 lots of 2 minus log 2. Take away 1 minus log 1 is 0, so it's just take away 1 there. So doing that, what do we get? 2 lots of 1 minus log 2. Is that it? When we expand those brackets, it is, 2 minus 2 log 2. Lovely jubbly. That looks good to me. That looks all spot on. Let's keep going. So this is on to this is the sample one or something. Yeah, the sample. Yeah, sample one. So this is the last paper one that's been officially released. I have 2025 at the very end as well, but this is like the last paper one that's actually been released by Edexcel at this stage. So find d by dx. 4 times 3 is a 12. 4 take 1 is a 3. 8 times 3 is a 24. 3 take 1 is a 2. 3 goes away. Do it again. 3 times 12 is 36. 3 take 1 is 2. 24 times 2 is 48. 2 take 1 is 1. Verify has a stationary point when x is 2. So what we need to do is take our dy dx, the first thing we found, sub in a value of 2. So 2 cubed is 8. 8 times 12 is 96. 2 squared is 4. 4 times 24 is 96. So we get a big fat 0. Term of the nature, let's take our dy dx, but the second one, plug in the value of 2. What do we get? 2 squared is 4 times 36 is a number in my head, 144. Take away 2 times 48, which is 96. I don't know what that is, but it's positive. So therefore, we have a minimum. Minimums. Lovely. Yeah, all the other way around in it. This is big, this is small. Because we're going up, then down. So that's a maximum. That's a maximum, not what we need. We need a minimum. We're going down, then up. So what's happening to our gradient? It was negative, then it's 0, then it's positive. So the gradient is increasing. That looks good. Let's keep going. Give the a as a positive constant. Show that a equals log k, where k is a constant to be found. Okie dokie. So doing this, let's actually just look inside. Let's just divide them all. We've got, again, like last time, 1 plus 1 over t dt from a to 2a. So doing that integral, 1 becomes t, 1 over t becomes log t. We've got 2a and then a. Plugging them in, 2a minus a. And then we're also going to have log of 2a minus log of a. So that's an a plus log 2. And what we know, a is log k. So we can think about the fact that this is actually log k plus log 2. So that's the same as log 2k. And that must be equal to log 7. So k is 7 on 2. Does that look good? Does it look good? Let's find out. What number question is this? 4. Okay, 7 over 2. Lovely jubbly. Put a circle, put a tick, and let's move on. First principles. What we're doing of sine to cos. Okay. So what do we need to do? Let's do f. Well, first of all, f of x. We're going to call that sine of theta. So therefore, well, therefore, I suppose that's the last thing. That implies f dash of x is equal to the limit as h tends to 0 of f of x plus h. Let's do theta, I suppose, isn't it? F of theta plus h. So sine theta plus h. Take away f of theta, sine theta, all over the h. And now then, what do we want to do? We want to expand that sine theta plus h. We want to use the double angle formula, or the compound angle formula, to get that it is going to be sine theta cos h plus cos theta sine h, still with that minus sine theta on the top, all over these h's. And again, still with the limit stuff. So limit h tends to 0. And now what we're going to do is take those bits that we've got on the numerator and basically factorize them in terms of sine theta and cos theta. So if we look at the bits with sine theta on, so sine theta, what bits are left over? Well, we've got cos h and minus 1. So cos h minus 1. And I will put the h's on the bottom for both of these now. Lots of sine theta. And then for the cos, very similar. Sine h on h. Lots of cos theta. And notice the bits that we've just found in those brackets are the same bits. So what we can say, this thing is that thing, it goes to 1. This thing is that thing, it goes. So this one goes to 0, this one goes to 1. So when we actually go and perform the limit now, you can't really sub it in, but it's the same idea. We know that this first one is going to be 0. So it's 0 times sine theta plus 1 times cos theta. And that therefore is cos theta. Exactly what we were looking for. Lovely jubbly. Let's keep going. Number 13. Parametric equations. Find dy dx. So dy dx, that's the same as having dy dt on dx dt. dy dt, what do we get? We've got a cos 2t, so bring that 2 out. 2 root 3. Cos goes to minus sign, so we need a minus, we need the sign, and the bit inside stays the same. On the bottom then, 2 cos is 2 of minus sign. That looks good to me. Is that all we need to do? I feel that should be more than that. So 2 marks, I suppose. Is that correct? I can cancel our 2's off, I suppose, and the negatives, yeah. So that's good. What do we have is, I know what I'm going to do. Root 3 sine 2t on sine t. And sine 2t you can expand out. It's 2 cos sine. So this is the same as 2 root 3 cos t. That's good. The point P lies on C, where t is equal to 2 pi 3. Line L is a normal to that. So that the equation for that is this. So let's sub in t as 2 pi 3. So dy dx t is 2 pi 3. So cos of 2 pi 3, I don't think what that is. Cos of 120, is it? Cos 2 pi 3. Yeah, we got minus a half. Times by 2 is minus 1. Times root 3 is minus root 3. So that's the gradient at the point. We want the normal. So the gradient of the normal is going to be the negative reciprocal of that. So negative, sorry, not negative, 1 on root 3 or root 3 on 3. Either way you want to think about it. Do we know the y values and the x values? Nope. We've got to sub those in as well. What we found, this was minus 1, so that's actually minus, so it's minus a half, that's minus 1. Because of 2t, so let's have a look at doing 4 instead of 2. I get minus a half. That's the same, yeah. Yep, exactly the same. So minus a half times by root 3, so minus root 3 on 2. That is our coordinate. Take that with us. So now then, y minus that coordinate of root 3 on 2 is equal to m, i.e. root 3 on 3. Lots of x minus 1, x minus minus 1, so x plus 1. Need to do some expansions and stuff. So let's actually really enough divide by a root 3, not times by it, and we'll times by something else as well. So we'll divide by the root 3 to start with. So y over root 3 minus a half is equal to a third, well, x on 3 plus a third. And what we're going to do now is times by, well, this thing, let's just make it into a, like, rationalize the denominator. Times on bottom by root 3. I'll have root 3y over the 3 minus of 1 half is equal to x on 3 plus 1 on 3. And now then we just want to get rid of all those fractions. So it's times by 6. So 2 root 3y minus 3 is equal to 2x plus 2. And let's bring it all to one side. Yeah, bring it all to one side, but to the right hand side. 2x minus 2 root 3y plus that 3 over is a plus of 5. No, so everything right? This is right, this is right. 5, it should be minus 1, so I'm guessing that should have been a positive 3 somehow. So that's a 3. Didn't change sign all the way through. That was a negative. Y minus stuff in it. Make that negative a bit more obvious. So yeah, should have just been bop, 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 bop. And then that becomes 2. Take away 3, minus 1. All looks good to me. The line intersects the curve again at the point Q. Find that point. That's not, yeah, not differentiation or calculus or anything. So we're not going for that one. We'll do number 14. Not trapezium rule. More accurate estimate of trapezium rule. Just do more trapeziums. More trapeziums, the more accurate it becomes. Show the exact area. Okay. So 1 and 3 is what we've got. We've got this thing. That is a product. So we need to go and do the by parts formula. So the integral of u v dash gives us uv minus the integral of u dash v. What is u? It is going to be x squared. Yeah. U dash is 2x. V dash, no, that's what I knew my brain was telling me to stop then. So we can't differentiate log, can we? So log x, differentiate that, 1 on x. V dash can be x squared, and then v is going to be x cubed. Well, if we made that on 3, then we include the 3. That can be on 9. So that's that bit. That's good. When we go to integrate this, yeah, we can do that. So r then is going to be equal to, what's the integral of y from 1 to 3? So it's going to be this stuff. So u times v. So x cubed on 9 log x. I'll do these bits as well. So x squared and 5x. So minus x squared plus 5x. And they have the limits of 1 and 3. And then we need to also take away like the u dash v bit. So this times this, x squared on 9. Integrating that, x cubed on 27. So let's take that as well. X cubed on 27. So what we'll do now, plug in all these numbers. We've got a 3. When we cube that, what do we get? 27 on 9 is going to be 3 log 3 minus 9 plus 15 minus 1. That's for the 3's. When we do the 1's, log of 1, 0, goes away. We've got minus 1 plus 5 minus 1/27. So 4 minus a 27th. And they're subtracted from each other. So 3 log 3 is just going to be as it is. Didn't want it to like log 27 or something. Yeah, log 27 is what it wants. So log of 27. And then all these numbers there. And on the top, 15 minus 1 is 14, minus a 9 is 5, minus a 4 is 1. 1 minus 1/27. 1 plus 1/27 is 28/27. Does that all look right? Number 14. 28/27 plus log 27. Yep, looks good to me. Any more? Any more? Yeah, is this the last one? Yeah, so this is the last one of paper 1's, and then this is paper 2. I'm pretty sure. I will just double check that's correct. I think the next one is then, yeah, 2018 paper 2. Yeah, so this is where paper 2 starts. So I'll do this last one, and then I'm going to stop, go have dinner and stuff. Whether I do any more tonight, I don't know. I'll have a look. So that's all good. Should a sketch of this curve. So the x-coordinate of points P and Q are assumed to this equation. Okay. Well, P and Q are the turning points, yeah. It says it in here. So we want to differentiate, set that equal to 0. So what do we have? We have a quotient. So we need to do the quotient rule. U on V is going to go to UV minus UV dashes on the outside, V squared on the bottom. What is our U? The thing on top. So it's 4 sine 2x. U dash then, 4 times 2 is 8. When we differentiate sine, we get cos. The stuff inside does not change. V, what's that going to be? It's E. That's just sort of root 2. It's not like the x. Nothing else is done like that. So the V dash, what's going to happen is we're just going to get root 2 times V. So root 2V. Let's stick this all together then. V dash should be U dash. So 8 cos 2x times by V. And then take away the U. Take away U. Yeah, 4 sine 2x times by V dash. So I times by root 2V. This is all over V squared. So we can cancel off our V's. V, V, and the square go. What have we got left? On the top, 8 cos 2x. Take away 4 root 2 sine 2x. All over V, which was e to the root 2 x minus 1. We want this to be turning points. So what we need is for this to equal 0. So when a fraction equals 0, you can just say the top is equal to 0. So 8 cos 2x is equal to 4 root 2 sine 2x. We wanted tan, didn't we? Yeah, tan. Let's divide by cos. Let's divide by 4 root 2. We'll have tan of 2x on that side. The 8 and the 4 make a 2, don't they? 2 over root 2. That is the same as root 2. So tan 2x is equal to root 2. Looks good to me. Always nice when it matches what they what they wanted. Using your answer to part A, find the x-coordinate at the minute turning point of the curves. Okay, so they're doing transformations afterwards, but we still need to find the actual values. I mean, but this I suppose is actually now it's just trig, isn't it? You solve the trig equation, you do the transformations. So no more calculus. That's me done for the day. I will do the rest of these. I don't know how long I've been doing this for. We've done 42 though. We've done 42. I did delete one, so we've got 104. So we're nearly halfway. Nearly halfway. I'll finish it tomorrow and post it tomorrow. So lovely. I will do this more tomorrow. Thank you. Right, hello again, mother lovers. We're back to do some more. We've done so far 42, only 52 to go. So first principles, cos to minus sine. So as always, we want to define f of theta to be cos of theta. So when we go to do the derivative, we're going to take the limit as some h goes to 0, where we want cos of x plus h, or theta plus h. Take away cos of theta all over the h. So we'll use the combine angle formula, and we will expand our cos into cos theta cos h minus sine theta sine h. Also take away that cos theta all over h. So again, this is the same as it always is. As it always is for cos or sine doing the first principles, we look for the one with the correct variable, i.e. theta. I'm going to factorize those bits. So cos theta, cos theta. So how many cos thetas did we have there? On the first bit, I've got cos h. On the second bit, minus 1, but they're all over h. Same for sine now. Minus. We're going to have sine theta, lots of sine h over h. Again, the limit, as all of this stuff has h going to 0. So now what we have to do is use the given ones. So this entire bracket is this entire thing goes to 0. This one goes to 1. So this whole thing is going to equal 0 times cos. Take away sine to minus 1 times by sine. So all together, that is minus sine theta. Lovely jubbly, looks good to me. Number 10, always got the mint in the mouth. Spherical mint of radius 5 is placed in the mouth and sucked. 4 minutes later, the radius of the mint is 3. So what does that tell us? First of all, we have that t and r, so time and radius, we have 2 different points. Starts at 0, starts at 5 mil. Later on, it gets to 4 minutes and it's 3 mil in size. So there are points that we have. In a simple model, the rate of decrease of the radius is inversely proportional to the square of the radius. So rate of change of the radius is going to be inversely proportional to the square of the radius. Lovely. So we have this, we have these two. Let's go and do some maths. So first things first, differential equation. Bring all the r's to the left. So we have r squared dr. And then bring all the t's to the right. So we have k dt. Integrating both of these sides. What do we get? Well, we'll raise that power to a 3. We'll divide by a 3. And we'll set that equal to k times t. And again, I'm going to do c over 3 for this one. C over 3. And actually, what I will do is do like k over 3, do you know what I mean? So k can always just be some constant. Doesn't matter what it is. If it's k or a third of k, it's still a constant, isn't it? So if we just make all of these be 3's, goodbye all the 3's, which is much nicer to deal with. So now what do we have? R cubed is kt plus c. So let's take our values, plug them all in. What are we going to get if we do the 0 and the 5? That tells us that 5 cubed is equal to c. If we do the 4 and 3, what does that tell us? Well, we have 3 cubed is equal to 4k plus 5 cubed. So we know that k is going to be the difference between those. So 3 cubed minus 5 cubed all over 4. That's good. What do they want? Find an equation. Yeah, lovely. So we'll just write that in one go. R cubed is going to be equal to k. So 3 cubed. Let's just work out what that is. So there's numbers, aren't they? 3 cubed, 27. Take away 5 cubed. Gives us minus 98 divided by 4 minus 49 on 2. So minus 49 on 2 lots of t plus 5 cubed. So plus 125. That is our equation. To find the values we use, so r is radius, t is time in mins, and I suppose radius is time in millimeters. Hence, on the total time taken for the mint to completely dissolve. So if we set r to be 0, what we're going to get, kt plus c is equal to 0. So t is going to equal to minus c on k. So doing that, what was c? 125. What was k? Minus 49 on 2. So the negatives cancel out there. 49 on 2 on the bottom. We have 250 on 49. That's just over 5 seconds, yeah. Yeah, just over 5 seconds. That looks good. It's just a limitation of the model. Well, what we said, this on the right side where we had it, this is a straight line, yeah? We got k to be a negative number. This was the negative 49 on 2. So it's a straight line with a negative gradient. Eventually, this is going to go negative, yeah? We can't have the negative radius. No chance at the mint can never have a negative radius at all, or negative volume, anything like that. So, limitation of the model, it allows r to be negative, which is not allowed. Next one then. Partial fractions. Let's have a go at doing this sort of stuff. So the partial fractions, I'm not going to do that bit. I'll just do the different, the calculus part of it. Hopefully that bit should all be okay. I'll tell a lie. We need. No, yeah, we don't need to do it. It proves it's a decreasing function. Yeah, I think they've been a little bit sneaky because they make you do that bit, and normally then you'd integrate in it once you've done that, but you don't need to do that. You need to differentiate. So doing this, what's going to happen? Well, we've got a quotient. So I'm going to actually expand the bottom quickly. I'm going to have negative 2x squared. I'm going to have, if we do 1x and a 6x gives me a 7x and minus 3. That looks good. So we have a quotient. We have a fraction there. We need to do the quotient rule. So we're going to have uv minus uv dashes on the outside, v squared on the bottom. What is our u? It's the thing on the top. 1 plus 11x minus 6x squared. And so for u dash, 11x becomes just 11. That 2 comes down, times it by the 6. For the v, we have that thing we just found, minus 2x squared, plus 7x minus 3. That's v, sorry, not v dash. So v, the 4 will come down, minus 4x, plus 7. So f dash of x, what are we going to have? U dash, 11 minus 12x. V. So we're going to have, that's v dash, minus 2x squared plus 7x minus 3. And then we need to have u. So that's going to be, take away u. 1 plus 11x minus 6x squared. I'm wondering if there's a way that like this might have been easier to differentiate, do you mean? And then like you end up with a very simpler function to deal with, but we'll still go and see what pops out. So that bit we've done the u, we need the v dash, so we're going to have the 7 minus 4x, yeah, 7 minus 4x, all over v squared. Yeah, all over v squared. So we want to show that this is decreasing. So this needs to be negative all the time. So the bottom is always squared, thus always positive, or 0, but always positive effectively. So we only need to consider the top. So let's expand that top out. What are we going to get as we start doing that? So f dash of x equals 0. Oh, ignore me. Yeah, f dash of x is going to be, well, expanding this out is not going to be so easy to do. What have we got? There's going to be our cube. So we've got 24 of those. Where are the squares coming from? Minus 11. And then minus 7 times 12. 7 times 12 is that, plus 11. 95. So negative 95 x squared. Let's double check that because that's actually going to be 12, isn't it? Not 12, 22. What I might do is just this this expansion is going to take me ages. I'm going to whack that on a calculator, make sure I get all the expansion correct, and then we'll deal with it from there. So let's do that quick. If you're ever doing that, Wolfram Alpha is probably the best one to use. I think it's always the best one to use anyway. So what have we got? 11 minus 12x, and then minus 2x squared plus 7x minus 3 minus 1 plus 11x minus 6x squared times by 7 minus 4x. As we do that, we get one big thing coming out. That is actually quite nice as we collect it all down. So we have minus 20x squared plus 40x minus 40. Still all over the v squared. We can take out a 20, yeah? So we have 20 over v squared there. What have we got left? We took a negative out as well, why not? So x squared minus 2x plus 2. This, let's look inside here. Let's complete the square on it. What are we going to get? That minus 20 on v squared stays out the front. And I have x minus 1 all squared. Take away 1 squared. That's plus 1. So what we have, that's something squared. So that's bigger than 0. Add 1 to it. That's still going to be bigger than 1 now, isn't it? Yeah. So we times it by this thing. It's always going to be bigger than or equal to that. But this is negative. So it flips it over. This whole thing is definitely less than or equal to 20 over v squared. That thing itself is always, it's less than or equal to negative that, which is always negative because v squared is always positive. So what we've shown is that the derivative is always negative, therefore the function is decreasing. Lovely jubbly, let's keep going. So we need to do some p. Figure 2 shows a sketch of this curve, x log x, L, the line L is a normal at the point P. The region R showed blah, blah, blah. Find the region R. Okay, so what have we got? X log x. First thing to do, we need to find this normal. So let's differentiate x log x. Differentiating x, we get a 1. So we're in there, times that by a log. Differentiate the log, we get 1 over x. Times by the x is going to give us a 1. So that's dy dx. That point is E. So if we evaluate this at E, what do we get? Well, log of E is just going to be 1, so it ends up giving us 2. So that tells us that the normal gradient is minus a half. So we've got y minus E is equal to minus a half x minus E. That is the equation of this line. Do we need it for anything? Really? No. Only that point. Where does that point happen? When y is 0. We never need to rearrange this to like make it work with mx plus c. We just need to plug in the fact that this thing is 0. And now let's solve this. Our negatives can go. I'm going to times by a 2. I've got 2e on this side, x minus e on that side, plus another e gives me x. So x here is 3e, and that's this point, 3e. So that's good. We can now split the region R into 2 little different sections by drawing a line there. Knowing the height of this is e, and the width of this is 2e. So this is e times 2e times a half. It is e squared for the area. I'm going to put that in a different colour. Let's make it blue. Lovely. Next bit then we want this little kind of, not triangle, but it's almost a triangle, isn't it? Want that little part. How do we get that? We need to integrate from whatever this hits the axis. When's that going to happen? When this equals 0. So either when x is 0 or log x is 0. When is log x 0? When it's 1. So this point is at 1. So we want to integrate from 1 to e of our curve. So x log x dx. How do we do that? It's a product, so by parts. We need the integral of u dash v to give us uv. Take away the integral of uv dash. Which one's which here then? So generally you'd have x as u, but we can't integrate the log. So that will have to be our u. So u dash is going to be 1 over x. V dash is x. So v is x squared over 2. Let's stick all this together. U times v, x squared on 2, log x. And let's stick in e and 1 to there. Take away the integral of x squared times on 2 divided by x. So a half of x. To do all that, what do we get? This stuff will stay the same for a second. Log x. Take away x squared on 4 now. And again with e and 1. Log of 1 just goes away. So that's nice. Anything I'll go away? Don't think so. Let's put in e then. What do we get? E squared on 2. Log of e is 1. Take away e squared on 4. This whole thing then take away. Plugging in 1 to there is just nothing. Plugging in 1 to there is a quarter. Well, negative quarter. So what do we have here? A half take a quarter is a quarter. So we've got e squared minus 1 on 4 from that, which I still will write as e squared on a quarter, or e squared on 4, minus 1 on 4. And if you remember, that was just this little left side. So we need to add on e squared to that. So therefore r is going to be 1 e squared plus a quarter of e squared is going to be 5e squared over 4, but with the minus 1. Minus 1 over 4. That looks good. Let me just double check I was actually correct in these other ones I was doing. And it looked quite nice, didn't it? What was this one? We got, oh, that's just to prove that one. Okay, yes, that's fine. Did I win anyone before that? Yeah, I didn't actually double check this one. Let us double check. Does that work still? Yeah, that's all good. It did want minutes and seconds, but yeah, you can do minutes and seconds, can't you? 11, yeah, that's good. 13, where are we? 5e squared on 4 should be plus a quarter. What did I do wrong? Negative. Pop. Yeah. If you know, like, part of doing revision and past papers is just figuring out where you make mistakes. So if I'm in an exam, I'm like double checking those bits, just because I know that I'd often just forget to do negatives. So making mistakes isn't a bad thing. Part of learning is just knowing where you make them, so you can double check in the exam. Look, this is all looking good. 10 marks for that. Not too. I think that's a go. That's not the worst in the world for 10 marks, I don't think. Let's keep going. Oh, we've got these mice doing things now. Yeah, mice on an island. They're going to keep doing things. Find the number of mice probably at the start of the study. So what we're going to do, t is going to be 0. So that's still 0. E to the 0 is 1. That's a 7. That's a 3. Add that to 10. 90 on, 900 on 10 is 90. So the rate of growth is given by that thing. So we need to differentiate this. We could do the quotient rule. We could do the chain rule. What's going to be nicer? Probably neither. But we'll do the chain rule. We've done a lot of quotient rules, so I'll do the chain rule instead. So I'm going to rewrite this. N is equal to 900 times by 3 plus 7 e to the minus t on 4 to the minus 1. So dn dt is going to have that 900 still, times by the derivative of the thing inside. 3 goes. Differentiating this, I'll have 7 over 4 e to the minus t on 4. But no, that will be negative coming out, but I'm going to get that negative as well. So it just stays like that. And then with this bracket to the minus 2. This is good. Let's just rewrite this a little bit neater. So 900 times 7 over 4, is that something nice? 1575. So let's not put it there. We'll have 1575 e to the minus t on 4. And notice that this thing, what is this thing? It's this bracket in there. So we could always rearrange. This bracket is like n over 900. Or I suppose the bracket is 900 over n. So doing that, this is going to be n squared on 900. And if you look what you want, like there is n squareds in there. Like that is n squared. So that's a good sign that you want that. The only thing I want to change now is getting rid of this. To do that, I'm going to start with the original. But you could start with that version. Start with the original though, and rearrange for e to the t minus 4. You don't need to rearrange for t. You just need to rearrange for something in there. I could rearrange for like 1575 e to the minus t, but not easy to find that in there. So let's do this. I'm going to swap that and that round. So my bracket is going to equal to 900 on n. So I can take a 3 and divide by a 7. So 900 take away, I know I'm going to take away a 3, but I'm going to make that 3n, yeah? Because it's the same as doing like take away 3 times the top and bottom by n, and then just combine them up. So that's like that. And on the bottom end, I will have 7n. And that is going to be e to the minus t on 4. So that's good. What we're going to do is then swap that. Do you want to put it in there for that instead? So let's do that. We have then the dn dt It's going to be, again, 1575. Instead of e to the minus t on 4, though, we have this bracket of 900 minus 3n over 7n times by another fraction, n squared or 9. My n on the bottom goes with my square on the right. And I'm going to start getting some factorization. So I timed something by 7 there, didn't I? So let's divide it by 7. Yeah, 225. So this and this makes me a 225. Divide that by a 9. I get 25. So yeah, these, and these are 25. 25, lots of 900 minus 3n, lots of n. And now then, how close are we? We're very close, aren't we? Should be a bigger number on the bottom though. We'll figure that out in a second. Let's take a 3 out of there. So we've got 75, lots of 300 minus n times by n. So everything looks good here, doesn't it? But this shouldn't be 75. It should be 1 on 1,200. So we're a long way off. Let's see what happened. Because it's just going to be a constant, and everything else is worked out right. Some constant somewhere is wrong. So 75, that comes from that, and that. So it should be 1 on 1,200. So I feel like this number, for some reason, should be on the bottom. So where did it come from? It came from here. Where did that come from? That came from this number times by 7. No, 7 over 4 in it. Yes, that is just that number. Should that be how that pops out? Yeah, should have brought a negative, but it brought that negative. So that does seem correct, but obviously it's way off. Way off. Let's see what the mark scheme's saying, if I can figure it out any easier. So it's just a scale factor off, isn't it? Like, what's going to go on here? Nowhere has my number appeared on the mark scheme. So let's just track through again. This is just a rearrangement. Did we do that right? 900, this entire bracket, 3 plus 7e to the minus 2 and 4 to the minus 1. That's good. Differentiating. We keep the 900. What's going to come out of here? 3 goes away. 7 comes. Minus 1 and 4 comes. This entire thing comes. This entire bracket comes, but it loses a power. This should have had a negative come, but it had this negative, so that cancelled it. So that looks good. That row, I think, is fine. And now we've got this. So maybe it's doing that was wrong. And this should be much bigger, because that's only 225. This looks good, and so this part seems correct. Everything I've done here is good. That comes from there, that comes from there. So I think this whole chain of stuff is like okay. So I think it's just going to be like somehow this bit is wrong, what I've done there. So let's go back through from maybe that point. This bracket is the same. Like we had just a bracket to minus 1. It's going to be n over 900. Yeah, so if we have that bracket squared, brought that to the minus 2, it's going to be n squared over 900 squared. So yeah, something just went wrong with that a little bit. So this bracket, yeah, n over 900 squared. What did I do before? Let's go back and see what it said. Did I just miss off a square or something? I just put 9. 9, not 900 squared. That's very different than 900 squared. So does that change everything? Let's track for a 900 squared on the bottom now. Well, we used a 9, so I will leave 1 9 where it was. And then times by 900 times by 100. That's still 900 squared, yeah. I've just left that 9 as it is. So we've got basically a 90,000 to divide by. So if I do 75 divided by 90,000, I get 1 on 1,200. Yes, that's good. So yeah, they should have just had a 90,000 flying around everywhere. So we'll just get rid of that one and whack it over 1,200. So there you go. That's how you need to do it if everything's right, but there's the scale factor's wrong. So just somewhere, some number's wrong. And you think like, where did this bit come from? This bit came from like this logic, and it's correct. So that's all good. We need an n, so that's good. It's just like a number. Where do the numbers come from? And like this, we needed something else big on the bottom. So this one being too big on the top, maybe that's too big, or maybe this is too small. That looks good. I think that should be worth more than 4 marks. It's very fiddly to do, isn't it? Very fiddly. I know I made a mistake, but even so, like doing the rearrangement is not so nice for 4 marks. The rate of growth is a maximum after t months. Find equal to the model the value of t. So it's going to be a maximum. So the rate of growth is a maximum. So this thing is a maximum. Like you'll find the maximum of the rate of growth. You're not finding the maximum of n. Find the maximum of the growth, so like the acceleration, basically. But this is a quadratic, yeah. So when is that going to be at its maximum? Well, it's symmetrical, so it's going to be the average of its roots. Where are its roots? 0 and 300. So we know that we're going to have this maximum happens at n equals to 150. So let's just take our original over here and make that equal to 150 over 3 plus 7 e to the minus t on 4. So as we do that, divided by the 900, that will be 1/6. Then I'll flip it over. So the thing on the bottom, 3 plus 7 e to the minus t on 4 equals 6. So e to the minus t on 4, if we take away the 3, we'll have 2. Divide by 7, 2 over 7. The negative, we can flip everything. T on 4, 7 over 2. And then log and times by 4. So t is 4 log 7 over 2. Is that correct? That looks correct to me. 4 log 7 over 2. 5.01. No, what's gone wrong there? They get minus 4 log of 3 over 7. Okay, well, so this is the same as 4 log 7 over 3. So I've got a 2, and I shouldn't have a 2, I should have a 3. So where did that 2 come from? There. It's that 2. That came from doing 6 divided by 3. So should that not be 6? Maybe this shouldn't be 150. Am I being really silly there? No, n equals 150. Yeah, 150 equals that. This is all good. E equals 3/7. That's a 6th. Oh, 6 take 3 is 3, isn't it? I'm not divided. So see, it's very easy to do those mistakes. Obviously hard to spot in the exam, but very, very easy to do. So yeah, that's all correct apart from that little bit. Nice. That's good. According to the model, maximum number of mice on the island is p. State the value of p. So what we can think about, this is the maximum growth rate. When is the maximum though of like the actual change? I mean, so when this would be equal to 0 is the maximum number of mice. When's it equal to 0? At 300. So p should be 300. Is that good? Yeah, nice. So it's either one of 299 or 300. Apparently it won't reach 299 or won't reach 300. So that looks good to me. What's going on here? Okay. We've got this sort of stuff and it defines it like this. So you've got sketch of curve, y equals root x. Calculate this thing. Okay. So this is just a fancy way of writing limits. It's like the definition of a limit. Of an integral even, sorry. So what we've got, 9 and 4. 9 and 4. Root x is x to the half. Doing that, the half goes up to a 3 over 2. We divide by a 3 over 2. We have a 9 and a 4. They've chosen square numbers for a reason. 2/3 can come out the front. 9 square root 3 cubed, 27. 4 square root 2 cubed is 8. So this is 19 times 2, 38 on 3. Is that looking good? What number is this? Number 5. So on to the next paper. June 19th, paper 2, question number 5. 38 on 3, 38 on 3. Lovely jubbly. Right, sorry about that, just popped to the toilet quickly. Let's have a look at this one. So we've got a storage tank, one in the shape of a hollow circular cylinder, closed at one end, with a hemispherical shell at the other end, as shown in figure 9. They've got no thickness, radius r, height h, hemispheres, radius r meters, volume is 6. Okay, so we want to find the surface area, and we know the volume. So this is not connected rates of change, it's just like connected something, I don't know what they'd call it. How do we work out the volume of this thing? Well, we've got one cylinder, so that we need to do the cross-sectional area, pi r squared, times by the height, h. Add on that hemisphere. You can see we have like the volume of a sphere is that, so we need just half that, i.e. 2 on 3, pi r h and pi r h pi r cubed. And what we know is that that should be equal to 6. So we're able to factorize this for h basically, or like rearrange for h, and then use that for a value on the other side. So doing that, let's take everything over to the side. So we're going to have pi r squared h is equal to 6 minus 213 pi r cubed. Divided by pi r h, we'll have, sorry, pi r squared, we'll have 6 over pi r squared. Take away, well the pi's go, don't they? This is squared and a cubed, so we'll have just 1 r left over. So minus 2/3 of r. That's all good. So we want the surface area as well. How do we work that out? We need to think about the fact that we have a circle on the bottom. So the surface area will be given by pi r squared for the bottom bit. Adding on the area of like the curvy bit on the outside, you mean? So it's h long. It's like a rectangle. It's going to be that long as well. So how long is this? This is going to be pi times diameter, or 2 pi r times by the h. And then we need to add on the surface area of a sphere, of a hemisphere. So normal one is going to be 4 pi r squared. So we want half of that, 2 pi r squared. That all looks good to me. We can collect some like terms there. We've got some pi r squareds. So we now have 3 of them. 2 pi r h. And now then, we want to take our expression for h and we want to sub it in there. So as we do that, 3 pi r squared, that's good. 2 pi r h, that's good. 6 over pi r squared. Take away 2/3 of r. Expand all these brackets out. We still have the 3 pi r squared at the front. 2 times 6 is a 12. Pi on pi is 1. R on r squared is 1 on r. 2 times 2 is 4. Over the 3 still as a pi, and we've got an r squared. And now let's collect. We've got 3 there, minus 4 over 3. This is 9/3, that's 4/3. So we have 5/3 pi r squared plus 12 over r. Is that what they want? Lovely. Lovely jubbly. What else do they want from us? Surface. The manufacturer needs to minimize the surface area of the tank. Use calculus to find the radius of the tank for which the surface area is a minimum. So let's take this surface area we just had and let's find the derivative with respect to r. So r is going to bring a 2 down to the front. We'll have 10/3 of pi times r. This is the same as like 12r to the minus 1. So it's going to be negative 12r to the minus 2. We want to set that equal to 0. Let's cube, well, not cube, let's times all sides by r squared. And then also add the negative to the other side. So it's going to be 10 over 3 pi r cubed is equal to 12. So times by the 3, divided by the 10 and the pi, I get r cubed would be equal to 36 on 10 with a pi on the bottom, and that whole thing is going to be cube rooted, yeah? We could have this a little bit simpler, 18 on 5 pi, yeah? To the power of 1/3, whatever number that's going to be. That's nice. Calculate the minimum surface area of the tank. Give your answer to the nearest integer. So we're going to take this value of r, sub it back into this thing. So what I suggest to do is just really to, first of all, write it out, which it means, so like S min, it's going to be 5/3 of pi, and then that thing squared, so 18 on 5 pi, to the 2 on 3, plus 12, lots of 18 on 5 pi, to the minus 2 on 3, to the minus 1, to the minus 1 on 3. That's good, but when we're actually using the calculator, what I'm doing is I'm getting the value of r and like saving it in the answer. So if we do 18 on 5 pi, cube root that bad boy, and now that's saved in the answer. So we don't need to type in all this faff, do you know what I mean? Like, all trying to put all this in. We can just go up and use like this one, but wherever r is, we want a whack answer. So I want 5 over 3 times by a pi times by my answer squared, plus 12 over my old answer. What do I get? 17.2-ish. Nearest integer, 17. Is that what they want? It is. Lovely jubbly. The other one was, yeah, the cube root of 18 over 5 pi. So that all looks good to me. Everything seems spot on. Let's do one or two more before we call it a day. Use the substitution to call it, to figure this stuff out. Oh, it's just the exact thing, is it? Okay. So let's find du, dh. 4 goes away. This is actually like minus h to the half. So differentiating that, we'll have minus a half out the front, h to the minus a half. So we know the dh then. We can think about, we actually want to get this in terms of u, don't we? So maybe it would have been better to do this slightly differently. Yeah, I think it will. So what we're going to do actually is take our original thing and rearrange a h. So we'll have add that over. H is going to be 4 minus u, and then we need to square that. That looks good. So differentiating this, what do we get? dh du is 2 lots of that thing, but negative 2 lots of that thing, with the minus sort of coming out from the u. So 4 minus u. That's good. So dh is minus 2 lots of 4 minus u du. Lovely. The bottom is obviously just u as well. So sticking that all together, what we have is our integral is, well, the dh is gone. We've got a minus 2, 4 minus u du over 4 minus h, which was u. This negative, I'm going to flip that round with it. So we're going to have like 2u minus 8 over u du. Let's divide some bits off. What have I got? 2 minus 8 over u du. My 2 becomes a 2u. My 8 becomes an 8 log u. And now I need to remember what u was. It's 4 minus root h. So it's 2 lots of 4 minus root h minus 8 log 4 minus root h. Have they got modulus in there? They have. So they've done it that way around. So let's do the same thing here. That's going to be the modulus. We've got some constant. And you'll notice above, when you see the answer in a second, they will not have the 8 that we've got at the front there. Why not? Well, we've got some constant and some 8. Combine them together, what do you have? You still have a constant. So it's one of these weird rules about like constants. You can just, it doesn't really matter what happens to it. You can just keep calling it constant and it's fine. Oh yeah, they made modulus, didn't they? So we'll follow what they're doing. Mod 4 minus root h. You don't really see it in A levels often. You hardly ever really have to encounter it. But yeah, that all looks good to me. That matches. That's got an 8. The k there is just our new c. That's fine. We will call it k. They just do match what they've got. So that's good. What are they on about now? Team of scientists studying a species of slow growing tree. Rate change in height species. Blah 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 blah. The range of heights in this tree species. So let's think about actually what's happening with the height. If we set height to be 16, this would be 0. If height is anything less than 60, say it's 9, this is going to be 1. So this thing will be, this thing will be 1. So it's always going to be positive, basically. Like t is positive. I think it told us t was positive somewhere. T pretty much always is. Yeah, it's time after the tree's planted. So that's positive. This thing's always positive. This is always positive. So dht is always positive until h is 16, and then it's 0, and then it's negative. But it's the idea, like, you can never grow past 16 then, at any point. Can we be 0? Yeah, nothing seems to break it from 0. So I've got the range of heights should be from 0 to 16. But I'm wondering if we're going to have some weird case where we don't end up with the lower end. So I know h is definitely at the most 16. Do we need to do, what's 1 meter to when it's first planted? The range of heights, I'm guessing it can just be anything less than 0 and big, less than 16 and bigger than 0. 1 meter when it first planted. I'm wondering, like, if it's just going to be like, how tall are they planting them, do you mean? It doesn't, nothing from there breaks, do you mean? We can have 0. You could have a 0 height and it would be fine. Everything would work out still. It would grow quite quickly, but yeah, everything would be fine. Let's double check that is correct. What number are we on? 14. They allow. Oh, okay. So you can have any like 0 to 16, or just under 16, and you can have any including or not including on both as well. Okay, so that's all good. One of these trees is 1 meter high when it's planted. Okay, the time it takes to reach 12 meters. Do we have any unknowns? The only unknowns we really have. No unknowns in that bit, so that's good. So let's do this. We have a differential equation, so we need to separate our variables. Let's think about bringing our h's to the left. So we're going to have the integral of dh on 4 minus root h is equal to the integral of t to the quarter on 20, but that on 20 I'm actually going to shove over there for a bit. As you know, I'll just work it out front. That looks good though. The left hand side is what we did up here. So we want to just copy really what we had. Stick that over there. This thing, we integrate it. The power of t is going to go up by 1, so it's going to be t to the 5 on 4, but then we'll times by 4/5. Still got that 20 at the front as well. Notice we don't need to worry about the plus c, because it's already in there. It's already there. So this is good. Modulus as well. The height is always going to be less than 4. Yeah, that's always true. So the modulus is like by definition, we don't need to worry about it because we don't see it be negative. So that's good. It's planted when it's 1 meter high. So when t is 0, that whole side is 0. We'll quickly figure this out though. That's 125. Yeah, 125. Yeah, but still, the whole side there is 0. So we need to set this to 0 and solve for h. No, solve for k, sorry, when h is 1. So doing that, yeah, 0, 1. What that does that tell us? That k minus 2 minus 8 log 3 is equal to 0. So k is equal to 2 plus 8 log 3. That's nice. When does it reach a height of 12? So what we need to do, plug in 12 onto there. So 2 plus 8 log 3 for our k, plus 2 root 12 minus 8 log of 4 minus root 12. We need to times that whole thing by the 25, and then do the power of 4 over 5. Let's whack that in the calculator, see what we get. So 25, open brackets, 2 plus 8 log 3 plus 2 root 12 minus 8 log of 4 minus root 12. Close the brackets for the log, close the brackets for the whole thing, powers of 4/5. I get a number out. 304. 304. What's this measuring? Years. Does that seem too many? 12 meters is quite tall, but 304 years is very old. Very old indeed. Can't see anything wrong immediately. Let's check the answers. 14 this was. No, it's not quite right. Are we exactly? No. I thought if we're exactly to scale factor off, but we were not. Let me just double check that. No, we weren't. So let's have a look and see if we can find something that's wrong. So this is incorrect. Did we copy everything down correctly? Where we write here as well, is our k actually? Did we get k correct? Yeah, that's one thing to think of. C is, yeah, it's minus 8 log 2, yeah, and 2. Okay, that's good. So that is correct. K is correct. Did I type everything in the calculator correctly? That's one thing to check, isn't it? 8 log 3, yep. 2 plus 2 root 12, yep. Minus 8. Let's have a little double check. Just going to rearrange this a little bit slower. So what should we have? I'm going to take all of these things, and we want to plug in t 12. So k we know, and that was correct. 2 plus 8 log 3. Take away 2 root 12. Take away 8 log of 4 minus root 12 is equal to 1 on 25 t to the 5 on 4. So let's maybe just work out what this left-hand side is. 2 plus 8 log 3 minus 2 root 12 minus 8 log 4 minus root 12. What do we get for that? 8.85. 1 on 25, t to the 5 on 4. Times that by 25. And then do the power of 5 on 4. Nah, it's doing the same thing in here. So something is wrong. What thing is wrong? I've got the exact same equation that they have. So yeah, the left-hand side is just that thing. This is 1 over 25 t to the 5 over 4. So the equation is correct. I'm not sure. This what I've got written down is matching the mark scheme exactly. They get the same number. Oh, I think all I've done is I've done 5 over 4, not 4 over 5 at the end. So I do apologise if we do this correct, like it's the right number. If I didn't ask the power of 4 over 5, I get, yeah. So t is 75. So I think I've done everything correctly. I just did the wrong power at the end. Sorry about that. So very easy on calculator stuff. Too much to get the wrong stuff. This is looking good. And that is the correct number for 75. Lovely jubbly. So differentiation by first principles. F of x then is going to be equal to 2x squared. So f dash of x is the limit as h tends to 0. That's not very good h, is it? Try again. As h tends to 0 of f of x plus h. So 2 lots of x plus h squared. Take away just f of x all over h. So thinking about this, limit as h goes to 0, expanding those brackets. I am going to steal just a 2. It's going to steal a 2 from everywhere. So put that 2 right at the front. It's nothing to do with h, so it can just live out the front. Expand that bracket, x squared plus 2xh plus h squared minus x squared all over h. X squared there can go away. Let's keep going. What we've got left in here, they're all multiples of h, so we can divide it off. We've still got our 2 at the front. Still need to take our limit. Inside them, we've got 2x plus h. As we plug h into that, because now it doesn't cause a calculator error or something that's undefined, basically, we have the 2 at the front times by a 2x in the middle plus 0. So that is 4x altogether, which is the derivative of 2x squared. That looks good to me. Let's keep going. So what have we got? We want to find the exponent of p over there. We've got this thing, lovely. So what's going on? F dash of x, we've got 8 sine of the half, so that half comes out to make a 4 with the 8. Sine changes to cos, and a half x stays as half of an x. Minus 3x becomes minus 3. 9 disappears. Set that equal to 0. Cos of x on 2 is equal to 3 on 4. So we know that the x over 2 is going to be inverse cos of 3 on 4. But noticing that we want p. So that's 1, 2, 3. The third positive value of x, well, of this thing. So let's think about cos itself. What does cos do? It starts here, does that stuff, and then does that. So if we draw a line around 3/4, we get 1 there, 1 there, but we want the third one. So we need to come back around this way. So whatever our calculator tells us this, just add 2 pi. So what does our calculator tell us? Inverse cos of 3 on 4. Doesn't tell us nice things. Tells us that it is 0.72. But then add 2 pi. So 2 pi plus 0.72. So what we have, x is going to be 4 pi plus, and this is like dot decimals and stuff, do you mean 7 dot dot dot. So if I just double all of that, what do we get? 1.45. So add that on to 2 pi. What do we get? 7.73. Yep, that looks good to me. Is that the correct one in the mark scheme? On 2022 now for paper 2. What question number is this? Number 6. I'm 2 off. Why am I 2 off? Do I need to double something somewhere else? Let me just put that in the calculator again. So 2 pi plus 0.7227 times 2. Yeah, I just didn't put that in the calculator correctly. If we do that, then x is the 14 that they want, 14.0. That's good. Part B then, go across the x-axis at alpha, blah, blah, blah. Oh, okay. Yeah, not calculus, this is it. So let's keep going. Let's find this one. Sketch with this stuff, blah, 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 blah. Find the shaded region. So when we have a quotient, we can do quotient rule. But when on the bottom, it's not a linear thing. It's just a single term. Do you know what I mean? It's just a single term. There's no additions or subtractions. And these are all just powers of x. You can just go and expand the top and then divide things off and do it like you would do in the first month, first year. So what's the top give us? X squared minus 2 minus 4 is minus 6 plus 8 all over 4x to the half. So what do we have is 1/4 x to the 3 over 2 minus 3 over 2 x to the half plus 2x to the minus half. So differentiating all that, 3 over 2 will come down alongside our 1 and 4. Tell a lie, what am I doing? We don't want to differentiate, do we? We want to integrate that. So where do we need to integrate this between? Well, the top, when this equals 0, the top equals 0. So it's 2 and 4. Hence why they've given it that way round. They'd rather you expand it out. It's much nicer to do that than try and factorize it down. So that's lovely. Let's think about actually integrating this now. So we're integrating this thing, aren't we? So let's actually just copy that over. Get rid of the equals. Whack a dx on the end. Call that r. Lovely jubbly. So what are we going to need to do? Raise this power. X to the 5 over 2. We'll times by 2 over 5. We'll keep our quarter. Take away, raise the power, 3 over 2. We're going to divide by 3 over 2. So, yeah, that's good. Here, raise the power, x to the half. Divide by half is like times by 2. So 4. And this we want to plug in 4 and 2. So, before we do that though, I'm going to first of all, let's make this nicer. So it's 1/4 or 2/5. That's 20 on the bottom, 2 on top, so 1/10 altogether. But then as well, we've got a square root everywhere. So what I'm going to do is going to take 1/10 of root x. Not out like the limit bracket, but just outside in here. So what is this? This is going to be x squared, 10x. And that we need to make 4, so we need to have 40. We could factorize that maybe, but I don't know whether it's worth it. I don't know if we can anyway, even if we can, but yeah, we don't need to. So let's plug in our limits. Root 4 is going to be 2 over 10 is a fifth, times by 16 minus 40 plus 40. So we know that both of those are just gone straight away. And then let's plug in a 2, so root 2 on 10. 2 squared is 4 minus 20 plus 40. So altogether, 16 on 5. And then we've got here, this makes 20 plus a 4, 24, minus 24 on 10, minus 12 root 2 on 5. So we could take a 4/5 out and have 4 minus 3 root 2. Does that look good? Well, they want it in that form. It's basically the same, isn't it? Yeah. What number are we on now? Number 8. 16 on 5 minus 12 on 5 root 2. Wonderful. Always nice, isn't it? Big ticks. Let's keep going. How many have we done now? 9:30. That's another 10, isn't it? Yeah, I'll stop here, I think. I'll do some more in the morning. So thank you very much, guys. I will see you in, for you, 2 seconds, for me, a couple hours. Right, Booty, thank you. Right, good morning, guys. All right, afternoon, I'm back again. Let's see how many we did yesterday. 53. I think there was one page I deleted last night where it was just like a blank page and there's nothing on it. And we've got 103 in total, so 50 to go. So let's get going. We've got f of x is a nice quotient. We want to find f dash of x and show it's equal to this thing. So let's think we need the quotient rule. So it's going to be uv minus uv, dash is on the outside, all over v squared. So what is our u? Our u is e to the 3x. So our u dash, take that 3 to the front, 3e to the 3x. Vv is the thing on the bottom, 4x squared plus k. So our v dash is, well, the k is a constant, that goes away. 4 times 2 is 8. Drop that power, we have 8x. Lovely. Let's stick all this together then. So f dash of x, let's do it over here, a bit more space. What are we going to have? Well, we need a u dash, so 3e to the 3x. We need a v, so we're going to have that bracket on the bottom, 4x squared plus k. Take away u, which was e to the 3x, times by v dash, so times by 8x. So actually just write that out at the front. All over v squared, so that bracket, which is going to be squared. Lovely jubbly. The way they want it formatted at the end then is they have some function g. You can see kind of what's missing. So we obviously have the entire denominator, that's not in there, so that's part of g. There's the e to the x's as well, and I think that's going to be the only bit that we need. So as we expand the brackets, we're going to get 12x squared. We're going to have the minus 8x, and then we'll get the 3k as well. So we'll write that down. We'll have the 12x squared minus 8x plus the 3k, and then our function g, what is it? It was e to the 3x over that denominator, 4x squared plus k, all squared. Looks good to me. Given that the curve of the equation y equals f of x has at least one stationary point, find the range of possible values of k. So the reason they've got to split it up like this is now we look at it, we've got this function and this function. This one over here can never equal 0. When you've got a fraction set to equal to 0, it's just about the top. But e to the power of anything is never 0. So this whole stuff is not 0. So f dash of x equal to 0 is exactly the same as having that 12x squared minus 8x plus 3k is equal to 0. So we want to have at least one stationary point. So that tells us that we needed at least one solution to this equation. This is a quadratic, so our discriminant must not be negative. It can be 0 because it can be one stationary point. It cannot be negative. So our discriminant is always b squared minus 4ac. So b was 8, so squaring that 64. Take away 4 times 12 times 3k, and we want that all to be bigger than or equal to 0. Let's work out some numbers. So what's 4 times 12 times 3? Not plus, 4 times 12 times 3. We get 144. So this, we're going to have 64. I'll add this over as well, is greater than or equal to 144k. So our k, therefore, is less than or equal to 64 over 144, so 4/9. It's a very nice simple number, which is always a good sign. Let's double check it is correct. What paper is this? This is number 12. I assume it's on the same paper. 4/9. Oh, one thing I didn't think about. Do we have? Yeah, it's a positive constant. So yeah, it's one of these things about. Do you need to note, like, actually write this down again? They do have it in the mark scheme. So even though, kind of by definition of k, it's in there, you should still write it down just in case. Will I check that to the end? So part B, do we have like condone? Condone means allowed, isn't it? Double check. Condone. Accept. Yes. So you don't actually need to write down the 0 bit because, like I say, it is defined up here. But it's always better to give them exactly what's written in the mark scheme. So what we can say is that k is greater than 0, so therefore 0 is less than k, which is less than 4/9. So it's going to be always beneficial to leave exactly what's on the mark scheme so that when they mark it, they can see that and they can just tick it basically. So they don't have to worry about looking for other bits of it. Much nicer for them to mark if they can just see the answer straight away, and then they can just walk through and see that, okay, as long as you've done everything correct along the way, all good. But if it matches it exactly, it makes it a bit easier for them to mark. Let's keep going then. So we want to express this in partial fractions. So it's going to be like a over 2x minus 1 plus b over the other bracket of x plus 1. If we write that in one denominator, what we can have is going to be like a lots of x plus 1 plus b lots of the other bracket, 2x minus 1. This would all be over like the product. But these should be equivalent, so we can say that this is just equal to 3. And it's like we've had both of them over that same denominator and just cancel them off immediately. This is good then. So from here we can do a few things. You can either compare coefficients, but that will make simultaneous equations. They've both got x, they've both got constants, so not the best way of doing it here. Instead, let's just plug in the values of like minus 1, see what pops out. So looking at x as minus 1, what do we get? On the left, we'll have 3. On the right, this whole bracket will vanish. We're left with this one. So it's minus 2 minus 3. So that's minus 3b. So b is minus 1. And now then, let's plug in x as a half. So x equals a half. What we're going to get? 3 on the left still. This is going to be 1.5 a's, so 3 on 2. The b bracket disappears, so we can see that a is going to be 2. That all looks good to me. It does say express it in partial fractions, so I will always write that out. It doesn't say find a and b, it says express it as partial fractions. So this is the same as a, which is 2, over the 2x minus 1 plus, well, minus 1 on the top in it, so we can do minus 1 over x plus 1. This is already good, so we're going to probably have to integrate this at some point. We've got a differential equation. They're already matching. This differentiates to this differentiates to this. So they are the log thing. If we integrate these, they're just the log of the bottoms immediately, which is nice. So what we're going to use this for now, let's have a little look. Chemical A, chemical B are mixed, oxygen is produced. Scientists mix these two chemicals, measure the total volume of oxygen produced over time, total volume, blah, blah, blah. T chemical mixes modeled by this different equation. K is a constant. 2 hours of chemical, we've got 3. Solve the different equation. Okay, dokie. So on all of this, all we actually need is that fact, and that we have the point of 2 hours and volume of 3. So we have TV is equal to 2, 3. Because right now we have no unknowns in here. Our integration will give us one unknown, so we need 1 point to be able to find the general solution to this. Not the particular solution even, not the general one. So let's actually do the integration now. We'll bring all the v's to one side, all the t's to the other. So v's on the left already, so we're going to have a dv over, and now we've got that 3 there, but notice 3 was up on here, and the rest of it's just the same. So I'll leave the 3 there, but still the v. Everything left on that side then is just the same as what we were given above. So integrating that, again with respect to t. So left-hand side, nice and straightforward, that is the log of v. Right-hand side, like we said, it's exactly the same as this. So it's just going to be the log of the bits on the bottom. So it's equal to, move this out of the way of that 3. Yeah, this is equal to the log of 2x minus 1. Like I say, this matches perfectly. Like this is the exact derivative, so we don't need to have any scale factors. Take away the log of x plus 1, and then we're going to have some plus c. Everything else here, though, is in terms of logs, yeah? So do your plus c as like plus log c. Completely fine to do. Absolutely fine to do. So let's do this now. We want to get rid of all the logs. We can't just cancel them all out. We need to first combine this together, and then we cancel it out. You can only really cancel logs when they are like the entire side is logged, or you have like one side is logged and this has got no logs at all. Then it's fine. But where you've got like the addition or subtraction of logs, you need to first combine them together before you can eliminate the logs. So left-hand side, we'll leave it alone, log v. This right-hand side then, so anything that's positive is going to go on the top. So we're going to have c lots of 2x minus 1. Anything negative on the bottom, so x plus 1 down there. That looks good. Now we can cancel the logs. So exactly the same, but without the logs in there. So what we have is that v is equal to c lots of 2x minus 1 over x plus 1. This is the general solution. Now we go and take our point of 2, 3, and we'll plug it in to find that value of c. So t is 2. Is it t? I've used x all the way. I've used x all the way through. I shouldn't have used x anywhere. If that happens in the exam, just write down somewhere t equals x. As long as they haven't used x anywhere else. Do you know what I mean? Have we used x? We did at the top, but that's okay. Like, it's a different question now. Do you know what I mean? It's not like we need to use that x again. So this should be okay. Obviously, try not to do that. Do try and use the correct letter in the exam. But this should be fine because you're saying they are the same thing. So this is good. Let's plug in our value of 2 and 3. So we know that 3 is equal to c lots of 4 minus 1 is 3 over 2 plus 1 is 3. So therefore our c is just 3. And we can rewrite then the particular solution. So v is equal to exactly what they have. 3 lots of 2, and I will do the t's now. 2t minus 1 over t plus 1. All looks good to me. Nice when you get exactly what they're showing. So now what have they got? They noticed there was a time delay between them being mixed and oxygen being produced. There was a limit to the total volume of oxygen produced. Find the model, the time delay, get an answer in minutes, and the limit, get an answer in meters cubed. So we want to think about the kind of top, like where is this going to end up as you let t go to infinity? The way we do that, we'll expand the brackets. So the top row is 6t minus 3. Bottom row is still t plus 1. And now, this might not be something you've seen in A-level maths. The answer is just 6. It's 6 over 1. The way it really works, though, is we're going to divide everyone by the highest power of t. So we've got 6 minus 3 over t, 1 plus 1 over t. So now as t goes to infinity, these fractions go to 0, and we're left with just those 6 and 1s. So it's going to tend to 6 as t tends to infinity. So that is the maximum value. As long as we don't start above that, we should be fine. But we know at some point we did only have 3 volume. So we were beneath that. So therefore v is capped. V is going to be less than, and it will never actually equal to 6. We can never actually get to the 6. That looks good. Another way to think about it as well then for the time delay, I think it's going to be as simple as like, when would this be 0? Well, whenever the top is 0, so whenever t is a half. So I think we need to have our time delay. If I could spell, time delay is 1/2. So whenever the volume was 0, I mean, it's basically saying that this is going to produce some negative volume for the first half. Is it minutes or is it minutes they're talking about? No, so this is going to be talking about hours. That's one thing to note as well, like the units we've got here. So this is in terms of hours. So that's 30 minutes. So they're basically saying that, yeah, this is going to take half an hour before it does anything, effectively. When it does do things, it gets to 6 and then it will stop. Was that in meters cubed? That's meters cubed, meters cubed. So yeah, we are fine, but we'll still write down meters cubed there. So we should have stop at 6, and we don't start till half an hour after. Let's double check all of that stuff. What number is this? 14. What did we get? 30 minutes and 6. That's a good sign. Everything's correct. Lovely. Let's keep going. We've got a C, we've got a P, we've got an L. We've got parametric stuff. L is a normal. Find the equation for the normal. Okay. So what do we need to do? We need to differentiate, and then we're going to get that point, and then we're going to plug the point in into the differential, get the tangent, use that with the point to find the straight line. We need to also do the negative reciprocal with it being the normal. So let's do that. Some things don't matter by the order, but we could find the point first, or we could find the derivative first. I'll find the point, just get it done. So we know it's going to be when t is a pi on 4. So let's do 2 tan of pi on 4. And we're going to add 1 to that. What do we get? We get 3. So t equals pi on 4. What does that imply? It implies that xy is equal to, well, x was 3. As we do the y, we're going to have 2 divided by cos squared. My calculator does not have a, what do we call it, a sec button. So we need to do the squared like that. And then we're going to add 3 to that one. I get 7. So 3 and 7. Let's move that left a bit so I can see it a bit better. And maybe write this 3 a bit nicer. Lovely. Jubbly, that's one bit done. Actually put that up there, why not? Now we need the derivative. So to get that, we want dy dx. We don't have either of them, but we don't have y in terms of x. So we want dy dx, but we can't get it. So what we're going to do is dy dt divided by dx dt. That's very obvious, that's a much bigger one. So that's good. Let's do them individually then. Sec squared, what does that differentiate to give? It integrates to cos, integrates to tan even, but I don't think it differentiates so nicely. Let's do that on the side. So that is 2 cos of t all to the power of minus 2 plus the 3. So as we were to differentiate this, what are we going to get? So the 2 times the minus 2 is a minus 4. We'll drop that bracket, so we'll have cos to the minus 3 of t. And then the derivative of cos is negative sine. So we'll have a sine out the back, and that negative at the front will disappear. So we should have 4 sine t on cos cubed. I'm not sure if that's in the formula book, like maybe the derivative of sec squared is in the formula book for you. Either way, it should be this. Maybe they have it written as like it's sec squared cot, maybe is what it comes out to be. Like this is going to be 4 sec squared, and then yeah, cot as well. Cot t. Which way we need it, not too sure. Sine and cos is always a good way to have things written because they're easy to work with, aren't they, really? That's good. Let's do the same now for dx dt. That's a little bit easier to do. So it's going to be 2 sec squared t. Having both of those be the same is quite nice. I imagine bits are going to cancel off now, and they will, because we're going to do this divided by this. So if we do that, what are we left with? 4 on 2, that's a 2. Sec squared on sec squared, it's just a 1. And cot, that's just cot. So that's for dy dx. We want to find the equation of the normal. So we can plug in the pi on 4. So if we do 2 over tan of pi on 4, what do we get? We get a math error because we didn't put a bracket at the end. If we put the bracket at the end, we get 2, which is nice. So if we think, yeah, t is pi on 4, implies that dy dx is going to be 2. So when we think about doing the normal stuff then, what's going to go on? That tells us our normal gradient, so the gradient of the normal is minus a half. We have our point up here as well, 3 and 7. So let's do all that stuff. Y minus 7 is equal to negative a half, x minus 3. I'm going to times the left by 2, so I get 2y minus 14. And that negative 1, I'm going to open that bracket up, so I've got 3 minus x instead. From here then, this is looking good. I want to rearrange for a y, so I'll add a 14. So 2y is 17 minus x, but I'm going to divide these all by 2. So over 2, over 2. Get rid of that 2. Lovely, jubbly, exactly what they wanted. That's that bit done then. Show that all points on C satisfy this equation. So you can go and solve it, find it, do you know what I mean? But if it's just show that it's doing that and they satisfy it, you can actually just plug in the values and show that you always get. Yeah, you can just plug in the x and show that it gives us the y. Do you mean? Either way is going to work here. Will that be easier? I don't know. Sometimes just verify, and it is much easier to do it that way around. Here, what I'm going to do though is actually use like tan and sec squared have a nice relationship. So if we know that cos squared plus sine squared is 1, we can divide them all by cos squared. So 1 plus tan squared is equal to sec squared. So what we can see is like sec squared's in there. And we can just rearrange this then for tan. So what is that? Tan of t, it's going to be x minus 1 over 2. You see x minus 1 in there, and there's a 2 over there. All looking good, isn't it? So now let's take our thing for y, but when we square this, yeah, let's just rearrange this all completely to get like sec squared over there. So let's square that. We'll have x minus 1 squared all on 4, and then we need to add 1 to that. So that's going to tell us that tan squared minus plus 1, i.e. sec squared, is going to equal to this thing plus 1. So x minus 1 all squared on 4 plus 1. So now we can take that into the y equation and see what that gives us. So y is going to be 2, lots of that thing. So x minus 1 all squared over 4 plus a 1. And then still plus that 3 on the outside. Expanding these brackets, the 2 in the quarter makes me a half. 2 times 1 is 2, plus a 3 gives me a 5. And that is exactly what they wanted, so that's looking good. Straight line with this equation has intersects at 2 distinct points. Find the range of values for k. So, okay, so one thing to be careful of when we've got parametric, this curve doesn't go forever. So if you just set this equal to it, you'll find a kind of phantom solutions where the rest of the curve exists. So I find it a lot easier to actually go and draw this. and then see what it's doing. So it's a curve with a gradient of -1/2. The normal we found is that same gradient. So the line we have is parallel to the normal. So let's go and look at that normal. I'm just going to draw a line through there, like to get it parallel. And then we're going to slide it down. One of them, that's kind of like, as you move through, we've got one solution here, and then two, and then one again. So we kind of need to think about all those boundary points depending on what bits we're looking for. So let's put lines there, there, and there. Let me just double check exactly how many solutions we wanted. It says 2 distinct points. So these are all the barriers between, like, we have 0 if it was higher, we have 1 in that range, we have 2 between these two, and then like 0 at the end. But you can see, like, we have 2 at that point, but then there's only be 1 at that point at the end, and then it's 0. So where do we want the 2? We need to be like in this range. We are allowed to be on this one, that's okay, but we're not allowed to be on that one, because this is going to be the one where there's like one repeat solution at the end. So let's think, where do these hit them? We need to find these points here, that one and this one. The one on the left there, the second one I drew, that's just the end point. It's going to have the lowest x value. Tan generally increases, do you know what I mean? Yeah, between this range, tan is purely increasing. So it's the lowest value, it's the pi on 4, or the negative pi on 4, sorry. So as we plug that in, let's see what the coordinates of that are. So let's set my answer to be negative pi on 4. I've got 2 tan answer plus 1. So my x coordinate there is -1. I'm going to put these up here. Yeah, this is -1. Let's do the y coordinate then. So that's 2 sec squared plus 3. Get that old answer, minus pi on 4. 2 divided by cos of the answer, all squared, all plus 3. That gives me a 7. I think I maybe could have seen that, and I probably could have got this all from down here. Actually, it's probably maybe an easier way to get this. But no harm done. That looks good. So what we know, we have this curve and it has a gradient of -1/2. You could go through and write down like y minus y1 is x minus x1, blah, 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 do all that stuff. But the gradient's -1/2. Every step we take to the right, we go down by half. So if we're at 6, we've got to take one step to the right. Where are we going to get there? 6.5, i.e. 13 on 2. That looks good. Second thing to do then, for this point down the bottom, that is a tangent because it hits it once. So the gradient there is -1/2. So what we want to do is take our dy dx that we had, wherever that was. It's 2 cot t, isn't it? And set that equal to -1/2. So if we have, 2 cot t equal to -1/2. Yeah, that should be 2 cot t, not 2 cot 2. This is 1 over tan. So if I times by tan, and I can divide by -1/2, or times by 2. So I'm going to have a tan on this side is equal to a -4, I want to say. 2 over there makes a 4. Cot over there makes a tan. Negative over there makes a negative. Yep, looks good. So t is inverse tan of 4. Inverse tan of 4. Not so nice, it's just like 1.32. But I will use it going forward as like inverse tan of -4. Oh, -4. So it should be should be minus that number. Tan's an odd function, so if you forget the minus inside, you can just whack the minus out the front. The minus comes through tan, basically. Like tan of minus t is just minus tan t. Same for sine, same thing. That's good then. So we've got that t value. We want to go and find that. I wonder if there's any easier way to do this. If we can maybe like think about differentiating this instead and setting that equal to it, because this just seems like a not very nice number. Do you know what I mean? It will work, but it's just not the simplest way of doing it, I don't think. So yeah, we'll look at the Cartesian form instead. Let's differentiate this thing. What's going to happen? Dy dx will be, well, the bracket's got a 2. Bring that down with a half, gives you a 1. Drop the power of the bracket to 1. And then we're going to times by the derivative of the bracket, which is 1. And then the 5 goes away. So it's just x plus 1, x minus 1. That's much nicer. If we set that equal to -1/2, what we're going to have is that x is equal to 1/2. And that does match, like it's positive, that looks good. With the diagram, it looks like maybe this is twice as far as that one, vice versa, that's twice as far as this one. So that looks okay. So we have, a half, what's the y coordinate going to be? Again, we could probably just plug it into this one, might be the easiest thing. So a half minus 1 is minus a half. Square that's a quarter, with that as an eighth. So it's going to be 5 plus an eighth. So 41 on 8. Same idea, we need to go back up though. We're going a half step. Every step was a half, so it's now a quarter. We need to add a quarter to that. So that's 2/8, so it should be 43 on 8, I think. So our k value, we needed to have 2 distinct points. So remember what we said earlier, the 13 on 2, we have that point and this point. That's okay. Did we actually include the t on the end? Let's double check that. Yes, we do include the point on the end. If we didn't, then neither would be allowed. But this point only has one solution, so we don't actually include that point at all. So our range of k, we still need to be doing 13 over 2 and 43 on 8. 43 on 8 and 13 over 2. But we include the 13 over 2, we don't include the 43 on 8. That looks good to me. Number 16, was this all correct? Let's find out. 43 on 8, 13 on 2. The fact we've got all the way to the end and getting the right answer probably means everything else on the way through is true. But they're not going to show you that, weren't they? Lovely. That looks good to me. Very long-winded, that one. Lots of maths going on. Maybe each individual step's not too bad, but just lots of steps to think about, Jimmy, one after another. Looks good. Let's keep going. Now we've got a little bit of an easy one. So find the second derivative. So to do that, we've got to do it once. So first one, 3x squared. Bring that 2 down, gives me a 4. Drop it to a 1. Minus an 8. And now I'm going to do it again. Bring that 2 down, gives me a 6. Drop that 2 to a 1. That just becomes a 4. So that's that bit done. The second one then, set that equal to 0. So doing that, what we have, x is minus 3 over 2. And that looks good to me. For the second one, which is concave. Oh, which one is concave? I always forget which one concave is. It's either going to be bigger or less than 0. Let me double check on the mark scheme. So it's either going to be the answers like we need to be bigger than minus 3 over 2 or less than minus 3 over 2. Which one is concave? Does that mean it's fallen over? So it's negative? I'll guess negative. It wanted us, the answer should be minus, like we need to be lower than that. Have I done this really silly as well? Yeah, I have. Sorry, 2 over 3. So what we can think about, like, this is an always increasing function, yeah? This is a function that goes up. We want to be like the negative point of that. What we found is where it crosses the x-axis, this is minus 2 on 3. But we always want this thing to be negative. So we really want to be less than that minus 2 over 3. So that tells us, yeah, x is less than minus 2 over 3. And that is exactly what they want. Lovely jubbly. Yeah, so concave, you're falling over. Whereas convex, you are rising up into the air. Is that convection currents? Is that what they're called? Maybe they could think that's a good way to remember it. Are they called convection currents in physics and fluid dynamics? I think they are. So that's a good way to think it. Convex, you're going up. Maybe that's not quite right, but if it's wrong, it's not a very bad way to remember it anyway. Let's keep going. So curve out this equation. Point of 3 minus 10, turning point at P. Given that this is true, show that K is 12. Okay, so it has a turning point at P. So we don't need to integrate yet. What we need to do is know that when we plug in 3, this is 0. So let's do that. As we plug in 3 and set it equal to 0, what do we get? 3 cubed is 27, times 2 is 54. This is going to be 9 times 9, 81. 3 times 5 is 15, plus a k. So what do we have in the end? 54, take 81, plus a 15 is a minus 12. So what we're saying is k minus 12 is 0. So k is going to be 12. Looks good to me. Part B, find the coordinates of the point where c crosses the y-axis. Okay, so we want to integrate, find the plus c. So let's do the integration. What are we going to get? Y will be raising that power, we get to the 4. Dividing 2 by 4, we get a half. Raising that power, we get 3. 9 divided by 3 is 3. Raise the power, we get a 2. Divide by a 2, we get 5 over 2. Raise the power of, remember this is minus 12. Sorry, positive 12. Yeah, positive 12. So raise the power, we get an x. Divide by 1, we don't get anything at all. Well, we still get 12, don't we? and we have a plus c. And now is where the minus 10 comes in. So when we plug in p, what we're going to have is that minus 10 is equal to all of these bits. I'm going to do this in a calculator though. So we've got 3 to the power of 4 over 2 minus 3 times 3 cubed plus 5 over 2 lots of 3 squared plus 12 lots of 3. Why has that gone in somewhere else? Plus 12 lots of 3. That gives me 18. So what we have at minus 10 is equal to 18 plus c. So c is minus 28. That looks good to me, I think. Let's double check. Number 5. 0 minus 28. Yep, lovely, jubbly. Next one. Cover this equation. Find dy dx. So this is implicit. This bit's just x. Do it normally. 3x squared. This bit's both, so we'll do it like product rule. So I'm going to ignore the y's. 2x becomes a 2. The bit I ignored, I whack down there. Now I'm going to ignore the x's. Y becomes a dy dx. And then whack down the bits you ignored. So 2x. 3y squared, do it normally, we get 6y. But it was the wrong letter. We used a y. We should have used an x. 47 just goes away. Now we want to factorize for the dy's. You can see we've got 2x and a plus 6y. I'll take these bits to the other side. So we'll have dy dx, taking those bits over, minus 3x squared, minus 2y. On the bottom then, 2x plus the 6y. Well, looks good to me. Is that actually correct? Let's double check. Number 7, 2y plus 3x squared. And then 2x plus 6y on the bottom. That's good. And they put the negative out the front. Lovely, jubbly. So at the point of minus 2, 5 lies on the curve. Find the equation of the normal. Given it's in the form, blah, 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 blah. So let's plug in those values. We want dy dx evaluated at p. So we're going to have minus 2x squared. X squared is 4 times 1 minus 3 is minus 12. Take away a 10 over a minus 4 plus a 30. So we have minus 22 on 26. So we want the normal. So that tells us that the gradient of the normal, if we flip it, make it negative, 26 on 22, so 13 on 11. That number seems a little bit not nice. Do you know what I mean? 2 prime numbers in a fraction like that isn't so... They're not nice prime numbers either, so I would just double check. Did I do this all correctly? 2 squared is 4, times by 3 is 12, make it negative. 5 times 2 is 10, make it negative, minus 22. 2 times 2 is 4, make it negative. 6 times 5 is 30. Yeah, all looks fine. Yeah, all does look fine to me. So we've got the gradient. Then it's y minus the point that we have, 5, equals that gradient by x minus 2, so x plus 2. Then times by an 11. I'll expand this by 13. And then I will collect my like terms and bring them all to one side. So let's go to the right. I'm going to the right because it's nicer to add the 56 to the 26 than it is to take it from there. But it makes no difference really, does it? So if we do that, what do we get? Is it 81? I think it's 81. And we'll have a minus 11y plus an 81 equals 0. But also, yeah, more positive things this way. More positive things. Is that good? 13x, 11y, 81. Lovely. Jubbly. Next one then. Right, that last question I started doing didn't have anything about calculus in it, so I scrapped that one off. So we'll carry on for this one. So we've lost one question, but we still have how many? 102. That's all good. We've got parametric stuff, show the Cartesian, and then we'll find a tangent. So we don't actually need to do the tangent stuff, do you know what I mean? Do we? Ah, no, we do, yeah, it cuts. No, yeah, we don't need to do the tangent stuff for this at all. I don't think that seems to be related to it. It might well be having the Cartesian, but we could do it without, so I'll show you it without. So we want to find the equation of a tangent to c at p, written in this form. P is the point where the c cuts the y-axis. So if it cuts the y-axis, x is 0. So what we can do is say that we're going to factorize this thing, or at least find the solutions for it. So what will we have for this one? I've got Wolfram Alpha open even. So t squared plus 6 minus 16 equals 0. It should have two solutions because of the negative c, positive a. What do we get? 2 and negative 8. I'm going to assume, like, given that x is bigger than something, do you know what I mean? Well, t is bigger than minus 3. Okay, yeah, so t is 2. That's good. So, lovely. We have our t value. What we want to do then is differentiate now. So, dy dx, we don't have y in terms of x, so we're going to have to do dy dt divided by dx dt. So, doing them individually, what do we get if we do this one? Well, when you differentiate log, you end up with the thing on the bottom and its derivative on the top. Obviously times by that 6 still. So we can just put that 6 on top, yeah. So that's good for dy dt. Dx dt is even easier, isn't it? Dx dt, we're going to have 2t plus 6, or i.e. t plus 3. 2 lots of t plus 3. Not sure if we need that, but it's good to spot like bits of them popping out because they're going to probably divide off. Do you mean? Most likely they're going to divide off. So as we do this, what's going to happen? Dy dt on the top, 6 over t plus 3. The other one on the bottom, 6 times t, 2 times t plus 3. Times done by t plus 3. What do we have? Well, it's going to be disappear from the top, be a square on the bottom. T plus 3 all squared. And our 6 over 2 is just a 3. So that is dy dx. We know that our t is going to be 2. So dy dx evaluated when t is 2. This will actually give us the gradient of the line. So doing that, 2 plus 3 is 5. Square, and that's 25. 3 over 25. Do we have the y and the x? No, but we know t is 2, so we can go and find them. So if we think about x, when t is 2, what are we going to get? 4 plus 12 is 16. Oh yeah, it should be 0, shouldn't it? It should be good. And y then, plugging that in for t is 2. What do we get? We're going to have 6 log 5, yeah. That's always a good sign when that starts appearing. So y minus y1, y minus 6 log 5 is equal to x, 3 on 25. Lots of x minus 0, so there's lots of x, yeah. They want to have all integers, so we need to times by that 25 down there. So let's do that. We're going to have 25y minus 6 times 25 is going to be 150, lots of log 5, is equal to 3x. And what they'd like is to have the x and y on one side, log stuff on the other side. So we'll bring that x over. So 25 minus 3x, add the logs over, equals 150 log 5. All looks good to me. Let's double check everything's correct though. Number 9, we get y equals, no, hold on. 25y minus 3x is 150 log 5. 25y minus 3x is 150 log 5. Lovely jubbly. Next one. So we got something here, do some partial fractions with it. So what's going to go on? We still have a quadratic on the bottom, linear on top, so nothing weird's happening. We've just got an a over x plus 4 plus a b over x minus 2. And what we can write then, put that in one denominator, we'd have a lots of x minus 2, not equals, plus b lots of x plus 4, and that should equal the numerator of the thing that we're given already. So 3kx minus 18. Looks good to me. Let's move that over a little bit. There we go. Lovely. Yeah, because we could have like both of these with the same denominator, doing both the brackets, but just cancel them off straight away. That looks good. In terms of case, this is fine as well. So as we do this then, let's plug in a value of x is 2. What do we get? Left-hand side, this goes away. 2 plus 4 is 6. We have 6b. 3 times 2 is 6, so 6k minus 18. So what we have is b is going to be k minus 3. And looking now, if we make x be minus 4, what do we get? This all goes away. Minus 4 minus 2 is minus 6. Right hand side then, we will have minus 12k minus 18. Dividing it all by negative 6, we're going to have the a is equal to 2k plus 3. That looks good. We actually wanted to express it in partial fractions, so we'll write that all out. So what we have is it's going to be 2k plus 3 over x plus 4, add k minus 3 over x minus 2. That looks good to me, and that is f of x. So find the exact value, for which this is 21. So we want to take our thing, we want to integrate it. So let's do that. If we integrate what we have, well, what we've got going on is fractions where we have a linear on the bottom and a constant on the top. So we want to make sure that this thing is 1 and that this thing is 1 when we do the integration. So for both, we're going to factorize out the numerator, effectively. So as we do this integral, especially 1 and minus 3, what we're going to have is that the first one will be like 2k plus 3, lots of log x plus 4. And then very similar to the other one, k minus 3, lots of log x minus 2. And we just sub the limits of 1 and minus 3 into those. So let's do that. When we sub in 1 for the first one, we're going to have 2k plus 3 of log 5. And then, so this is the only time I think I've ever seen where we've had to actually use the modulus in A-level maths so far. So when we do this integration for logs, it should actually be the modulus. All of these should be modulus of the thing. And you can see that we needed that in this case because we're going to plug in 1 and make a negative. It would obviously be for the same for the negative 3 going in, wouldn't it, as well? Why am I 3s? Why can I not draw 3s today? I don't know what. There we go. Oh, that's quite a good 3. But yeah, so we actually need the modulus in all of these. So get rid of those little bits, get rid of those little bits, and then just put some big lines there. Boop, and boop. Not with a 2. Pop. Lovely. So when we go to this, like, we're going to have 1 minus 2 is minus 1. Mod of that is 1. Log of all that is just 0, so that goes away. Similar thing's going to happen here. I'm pretty sure we're going to get a 1 and that's gone away. And this one, the minus 3 minus 2 is minus 5, so it's the positive of that because it's a modulus. So this is going to be k minus 3 log 5. But remember, this is in the second one, so it's been taken away. This looks good, so we can now factorize the log 5 out and think how many bits do we have? So how many k's? 2 k's, take away 1k, I have a k. I have a 3, take away a negative 3, so that's adding another 3, gives me a 6. And this was equal to 21. So doing that, what we can say then, we can rearrange for the k. So if we divide by log 5, so one thing actually is to do here, that the way I've written it, don't really want to have this k plus 6 afterwards, because it looks like you could read it like that. Do you mean? So we want to not have any ambiguity. So either you can just put brackets around the log as well, or just move that there. Either way would be fine. When I say bracket around the log, I have like log 5 in brackets, k plus 6 in brackets. So you do that bit first, and then times them. This is good though. So yeah, we can divide by the log 5 and take away a 6. So 21 on log 5, take away 6. Does that look good? Number 10. 21 on log 5, take away 6. Wonderful. Next one then. So tank in the shape of a cuboid, it's been filled with water. We got a 20, we got a 10, we got a H, we got a 5. Water's flowing into the tank. We got T minutes, H meters for the height, V for the volume. The tank doesn't have thickness. The rate of change of V is inversely proportional to the square root of H. So the rate of change of V is inversely proportional to the square root of H. Show that dH dt is equal to lambda root H, or lambda over root H. So what do we want to do? We have T minutes, I thought something was H. We do have a H in there. Oh, is that it? Oh. Show. What do you mean? Okay. So yeah, we want to work out then the height of the water in terms of, well, we want to look at the volume and height relationship. So what is the volume of the water? Well, it's a cuboid, yeah, which is effectively a prism. So we need the surface area of 200 times by the length of h. So when we go and look at dVdt, dVdh, sorry, it's just 200. So where we have dHdt, we can think of expanding that out. It's going to be dH, dV, dV, dt. So the third variable, the one that's not used there, just becomes like a bridge between the two. We're looking for dHdt, that's good. dV dt they've told us. And we just worked out dV dH. So this is the opposite of that, the inverse, 1 over it. So this is the same as 1 over 200. Lots of the k on root h. Make my k a little bit more k-ish. I would say my handwriting is better than this in pencil than in on the iPad, but it's not really. it doesn't get any better, really. So this is good. We just want to combine together then our k over 200. So it's actually just like, whoop, whoop. And then this whole thing, that is our lambda. So that looks good to me. Now then, given that initially the height of the water in the tank was 1.44, so that's one coordinate of 0, 1.44. Exactly 8 minutes after it started from the tank, the height was 3.24, so 8, 3.24. Use the model to find the equation. Okay, so what do we want to do? We're going to integrate this using like separation of variables. We've got our 2 points, so there'll be 2 constants, and then we'll plug them in, and then we'll realize what's going on. One constant's there, one will be the plus c from the integration. So let's actually go and do this integration then. It's a differential equation, so let's bring the h's to one side. I will have a root h, so h to the half, dh is equal to lambda dt. Integrate both these bad boys. What do we get? We'll raise that power 3 over 2, divide by it, so 2 over 3 at the front, is equal to lambda t plus a constant. And now what points do we get? 0 and 1.44. So what we can do, if we plug in the 0, and actually as well, what I'm going to do is call this 2/3 of c, yeah? Just so it matches that coefficient on the right hand side of the on the left hand side, so with the h. So when we plug in the 0, this becomes t. These will cancel out, do you know what I mean? So it's a bit nicer having c just be straight away like 1.44 to the 3 over 2. It's not that nice still, but it's better than it being 2/3 of that. So there's no harm in calling this 2/3 of something. It's still a constant as long as it is just a number. Doesn't matter what you call it. You could call it something horrible. Do you know what I mean? This would be fine. Do you know what I mean? As long as then you say like c and y are just like constants, you'd be okay. This is still a constant. There's no point in doing it, I don't think, not in this example anyway, but it's perfectly valid to do. You could also draw a picture of, like, you could draw something. You could draw like a nice picture of a house and be like, yep, where house is a constant. Completely fine to do. It's a symbol. Just because you use letters, letters aren't special. They're just symbols. So anything can go there. Doesn't matter what it is. C, 2/3 of C, a house, picture of your mum, anything. As long as it's a symbol, we can then redraw, recreate somewhere else. All is good. So let's take our values, plug them in now. So the first one with the 0, we'll work out that C. So like I say, that's gone away. The 2/3 will cancel. C is 1.44 to the power of 3 over 2. I think it's 1.2 if we were to square root it. So it's 1.2 squared, 6 over 5, cubed. 6 over 5 cubed. So we've got 216 over 215 is C. For the 8 and the 324 then, we're going to plug them in as well. So with the 2/3, I'm actually going to just put like this is now 3 over 2 on there, do you mean? So I've got h, which is now 3.24, to the power of 3 over 2 is equal to 3 over 2 lots of lambda t, and t is 8. So 3/2 of 8 is 12. So this is the same as 12 lambda. And then we need to have that plus c on the right hand side as well, don't we? Well, actually plus, yeah, because we've times by the 3 over 2, so that's good. So it is just 216 on 215. The bottom should be 125. That's 5 cubed, wouldn't it? 125. This looks good. So lambda then is just going to be this, take this, divided by this. 3.24, 3 over 2, minus 216 over 125, all over 12. Let's whack that in the calculator, see what pops out the other side. So 3.24 to the power of 1.5. Let's make sure your calculator's on before you start doing stuff. 3.24 to the power of 1.5. Take away 216 on 125, and then divide that whole thing by 12. So I get 171,500. Did they seem correct? What number is this? Number 11. 513 on 1,000. No, it's not right. This is good. Something's gone slightly wrong here. Let's just start again. So looking at this, let's just rewrite this again where I do times by the 3 over 2. So you've got h to the 3 over 2 is equal to 3 over 2 lambda t plus c, which is 216 on 125. Let's check that everything there seems correct. Yeah, looks good. So we'll plug the values back in again. I wonder if I just typed in the calculator wrong, maybe. Or let's just rearrange for lambda, maybe. So we'll take away that fraction. So h to the 3 over 2. Take away 216 on 125 divided by 3 over 2 lots of t. I don't know if anything different is going to happen here from what I've done. Let's find out. So we've got h, which had the value of, it was 3.24, wasn't it? Yeah, 3.24. And that was all minutes, wasn't it? T minutes, yeah. So, yeah, 3.24 to the power of 3 on 2. Oh, hold on. 3.24 to the power of 3 on 2. This whole thing then is, oh my god, is over, not under, over. Right, take away 216 on 125, then it's over 3 over 2 times by the 8. I get the same number, 171 on 1,000. Okay. I was right the first time. Where they've got it written, I was thinking about my lambda being correct, and then like the 2/3 are there. So like if I do 3 over 2 lambda for my thing, then this is all good. So that's lambda. So that's going to be 171 on 500. So 3 over 2 lambda is what they gave us, 513 over 1,000. So sorry, yeah, I was correct first time there. Nothing was wrong there. I just didn't realize I needed to times by 3 over 2 to get the same answer in the book. That looks good. So yeah, let's write this in the form then. So h to the 3 over 2 is equal to a. So that's going to be the thing inside the t. Oh, next to the t, sorry. So the 513 on 1,000 plus our b of 216 on 125. I've missed up a t somewhere. Yeah, it should be by the a. Lovely, that looks good to me. Hence, find the time taken for when the water starts flowing into the tank for the tank to be completely full. So how full can it be? It can be 5. So we just want to set h to be 5 and then solve for it. So what we can do, let's rearrange it in terms of this. So t is going to be equal to the h to the 3 over 2 minus the b over the a. That's what we want when we're thinking about t. So let's plug in the values we have. We have 5 and we know what a and b are. So it's the same as having 5 to the 3 over 2. Take away the b that we just found, which is the 216 over 125, and then divide that by the a of 513 over 1,000. So let's have a look at this. We've got 5 to the power of 3 on 2. Take away 216 on 125. All over 513 over 1,000. I get 1.35. So 1.35 minutes. Does that look good? No. 18 minutes. Did I type it in right? Have I just been typing things in the calculator wrong is what I'm wondering. No, I didn't. Yeah, my calculator. So always be careful. Where I've typed this in, the calculator has put the negative 216,125, like that fraction. It's put it in the power where I'm doing like the minus, like the 3 over 2 power on 5. I didn't press right to go out of like the power land, and I was still up in power land when I did the minus stuff. So it should be a minus 216 on 125 in that fraction, not up in the power there. And that does then give us, yeah, the 18 that we want. Nice, that's all good. Was it 18.4 they want? Yeah, 18.4 means. Beautiful, that looks spot on. Let's keep going. Binomial expansion, don't care about that. Use the answer though, so yeah, I will get the binomial expansion. First three terms. So let's get that one. What do we get? We get 1/9 minus 2x's on a 27, and then plus x squared on a 27. I'm going to put this all over 27, so it's 3 out the front, yeah. 3 minus 2x plus x squared, all over 27. That's good. Use answer part A and algebraic integration. Estimate the value of this. Yeah, estimate just simply because we've done this approximation, do you mean? So we can write this slightly differently, where you think the bottom is, well, 1 over the bottom thing is this entire thing. So this is equivalent to having still the 0.4, 0.2. 6x is still there, but that entire denominator is now replaced by the thing we found above. So we're going to have that over 27 times by the 3 minus 2x plus x squared. That looks good. I can take the 6 over 27 out the front. Still got my limits of 0.4 and 0.2. And I'm going to expand that x out. So I've got x cubed minus 2x squared plus 3x dx. Let's integrate everything then. So x to the 3 goes to x to the 4, divided by a 4. Here, x to the 3 over 3, we had a 2 already. Here, x squared with a 3 over 2. And we need to add on a constant, but we don't because we've got limits. So 0.4 and 0.2. That looks good to me. I'm going to see if that is the correct, like, as long as I've got the integration correct, I'm just going to plug the numbers in. It's a bit fiddly in it, plugging them all in. So B, we should end up with x squared on 3. What we're doing? Oh, with this stuff as well, isn't it? Yeah, so the 4 should be on 18. So if we do 6 on 27 times 1 on 4, 1 on 18, 6 on 27 times 2 over 3, 4 over 27, which is what they wanted, and then 3 over 2 times 6 over 27 is a third, which they always want. So this is good to just plug these numbers in, do it on your calculator, and plug them all in, should all be fine. We get an answer of 223 over 6750. That looks good. So for part C, find the exact value of it now. So here, they're going to use the reverse chain rule. So if we think about kind of making a guess, how do we know it's the first chain rule? First of all, is like we have x squared on the bottom, x on the top. So will it work? Ooh. Actually, no. We need to do partial fractions, or we need to separate it out. I'm trying to think what the best way to do it is. Do we just separate it all out? I think we might do. I don't think what the best way of doing it is. So what I'm thinking, let's expand the bottom. We'd expand that out, we'd have x squared plus 6x plus 6. It looks like it should just be like reverse chain rule. But the reason it's not is because if we differentiated this, yeah, you'd get an x, and it's like, okay, lovely. But you also get the plus 6. One way we can deal with that then is doing like plus 6 minus 6. Or like plus a number to make this work. I mean, so this is 6. It's 6 times too big. 3 times too big. It'd have to be 18 that goes up there. Oh, don't do that much. So we could do that. And then try and kind of separate it out and do the ones individually. Where we could then think about the chain rule. Yeah, this is going to be the way that we do it. No. Why can I not do this one? Substitution. Silly me. Yeah. So what I'm thinking does work, but it does things that you don't do in A-level maths anymore. So it'd be the idea of like, we're going to split this up into like the 6x plus 18 and then this bit on the bottom. That would be exactly like the log formula for integration, because it's like the exact derivative on the top, or like 3 times the exact derivative. And then the minus 18, you'd have like over this bracket, it's the same bracket, and over that bracket. Well, that should be 9, sorry. That should be 9 again. Yeah, it'd be over the same bracket. And then you used to have formulas for like if you want to integrate this sort of stuff, it's like arc sine and I can't remember exactly what they were, but arc sine and arc cos and sort of stuff like that. But I don't think you do that anymore. So that's why we have to do substitution. So how are we going to do that? Firstly, we're going to write out the wrong bit, and then we're going to have our u be the thing inside the bracket. So 3 plus x. So when we go and differentiate du, dx is just 1. So effectively that tells us that dx is just du. They are the same thing. When we now go and plug in the limits, we can see like we've just added 3. So our new limits are going to be 3.2, 3.4. So let's plug this all in together. Like we say, 3.4 and 3.2. 6x, well, x itself would actually work down, but we can also have that x, if we take 3 away from the u, we've got that, so x is going to be u minus 3. So on the top, 6 lots of that, u minus 3, all over the 3 plus x, which was u, squared. And now let's keep going, 3.4, 3.2 down there. So we've got 6u over u squared, so 6 over u. And then I've got a minus 18, u to the minus 2. du, integrating both of these then, we're going to have 6 on u is 6 log u. Take away, well, we need to raise the power, u to the minus 1. Divide by that power, so positive 18. Now we need to plug in 3.4 and 3.2. So what happens now then? 6 lots of log 3.4 plus 18 over 3.4. Take away 6 log 3.2. Take away 18 over 3.2. So in terms of logs, how did I want us to leave it actually? Was it a log b? So we've got 6 log of 3.4 over 3.2, 17 over 16. And then we need to add these numbers up. So it's going to be like 18 lots of something in it, but I'm just going to calculate. 18 over 3.4, take away 18 over 3.2. So we get minus 45 on 136. And that is all spot on. Lovely, jubbly. That looks good to me. Nice, yeah, let's keep going. I might take a little break and then I'll be back in like 10 minutes. Right, back again. Let's carry on. So we've got this thing. Let's find dy dx. So to do that, we will times the 3 by the 4. We'll get a 12. Drop the power 2 squared. 7 times 2 is 14. Drop the power by 1. 5. It's just 5. Well, 5x is just 5. For the next one, 2 times 12, 24. Drop the power here. Drop the power. Drop the x all together. Find when this is equal to 0. So if we do that, x will be 14 on 24. Divided by 2, 7 on 12. Does that look good to me? Seems alright. Yep, 7 on 12. Lovely, jubbly. Next one. We've got a y. Yep, we've got an f. We've got a g. We've got some functions. We want to find the derivatives. So if you differentiate f, what are we going to get? Well, we need to differentiate the power. So the power is 4x squared minus 1. So we'll get 8x. The minus 1 goes away. And times by the original thing. So e to the 4x squared minus 1. For g dash of x, log of x goes to 1 over x. So we've just got 8 over x. From here, then it's just solving. Nothing else is about calculus. So we'll move on from there. Here, then, we need to have parametric stuff. So what we got? Parametric differentiation. So the tangent to c at p has this equation. So 4, 2 is the point. So if we could do this, we could either like do it implicit parametrically, or we could rearrange and sub the bits into each other. I think probably just doing it parametrically here will be okay. I don't see why not. So if we think about doing dy dx, what do we have to do? We have to do dy dt, all divided by dx dt. On the top then, when we do this one, what do we get? Minus 3t squared. All divided by this thing. Well, we'll bring the 2 out the front. We'll have that bracket, but with a lower power. Difference in the bracket is 1. Times over that is all good. So that looks quite nice to me. We want to find, obviously, the this in terms of t. So we need to know, like, when we have these values, what actual t is it. So if we set our x, the t plus 3 squared equal to the 4, what we're going to have is that t plus 3 is equal to plus or minus 2. So t is equal to minus 3 plus or minus 2. We know that we have this fact here, so therefore t must be the one with a positive, i.e. minus 2 minus 3 plus 2 is minus 1. So that's our t value. So we can say then that dy dx evaluated at that point p is going to be the same as if we just plugged in minus 1 to the t. So squaring it makes no difference. You've got minus 3 on top. And 3 take away 1 is 2, times by 2 is 4. So that's good. We're on the tangent to it. So that's our gradient. We know the point is 4, 2. So we're going to have y minus 2 is equal to that gradient minus 3 over 4. Lots of x minus 4. Times the left by a 4. What do we get? We get a 4y minus an 8. Times the right by the 3 and expand that bracket like with a negative as well. So it's going to be 12 minus 3x. Do you want it all on one side? Nope. So let's bring all my x's to the left and my standard numbers to the right, and I have exactly what they wanted. Looks good. Curve C is used to model the profile of a slide of a water park. Units are in meters, y being the height above the slide level. Oh, the greatest height. So thinking about that, like, where do we get turning points or anything going on? If we were to set this equal to 0, what do we get? It's going to be 0. So when t is 0, we get 1. Does that seem good? That doesn't seem good. No. So that's the only turning point that we get. But where else could the maximum occur? It's up here, yeah. We found this point down here, but obviously it's because we are limited in our domain of t, we have possible maximums that are not turning points, where they can occur at the end. Same for minimums, do you know what I mean? So they're not turning points, but they are a max or min because they are simply the end point of the function, and it's the highest point. It just ends at the highest point. So we need to find this highest point, basically. So x being as small as possible, I think it's going to be when the t is, yeah, we can kind of see if t is positive, what's going to happen is this would be positive, but then with negative, that makes that negative, so you've got 1 take away something. So when t is negative, cubing it will make it positive. So 2 cubed is 8, so that's positive 8. 1 plus 8, 9. So do be careful on these ones when you have, not just parametric, but when your domain is limited. You could potentially have maximums and minimums that are not turning points, but they are at the end points of the functions. Very similar to if you do like domain and range in functions, trying to find the range of it. Same bit, this is just like we're finding the range, but only one side of it effectively. All looks good to me. Did it look good for the mark scheme though? Double check that bit of it. 10. Where are we? 9, and yeah, that's good. Lovely. So what's going on here? Right, faffed out some numbers there. A little bit too much to go through and fix it. Yeah, let's go with that bit. So what we need to do here, we have some function. It is 8x squared e to the minus 3x. We just want to find this area. It's bounded by c, x equals 1, and the x-axis. I'm going to end up with this sort of situation. So what have we got? Down here, this is a product. So we need to use by parts. We're going to have the integral of u v dash is equal to u v minus the integral of u dash v. Let's write that bit later, u dash v. So what do we choose to be u? What do we choose to be v? Or v dash, I suppose. We want the u to differentiate down to nothing. If we set that to be e to the x, or e to the minus 3x, it's going to remain some multiple of e to the minus 3x at all times. If we choose it to be x squared, ax squared, eventually it will become some amount of x, and eventually some amount of just constant at the end, which is nice. So that's what we're going to do. We're going to have u be 8x squared. So u dash is 16x. I think I did that. I think that's what I made wrong earlier. I did 4 instead of 16. So no, well, let's keep going. V dash then will be e to the minus 3x. Raising that power, what are we going to get? Well, raising that power, integrating that, the minus third gets spat out the front. So that's good. So our integral then is going to be the u times v. So negative 8x squared on 3 e to the minus 3x from 0 to 1. Take away the integral of the other bits. So there's another negative in there, so it's going to cancel out to make positive. And then we're going to have 16x on 3. Lots of that stuff. E to the minus 3x. That looks good. Now we still have a product here. So we just need to go and do this whole step again, but making sure you keep these the same way round. So our u this time will be 16x on 3. So u dash is 16 on 3. Our v dash is the same, e to the minus 3x. So our v is also e to the minus 3x. Then we're going to keep the bits we had. So we still have an e to the minus 3x in this stuff. But I'm going to factorize it out. So minus e to the minus 3x. What do we have? We still have 8x squared on 3. And then we'll have u times v over here. So we've got the e to the 3x. We need 16 on 3x, but it must be negative. So negative 16x on 3. Something feels, yeah, this bit, no, that's not quite right. That one should have been negative as well, negative a third. So we should have positive 16 on 9 instead. So times that by negative a third. That looks good to me. And now we're going to take away the integral of u dash times v. So that negative there makes it positive. We've got a 16 on a 9 with the e to the minus 3x. So that we can actually just perform. There's no by parts need to be done there. We're still going to have all of this other stuff. Minus e to the minus 3x, 8x squared over 3, plus 16x on 9. As we integrate this then, what are we going to get? Well, we're going to get a case of dividing by minus 3 again. Minus a third. Yeah, divided by minus 3. So 16 on 27. There is a negative, but we've got a negative at the front there. So this is going to be positive 16 on 27. This looks good. We need to also do our limits. So this should have a 1 and a 0, 1 and a 0, 1 and a 0, 1 and a 0. And now let's go and plug all these bits in. So when we plug in the 1, what are we going to get? So it's going to be minus e to the minus 3. It's then going to be all of these bits just with 1 in them. So it is just 8 thirds plus 16 on 9 plus 16 on 27. That looks good. And then when we do the 0 one, we're going to take away, so we're going to add e to the 0 is just 1. And this thing's just going to be 16 on 27 then. Looks good to me. Let's write that all together. So what's that bracket give us? 8 on 3 plus 16 on 9 plus 16 on 27. I get 136 on 27. That many e to the minus 3s, but also a negative version of that. And then with the 16 on 27 added on to that. Does that look good? That seems right. Does the mark scheme agree? The mark scheme does. Lovely jubbly. I think, yeah, I made a mistake. I'd done 4x, not 16x. And that just obviously cascaded all the way through and made it very horrible to find where it's going to be. So, no worries there. Let's keep going. Express this thing in partial fractions. Okie dokie. What do you want? You want an a over a v. You also want a b over 25 minus v. So, thinking what this is going to give us, we'll have a lots of 25 minus v plus bv, and that's going to equal to 1. So what we can do now is think about the fact that we can just look at the powers of v. So if we look at the v to the zeros, i.e. the constants, left hand side we have 25 a's, there's no b's, equals 1. So a is 1 over 25. And now if I set v equal to 25, what I end up with is that 25b is equal to 1. So b is also 1 over 25. If we look at the powers of v, we could have saw as well that like there's b minus a of them is equal to 1. No, it's equal to 0, sorry. 0 b's on that side. So they are the same. Yeah, they are the same thing. So b minus a equals 1 equals 0, b is equal to a. Lovely, that's all good. So the volume in v microliters of a plant cell T as the plant is watered is multiplied by this differential equation. Has an initial volume of 20 microliters. So that tells us that we have a coordinate of T and V. And we know that they are going to be initial, so 0, and then add 20. That's good. Find, according to the model, the time taken in minutes for the volume of the plant to reach the plant cell to reach 24 microliters. So Okay, yeah, we just want to integrate, don't we? Am I being silly? Am I over? Yeah, we just do want to integrate, surely. Yeah, I think we do. So let's do this. What is it going to give us? I'm just going to move that over there somewhere. Yeah, we've got a differential equation. So v's on the one side, we're going to have that be dv over v25 minus v, and that's going to equal dt on 10. So that's good. This left-hand side is what we found above. So it's 1/25 of these things. So when we integrate this, that's just 1 over v, yeah? Well, what we're going to get, basically, is a log v, so 1/25 of log v. And then this, what we really want is like to take the b out the front, then it'd be minus 1 at the top. So it needs to be minus b out the front. So minus 1 on 25 log of 25 minus v. And that will equal t on 10 plus, and I'm going to do log c in there. That looks good. So we need to rearrange this a little bit. Let's actually make this log c on 25, weirdly enough. So I'm going to times by 25. So all those 25s have gone there, 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 and I've just times by 25 on the top there. So, and then I can collect the logs on this side. So I've got log of v over 25 minus v is equal to 25 on 10, so 5 over 2t, plus log c. If I was to subtract this log over, that would be okay. But what I'm going to do actually is make this a negative log c up there. So this becomes negative log c. So now I can add it over. It's on the top row, and it's going to be like cv on the top. So yeah, we can cancel that bit off, and the whole thing is just c in there instead. So that looks good. Find, according to the model, the time taken for the volume of the plant to reach 24 microliters. So we still need to work out what c is. So actually, maybe it's better to leave it where it is for a second. So let's undo those steps. We have our 0 and our 20. So as we go in, make that 0, that's all gone away. So we're going to have log of 20 over 25 minus 20, i.e. 5, is equal to negative log c. So log c is equal to negative log 4. So that was with the negatives. Let's actually make it plus again, plus, plus, plus. It's all just positive. So that negative step, it was useful if we just needed the general solution, but we wanted the particular, so not so useful here. So yeah, log c is log 4. So we can take again log 4. It's going to be the same idea. It's going to be a 4 on the bottom. So log, just to walk through that again, like we have log 4, we subtract it over, so now it's like minus log 4 with that, plus that bit. This is a negative, so you can actually, it's going to be on the bottom of this fraction. So we have log of v over 100, well, let's keep it as a 4. 4 lots of 25 minus v is going to equal to 5 over 2t. Let's make that a little bit nicer. And now that we want to find the time taken for it to reach 24 microliters. So what we want to do, plug in 24. As we do that, we'll have log of, this will be 24 on the top. This will be 1. So this is going to be 4. 24 over 4, 6. So t is 2/5 log 6. Does that sound good? This is 12a. Let's double check. 12b. We got that right the first bit. And the second bit, we get... oh no, something's gone slightly wrong with the numbers. C was correct. C is good. Was that not 6? Have I been silly there? It was 24, wasn't it? Yeah, 24 on 4. Equals 2/5 of log 24. Take away 2/5 of log 1. Take away 2/5 of log 4. That seems fine. Unless 25, 2/5 of log 6 is that. I don't think it is. No, what have I done wrong there? I don't know how they've got that actual number out of it. 2 on 5, 2/5 log 24. That's 2/5 log of 1 minus 2/5 log 4. I get the So yeah, okay. Reading through this, I've typed in where they have like the answer, and then they have the line before it with the algebra written out. 2 on 5 log 24. Take away 2 on 5 log of 25 minus 24, so log 1. Take away 2 on 5 log 4. The answer that I get in the calculator is not the same answer that they've written down. Have I typed it in exactly the same? 2/5 log 24, yes. Minus 2/5, let's change that 1 to 25 minus 4, why not? 25 minus 24, and then minus 2/5, yep, log 4. Okay, so this is a little bit strange. I have this answer. The way that they've done it, it ends up being like basically the same thing, but not exactly the same. So I'm going to walk back through and see if something different does happen. So we got logs up there, it's like that. So let's go back through. We know log C is 25. So we can go back to this row and sub it into there, which is what they've done. But weirdly enough, like what I've typed in, their like second to last row doesn't equal the answer mark that they put in there. They have 24 log 6, and I have 2/5 of log 6. And looking at what they've got 2/5 everywhere. I don't know how I think they've just done a typo there in the mark scheme, which is not ideal, but I will go through this other way as well and see if this is going to be okay. So going from here then, let's just rewrite this. What do we have? Log v minus log 25 minus v is equal to 25 on 10, 5 over 2, lots of t, plus a log 4. I will take that to a negative log 4 on the other side. So t is going to be 2/5 of log 25 minus 25, sorry, log 24 minus log of 25 minus 24 is 1 minus log 4. Log 1 is 0. When you have subtraction of logs, you can do a division. 24 divided by 4 is 6. So this is 2/5 log 6. Yeah. I think that they've just got a typo and they've put 24 when they should have put 2/5 in the mark scheme. So I think that they are actually wrong in this case. Let me investigate. I'm going to go and get like some other work solutions and see if they've mentioned that. But it's very bizarre. Like this row is the same as they have written down, just expanded. They've just put 24s everywhere. Just like 2/5 everywhere. But then the next row they haven't got 2/5. They've just put 24. So I think I think everything's okay. I think I've done it correct, and they've just got a mistype in the mark scheme. It happens every now and then. So it's always careful to look out for it. You might not be wrong. They might be wrong. So what year was this? This is 2024 June 2024. Edexcel paper 2, A-level maths. Let's have a look at. Let's do PMT and then get the work solutions they've got. So PMT, Edexcel papers. Paper 2, and it was 24 model answers. Question number 12. Ah, okay. Minutes, hours. Why? Why would you ever? Why is that in maths? Why is that important? It's physics, it's not maths, changing the units all over the place. Never at any point in my degree did I have to change units around the place. So this is the answer in hours. So we times that by 60. So we do get 24 log 6 minutes. Well, that was fun, wasn't it? Part C then, show that this is going to be true. So what we need to do, we can take the bits we had earlier on, like we're going to rearrange this thing, or like one of the bits we've got. We kind of got rid of it, didn't we? So no harm done. We've got this. Let's take the C over. We know it's 4, don't we? So we're going to have log of v over 4 lots of 25 minus v is equal to 5 over 2t. So we can get rid of those logs, whack an e on the other side. 5 over 2t is v over 4 over 25 minus v. We need to then multiply this to the right hand side and expand all the brackets. So we're going to have v is equal to, it's going to be 100 lots of that e, and then take away 4v lots of that e. Add that over and divide by the bits. So we're going to have that v is equal to the bit we left over, 100 e to the 5 over 2. And then we've added this over, so how many v's do we have? 1 there. And how many there? I've got 4e stuff. So plus 4e to the 5 over 2t. All good. Looks all good to me. Check the mark scheme. 100 and then 4 on the bottom. Okay, what they've done, they've divided by this thing. So yeah, this is all good. One more little step for the form. So e to the minus 502t plus 4. Lovely jubbly. Model predicts as an upper limit for the volume of the cells. Find L, given a reason for your answer. So find the upper limit. So what we can do, it's kind of reason why they made us write it like this, basically, so we can think about this now. So this thing, where's the maximum of this thing? Well, this goes down to 0 like that. T had a lower bound, I'm going to guess of 0 if they haven't told us anything else. Yeah, 0. So where's this at a maximum when t is 0? So this whole thing is 0. E to the 0 is 1. 1 plus 4, 5. 105, 20. And what we have is that's at the very starting point. So that's the maximum, and it's just going to slowly decay. Am I being silly? This number's going to get smaller, it's going to get bigger. No, I'm being silly. Yeah, that's the starting value. Think about the function the other way around. This thing is getting smaller, and it's the bottom's going to get smaller and smaller and smaller. So the fraction itself will get bigger and bigger and bigger. How small can this thing get? 0. Can't be negative. So this can be as small as 4 on the bottom. So the whole thing can be as big as 25. So what we have is that we're always between 20 and 25. Can we be equal to 0? I'd assume so. We start at 20, so we can be 20. That's a way to spot it as well. We were given that as a coordinate, so it's not going to be kind of the one they want to find. That one is good to me. Let's keep going. Sorry about this minutes, hours things. All the maths is correct in it. Like all the maths is correct. It's just questions. You don't really see that too much past A level. So what have we got going on here then? Find expression for dy dx in terms of x and y. So let's do implicit on this one. So we need to differentiate the bracket. We'll have 3 lots of the bracket squared times by the derivative of that bracket. X gives us a 1. Dy dx gives us, y gives us a dy dx. Right hand side then, 3x squared, nothing different there. 3y will become just a 3, but then a dy dx because we used y when we should have used x. Take away 2, just goes away. We want an expression for dy dx. So we've got 1 there, 1 there. We need to expand this side out then. So we'll have one version of this thing, like from that one. So 3 lots of x plus y squared, and then plus that version with a dy dx. So 3x plus y squared dy dx. What I'm actually going to do is going to take that bit over that way. So it's going to be negative on that side. It will sit there with the 6x squared. And then we'll add that 3 dy dx on the other side. Now then, let's divide by, factorize and then divide this side. So dy dx, right hand side stays the same, 6x squared. Take away 3 lots of x plus y, all squared. All over then, the bits that we factorize out this side. So 3 lots of x squared, x plus y, all squared, plus 3. Looks good to me. Does it look good on the mark scheme? They've divided everywhere by 3. So we'll divide everywhere by 3. X squared, 2x squared, minus this bracket x plus y squared over x plus y squared plus 1. And that looks very good to me. Not that plus though. Nice, that is good. So we found dy dx. We now have a point P at 1, 0. We're going to find the normal to it. So doing that, what do we want to do? Well, we've already got the derivative. So we just need to plug in the 1 and 0. So dy dx evaluated at that point P. X is 1, so they're all just 1s, and then all the y's are 0s. So we've got 1 squared times 2 is 2. This bracket is 1 plus 0, and squaring it is 1. So this is 2 take away 1 on the top. Same way in the bottom, that bracket's still 1, so plus a 1. What we have then is a 1 over a 2, i.e. 8/2. We want the normal though, so that tells us that our gradient is going to be minus 2. And you can kind of see that there, that's always a good sign. And now then, we need to do y minus y1, 0, is equal to m x minus x1. So i.e. we have that y is going to be minus 2x plus 2. That looks good to me. Part C is not calculus. We just want to basically have this equation. We're going to set it equal, well, not set it equal, but solve simultaneously for this. And you're going to show effectively that there's only one solution to that equation. And that solution was the point P that you had. Everywhere else does not hit it. Looks good. Let's keep going. One more past paper down the drain. So what have we got now? Trapezium rule, not doing that bit. We'll do the, we'll talk about it though. So we can talk about it very quickly, like what's happened. I'm not actually going to perform this, do you know what I mean? Let's just stick in a calculator, do you know what I mean? So the only thing that's changed, we've gained a 9 up there at the top, yeah? We want to factorize that out, so we've got to like, this thing still exists as a whole object. So that 9, we can square root it and bring it through the square root as a 3, and then that can move straight for the integral sign. So whatever answer you get in part A, you just triple it for part B. Nice, looks good to me. So given that this stuff is true, find these bits. Okie dokie. So let's think about writing this all under x plus 1, x plus 2, sorry. So we have x plus 2 plus b x plus 2 plus a c. And that whole thing will equal the numerator on the left, x squared plus 8x minus 3. This one then, we can use all the powers. Where you have lots of these bits going on, generally, like these first bits, the way to solve this that's the quickest, or I find the easiest, is just to look at the powers. So like when we look at x squared, how many have we got on the left? 1. Where are they on the right? Well, there's none there. None there either. I've got a of them. Lovely. Let's look at x's. I've got 8. Here, how many have I got? 2 times a. So 2. And we've got there, b. b is 6. Not b is c, b is 6. And now let's look at the constants. Minus 3 on the left. None there. 2 b's, so 12. Plus a c. C must be minus 1/15. Does that all look good? What number are we on? Number 6. 1, 6 minus 15. 1, 6 minus 15. Lovely jubbly. Part B then. Use integration, find this stuff. Okay, well, yeah, we're not going to do it from here. We'll do it straight from there. So what have we got? 0 and 6. That looks good. A was 1. So we've got x plus 6. And then minus 15 on x plus 2. That looks good. I'm going to rewrite that 15 on x plus 2 ever so slightly, just to have it 15 out the front, so that we have a 1 on top. And in that way, differentiate this, we get 1. This thing is ready to be turned into a log when we integrate. So let's do this integration. What are we going to get? X becomes x squared divided by 2. 6 becomes 6x. And then the minus 15 log of this stuff is minus 15 log x plus 2. For 0 and 6. Let's plug these bits in then. So for the 6, 36 on 2, 18. 6 times 6 is going to be 36. Minus, this is going to be 15 log 8. So 15 log 8 8 is 2 cubed. So instead of 15, we can bring that 3 at the front and have it be 45 log 2. Plug in the zeros, 0, 0, and this is going to be then 15 log 2. We've got that negative, we've got that negative, so it's going to be adding on a 15 log 2. Get rid of that one, get rid of that one. Those numbers give me a 54. These ones give me a negative 30 log 2. Does that look good? 50 minus 30 log 2. Lovely jubbly. Next one then. So, I've got this stuff. Find dy dx. So this looks like you should do quotient rule. Don't have to. Don't have to. It's only a single thing on the bottom, single term. So we can just divide off each term on the top individually. 4 over 2 is 2. X squared over root x. X to the 3 over 2. Very similar now, but we're going to have a half. 1 minus a half gives us a half of that power. And then still minus the 4 log x. We're differentiating this, aren't we? Yep. So therefore, we're going to have that dy dx. 2 times 3 over 2 is 3. 3 over 2, take 1, 1 over 2. A half times a half is 1/4. A half minus 1, minus a half. And then 4 stays as 4 log x, 1 over x. That looks good. They want it back in terms of, so having, you can see here we've got x to the negative half, x and a 4, with a 4 and the x on the bottom, and that's going to be these bits. So we effectively want to make just that into the common denominator. So let's just do that first. What bits do we need then? So this is going to be 4x, the x to the half. So what do we need to make sure that this is still correct? Well, if I'm dividing by 4, and you've got times by 4 there, so that's going to be 12. I need to make sure I have a half, so I need to have like this is the same as this one, take away this one. This is 3 over 2. I'm just going to write that as 3 over 2. Might be easier to think about. This is 3 over 2. So this take away this is a half, i.e. the top has to be x squared. Similar idea now. I've got the numbers. The quarter's done. That's good. I need to make sure that like minus 1, well, this thing and this thing make minus 1. So this is going to be just x. And then over here, what do we need to do? We need to make sure actually we times top and bottom by root x and a 4. So 16 and root x. So yeah, we divided by a 4, so I had to times by another 4. And we had to need an x over 3 over there, so just times by another one at the bottom. That all looks good to me. Oh, and that is what they want. It's nice for show that. We want to find the minimum turning point. So from this, all we need to do, take the thing we've just found, so f dash of, well, dy dx, set equal to 0. That's the same as having that top row equal to 0. So 12x squared plus x minus 16 root x. How do they want us to rearrange it? Because this is not something you could solve so easily. It's a quartic. Like if you wanted, you could do it as a quartic, where this would be like 4 square and power 4, power 2, power 1. Not so nice though. But what they've got down here, iteration instead. So you can see what we're going to arrange it for. It's not the root, is it? We've got 12 down the bottom there and a 3 down the bottom there. So like 4 over 3, that is 16 over 12. This is over 12. It's the 12, isn't it? And you can see like we've cubed, like done some weird stuff here. So I think the first thing that's going to happen, we're going to divide off by x, root x. Doesn't exist in there, but it's still over there. So let's do that. What do we have? Well, we're going to have that 12 x to the 3 over 2 plus x to the 1 over 2 minus 16 is equal to 0. Rearranging for that 12x to the 3 over 2, we're going to have that it's equal to 16 minus root x. Let's divide by 12 and do the power of 2/3. 16 over 12, 4 over 3. This thing over 12, all to the power of 2 on 3. Lovely, that looks good to me. And then the next part is just going to be iteration, stuff like that. Let's keep going. So we've got this equation, f dash is this, y-intercept is minus 12, x plus 4 is a factor of this. Okay, so what we're going to do is we're first going to integrate. So as we do that, what do we get? F of x is going to be raised to the power to cubed. 6 divided by 3 is 2. A raised to the power by 1 to 2. Divide by that new power. Take away 23, which will raise to a power of 1. Then we'll have some plus c. That looks good. We knew that the y-intercept was minus 12, so that plus c is just minus 12 straight away. I didn't. I think it came up like undoing, but I didn't quite see that. So that looks good. Next, then we want to go through and make sure that plus 4 is a factor. That x plus 4 is a factor. So when we sub in minus 4, we get 0. So if we do that, what happens? We're going to have, for the first one, 4 cubed, 64 times 2, 128, but that's negative. Then we're going to have 4 squared times by alpha on 2. So 4 squared 16, on 2 of that is 8, so plus 8 alpha. Minus, we've got 23 times 4, they're both negative, so make a positive, 92. And then minus a 12, and that all equals 0. So 128, take away 92, plus a 12, gives me 48, divided by an 8. Alpha 6, by the looks of things. Is that what we have to do? And then rewrite it. Okay, rewrite it. So f of x is going to be 2x cubed plus a half of alpha, 3x squared, minus 23, 23x minus 12. That seems too simple for 6 marks. Question number 8. Yep, all good. Lovely. Weird, yeah, it doesn't seem like there's much there for 6 marks. Have I missed a step? No, because yeah, this is 2 marks. This, and then, well, this bit of it's 2 marks. This bit's another 1 mark. That's 3 marks for doing that bit. And then getting A is 6. That's another 2 marks. And then the final mark. Yeah. Okay. Okay. What year was this? 2020. Okay, 2020 October. Okay, that makes sense. So what's going on here? Find the area. How do we do that? Parametric integration isn't so common anymore. So if you haven't seen it, I will walk through what we do. We're wanting to find the integral of y with respect to x between 0 and whatever point that's going to be. Let's work that out very quickly. If y is equal to 0, then sine of 2t is equal to 0. So thinking 2t would be 0, or the next time that it hits that would be at pi. So t is going to be pi on 2. Could have also just read the domain as well. But just in case you didn't, that's how we want to do it. So yeah, 0 and pi on 2. But yeah, y is not a function of x. It's a function of t. So what we need to do is this needs to end up with a situation where we have y and then dt on the end. So we times by dt, so we have to divide by a dt, and we still have the x there. Make sure when you do this, the limits now have changed. So if we think about these bits, we have t, we have the t values, we need to work out the x values, yeah? This actually should say t equals... tell a lie, no, we don't need to do that. We don't need to do that, because we want them in terms of t, don't we? It's the other way around. I was thinking the first one's in terms of the x, but no. These are t, so we're already done. It's okay. That looks good. So now then, what is y? It's 5 sine 2t. So we need the integral pi on 2, 0, or 5 sine 2t. Differentiating the x, we get 6 cos. So altogether, what do they want from us? Not quite that, but close enough. So I've got 30 there. And what you can see, we've got sine 2t. But down here we haven't. Sine 2t itself is going to be 2 cos t sine t. And then with the other cos t, mixing them all together, and the dt, mixing them all together, 30 and a 2, 60. How many coses? Got 2 of them, so that's squared. How many sines? Just the 1. So that looks pretty good to me. We want to find now the exact value of r. So doing this integration, the reason they've made us set it up like this is just guide you on the way, basically. This paper might be a little bit easier with it being the lockdown ones. They might be a little bit easier for half an hour or so, these questions. So this one is reverse chain rule. We have a high power of something next to its derivative, i.e. the inside bit. So cos differentiates to give, I know it's minus sign, but it's a scale factor of it. That's fine. So this is going to come from something like cos cubed. So if we were to differentiate cos cubed, what do we get? We get a 3, we get cos squared, and then we get that sign, but the negative of it. So that's what we should have inside. We've got all the actual bits, but we're just negative 20 off. So we need to do like negative 20 times that. So our integral then, if we actually performed the integral, what would we get? The r is equal to the integral. Well, we've done the integral now because we've got minus 20 cos cubed of t. And we want to sub those in with pi on 2 and 0. If we sub pi on 2 into cos, we don't get anything. If we sub in 0, we get 1. So this, I think, is just 20. That seems too nice of a number for this answer, but seems correct. Number 12. Why have you got such weird... Every question starts at the bottom of the page, not the top of the page. Number 12. Where have we gone? We need to be here. 20. Yeah, 20. Lovely. Nice. So what's going on here? Part of the curve is used to model the profile of a small dam, blah, blah, blah. X and Y are meters. Focus the dam. Oh, okay. This isn't calculus anymore. We know the heights, we know the Y coordinate. So plug in there, find T, put it next coordinate. Nice and straightforward. Let's keep going. G is this thing. Find K. Okay, so K is E squared. Plug E squared into that. 2 comes out the front. Log of E is 1. 2 minus 2 is 0. Not allowed on the bottom. Prove that G dash is always positive. So if we think about doing the quotient rule, U over V goes to UV minus UV. Dash is all on the outside. Over V squared. What is our U? It is 3 log x minus 7. So U dash is 3 over x. For V, similar idea. Log x minus 2. V dash, 1 over x. So sticking everything together, what we're going to have, let me just move this one out of the way, is that G dash of x is going to be, so U dash, so 3 over x, times by V, so log x minus 2, and then take away U, 3 log x minus 7. Let's move myself left a little bit with everything. U times V dash, 1 over x. That looks good. And then over V squared, log of x minus 2, all squared. So we want to simplify this a little bit. The x's I'm going to put on the bottom that we have. So we're going to have an x and log x minus 2 all squared. And here then, what we're going to have, well, this is going to be 3 log x. And that's 3 log x. So they go away. This is minus 6. This is going to make a 7. So we've got 13 on that. So this is looking good. What we have then, we want to prove that this is true. So thinking about that, we need to have the case where the bottom is always positive. So because we have the x cannot equal e squared, what we just found, what we can say then is that log of x minus 2 squared is always positive. If we allowed x to be e squared, imagine it wasn't on the denominator, we'd have it be 0. It's the exact one, it is 0. So by not allowing it to be that, everything else is going to be positive. When we square it, it will always be positive anyway. So that's good. We know that x is positive, so that's positive. We also have and x is positive. So what we can say is that all of those things are positive. This is positive, this is positive, this is positive. So, and that's true, and 13 is bigger than 0. So therefore, we have that G dash is bigger than 0. If you're just multiplying or dividing things that are all positive, it stays positive. You can't get a negative out of there. Is that enough? Looks good to me. Is it fine? As x greater than 0, and this is squared. Yep. Yeah, nice. Didn't need to worry about the 13 part. But yep, that's good. The range of values for which a is, oh, the function's bigger than that. Function bigger than 0. Okay. That's just setting that equal to this and making this be positive, I think. So nothing to do with calculus. I'll just check the mark scheme. Yeah, nothing to do with calculus there. So let's keep going. Nice and simple one to get us to start this little paper. To start this next paper, I think, isn't it? Yeah, so this is October 2021 now. So what do we have? 5 times 4, 20. X goes down from 4 to 3. 24 times 3 is 72. 3 take away 2. Take away 1 is 2. 2 times 42, 84. Drop the power. 32. We get rid of the x out from there. So that's that one. That's good. And now let's look at the next one. 20 times 3 is a 60. 3 take 1 is 2. 72 times 2, 144. 2 take 1 is 1. 84 still over there. Verify, see a stationary point when x is 1. So we can see that nice and straightforward. This plus this is 144. Makes it go away. So dy dx, evaluated for x equals 1. My y even, so it looks too much like a g. That's going to give us 60 minus 144 plus 84, which equals 0. So that's good. So therefore, stationary point. Show that the stationary point is a point of inflection. So the second derivative. Oh, tell a lie. What am I doing? This is the second. Okay, we've done it in the wrong order. This is fine. It's not fine, but like we've done work that we still need to do, if that makes sense. We've just done the wrong bit first. So that's not stationary point. This means point of inflection. So let's just slide that down a row. What we're going to have is the first derivative. We need to plug in 1 into that. So 20 minus 72 plus 84 minus 32. So I guess again that is going to be 20 minus 72 plus 84 minus 32. Big fat 0. Yeah, big fat 0. Lovely, jubbly. So that top one tells us that it is a stationary point. The bottom one tells us point of inflection. So first derivative, stationary point. Second one, point of inflection. Let's keep going. So this whole question, just find R. You find the tangent, then you verify it meets it again, and then you find the error. So we're just going to go through, find the entire area. A function then, we need to differentiate, find this tangent, find that point, and that point. Do we need that point? No, don't need that one. We need this one though. And from there, we can start doing some stuff. So let us differentiate. We're going to have that dy dx is equal to, let me go left a little bit. X cubed goes to 3x squared. 10x squared goes to 20x. And 27x goes to 27. Plugging in 5, what we're going to get. So this implies that m is equal to 5 squared is 25 times 3 is 75 minus 100 plus 27. So think about that. That's minus 25 plus 27 is plus 2. So we're going to have y minus the y coordinate of 13, so plus 13, is equal to 2 lots of x minus 5. So what we don't need to expand this out. One thing to think of, we don't need to. Do we care about the equation of the line? No. What do we want? We really want like this point is kind of what we want. Do we need to worry about that? No. Am I just doing this? Am I overcomplicating it? No. Okay. They don't actually need to do that point. I was being silly. I was thinking if we needed to find that area, do you mean we would need to? This is just part A. It's actually slightly different. So yeah, different way than I was viewing it, thinking like we needed like this point and this point, but we already know them. Do you mean? So we could just do the integral. There's no harm in it. So A and B are actually, yeah, they're not related at all. So ignore me for that first phrase. So doing this, yeah, we do want y cos mx plus c. So let's expand and contract and stuff. We've got 2x's, that's a minus 10. So minus another 13. Y is going to be 2x minus 23. Looks good to me. And you kind of see as well, like 5 and minus 13. Gradient's 2. We take 5 steps to the left. Every step we take 2 steps down. So we must have gone down 10. So we've gone down 10 from minus 13. We are at minus 23. That looks good. Finding the area, or verify that C L meets C again on the y-axis. Oh, okay, so we plug them both in, we get 0. 23 even. So this one, if we have x equals 0, y equals minus 23, and down here, x equals 0 implies y equals minus 23. So that's good for those two. finding the area, then we need to do the curvy bit, take away the straight bit. So we're going to have the integral of x cubed, take away 10x squared, plus 27x minus 23, take away this thing of 2x minus 23. So plus 2x, no, take away that thing, sorry, negative 2x plus 23. This is good because our 23 should cancel because there's a 0 difference at that point. So nice. Can we combine some of these x's? Yeah, this makes 25. So let's just do that very quickly. Nice. And now then, we can raise that power to 4, divide by a 4, raise that to 3, divide by a 3, raise that to 2, divide by a 2. We need our limits. What were they? 0 and 5. 0, 5, 0, 5, 0, 5. Plugging them in, there's going to be some big numbers. All the zeros are gone, aren't they? So not too much to worry about there. Actually, it's going to be a multiple of 625 because here's 65. This is 5 in there, times that. And then this is 5 as well. So, yeah, can I do it without a calculator? 625, take that out the front. What am I left with on the first term? 1 and 4. On the second term, I've got a 2 left over there and a 3 on the bottom. So minus 2/3. And then plus the half at the end. So what we have, 1/4 plus a half is 3/4 minus 2/3. So how many twelfths is it? So this is 3 of them, 6 of them makes 9, 8 of them leaves 1 remaining. So 6, 2, 5 on 12. In the exam, I wouldn't do it like that, but it's now when you practicing to do little bits as you do this sort of stuff. Hence why I'm making all these videos so I can go back to uni. So I need to practice doing little bits like this just to make sure it's a bit easier. Well, we're correct. Numero 7. 65 on 12. Let's keep going. Curve has this equation, show that this is true. Okie dokie. So parametric, no, implicit. So the first one is just x's, nice and straightforward. 3 will come to the front. Power from 3 will go from 3 down to 2. In the middle one, we have a product. So let's ignore the y for a second. We have qx. So differentiating that, we get q. We ignore the y, write that back in. Now ignore a qx. Differentiate y, you get dy dx. We ignore the qx, so we write that back in. On the end here, 3y squared goes to 6y. But we've used the wrong letter. What letter did we use? We used y. What letter should we use? X. 26 just goes away. So now we want to make sure that we collect all our like terms for dy dx. Everything else goes away. So these bits, they're being banished to the other side. Minus 3p x squared minus qy. And then we'd have like dy dx is equal to this stuff. What factors of that did we have? Qx plus 6y. This is looking good. Like when you have a qx down there, do you mean qx is good? apx squared, everything's looking nice. Looks good. So is this differentiation, integration? I don't think it is now. Point P lies on this. So okay, no, this is not. We have this point, we have this equation. We're going to sub that into there. And we're going to do some stuff with like the normal way, we just plug it in. So we're going to plug it in and make sure that this is getting the right number. So effectively what this tells us is that our gradient should be, if you think y would be equal to minus 19 on 26 for the normal. So for the tangent, it's going to be not 19 on 26, but it's going to be 26 on 19, and that negative will have gone away. So that will equal this when you plug in these points. And when you plug in these points, it will work up to there as well. So that all seems good, all seems fine. Not anything to do with calculus, annoyingly, but obviously the kind of follow-on bits of it. So what's going on here? Let's have a look. How many have I got left to do? Ooh, okay, I've done more than I thought. We've got 79, 102. So yeah, that's looking not too bad actually. So I've done I've done a lot of this, haven't I? So not much further to go. I don't know if I'll do it in one go. I don't think I will. I think I'll have to take a break. I'm a bit concerned my iPad's going to run out of storage at some point. We'll see how it goes. So use a u sub. U is 1 plus root x. So as we do that, we're going to rearrange for x. So u minus 1. If we square that, that will be x. Move that over a little, ever so slightly. That's good. The reason we've done that is just a bit easier to sub in the top, isn't it? And as well, we want to have a dx. Easier to differentiate this than this thing. And plus, like, this is going to give you things in terms of x, and it's du, so it's going to be horrible. You'd rather have this one, and then have the dx du is going to be 2 lots of u minus 1. So bringing that power to the front, the power is dropped by 1 in it to 1, and then we differentiate inside, we get a 1, we times by that as well. So that's good. Let's stick everything together. Apart from units. So x is 16. So square root of that is 4 plus 1 is 5. If we do 0, we get a 1. So what we have, this should be equal to the integral from 1 to 5. The x on the top is going to be u minus 1 all squared. The 1 plus root x on the bottom, that's just a u. And our dx is now 2u minus 1 times du. So 2u minus 1 du. And if we collect everything here together, what do we have? 1 and 5 still. We've got 2 on the top. How many brackets have we got? We got 3 of them. How many u's? We got 1. Oh, look, that's exactly what they wanted. Lovely jubbly. Now, show that that's the answer. So let's just keep going. This one, you could do quotient rule or like doing some by parts or something, but just expand the brackets, I think, is the easiest. And I'll whack that 2 at the front to not have to deal with that. And everything here, what's going to happen, I'm going to have like descending powers of u from 3, 2, 1, and 0. But I've divided by a u as well. So actually I'm going to go from like u2, u1, constant, u minus 1. I'm going to move myself left a little bit. What coefficients do we get? Are just the Pascal's triangle. So 1, 3, 3, 1. So 3, 3, and a 1 at the end. But here we have a negative inside the bracket. So these are going to alternate. The biggest one will be positive, and then everything from there alternates through as we go. So that's good. Let's perform this integral then. 2 out the front still. Oh, still with the 1 and 5 as well. U squared is u cubed on 3. This is going to be 3 halves of u squared plus a 3u, and then minus log u. Stick in the 5 and the 1. So sticking in the 5 into that stuff, what do we get? 5 cubed on 3. Take away 3 over 2 times by 5 squared plus 3 times 5 minus log 5. The syntax error because there's no bracket on the very last one. It's still a syntax error because I've done something else wrong. It doesn't like 3 over 2 times 5, does it? Nope. So that gave me a not very nice number. Yeah, not a very nice number. Let's get rid of the log 5. Does it give me a nice one then? It does, yes. Okay. So without the log 5, 1, 1, 15 on 6. Yep. Take away log 5. That was for the 5s. For the 1s then, a little bit easier. We just need to add all the numbers up. So it's going to be 1/3, take away 3 on 2, plus 3. 1/3, take away 3 on 2, plus 3. 11 on 6. Take away log 1, which is 0. And this whole thing gets doubled, doesn't it? Everything gets doubled here. So inside, what have we got? What, 115, 6 minus 11, 6. It's 104, 6. Double that. It's 104 on 3. And then log 5 doubled. 2 log 5. Does that match up with everything? What have we got? Number 12. 104 on 3 minus 2 log 5. Yeah. Look at us go. And let's keep going. So x is sine 2 theta. Y is cosec cubed theta. Find dx, dy dx in terms of theta. Okay, so this is parametric. Dy dx is going to be dy d theta over dx d theta. Differentiating y is not so nice, is it? What is that? It is sine theta to the minus 3. So as we go to differentiate that with respect to theta, what we're going to get, the minus 3 comes out the front. That bracket lowers from minus 3 to minus 4, and then we times by by sine, sorry, the derivative of sine, so cos. So that's what we should have. Dx dt is fine as well. What's that going to be? This goes to 2 cos 2 theta. So that's quite nice with like that. It's not quite. Nearly. So let's take these all together. The y on the top, minus 3 sine theta to the minus 4 cos theta over 2 cos 2 theta. I'd be arguing that's all the answers. That's all we need to do. Find an expression. That is one. Yeah, it is. That's an expression. It's an expression for dy dx. It's in terms of theta. We have done exactly what they wanted. So we don't need to actually go around and doing stuff. Do you know what I mean? We don't need to be simplifying this down. And we'll look at the mark scheme, but the way that they phrased it, there's no reason for you to have to do things. Do you know what I mean? It hasn't said like leave it in a specific form. Just get an expression. That is an expression. Whether you want to risk it in the exam because they've not been correct in the question asking is a different thing. But in terms of what they've asked you to do, you have done exactly what they wanted you to do. Does it say anything else? Correct expression for dy implied or in any form? Yeah, so any form, as long as that's fine, you're allowed. Looks good to me. I didn't make any mistakes, did I? Let's just double check that. So when I differentiated sine 2 theta, what did I get? We should have 2 cos 2 theta, yeah. Oh, if I differentiate it. What? Why do you have a drop-down menu? When you choose the drop-down menu, it doesn't pick the one that you pick. Yeah, 2 cos 2 theta, and let's do the same for cosec cubed. Minus 3 cot cosec. Can we get a different form of that? Well, okay. Let's copy that then and take it away from what I said. So minus 3 cot cosec cubed. Take away what I said of, say, the top one would be minus 3 times by sine of x to the power of minus 4 times by cos x. Is this good? I think this is good. Does it give me 0? I think I put my brackets in wrong. Yeah, 0. So they're good. They're all spot on. That's nice. So full marks on that one. The way I've done that is I've gone to Wolfram Alpha. I've got the answer that they've given me, or like I've checked both of these are correct. Do you know what I mean? So that this didn't come up with the exact same form, but the form it's come up with, I've done that. Take away this thing, and because it's just said 0, they are the same. Yeah. So this answer is correct. This answer is correct. I've just written them one over the other one, so all is good. Find the exact value of the gradient of the tangent to C at the point where y is equal to 8. So when y is 8, we have that cosec cubed is 8. So we have that cosec is going to be 2. So this tells you, yeah, cosec is going to equal to 2. So therefore that tells us that sine of theta is 1/2. Let's have theta in. So what does that tell us? Well, theta is between 0 and pi on 2. So theta is going to be 30 degrees, but pi on 6, yeah. So that's good. We're going to find the exact value of that gradient. So we just want to take this pi on 6, plug it into here. So what I'm going to do, set my answer as pi on 6. Now, big fraction, minus 3, big brackets, sine of answer, close those brackets, to the power of 4. What am I doing? Power of 4. And then we times that by cos of our answer, making sure you're not in the power land still. Cos of our answer, and then go down and divide it by 2 cos of 2 answer. I get a number of, it's quite a nice number, considering what we've just done. Do you mean how complicated that multiplication was? 3 root 3, negative 3 root 3 on 32. Not the worst, not the best, obviously, but not the worst either, compared to like what things we've just done. Root 3 is appearing from these bits is normally a good sign. What does the mark scheme say? Number 13, minus 24 root 3. Is that the same thing? No. Have I just typed in the things wrong in the calculator? I think I just typed them in wrong in the calculator when I somehow. So let's maybe simplify this down a little bit. I'm going to write this ever so slightly differently. Minus 3 on the top with a cos. That sine of the 4 is going to be sine of the 4 on the bottom with the cos 2. So let's just try that instead. Minus 3. Oh, let's go up and get answer again. It's pound 6, isn't it? I'm not being. Yeah, it's pound 6. Yeah, it's pound 6. It's the same. I'm plugging in the same thing. I've just typed it in the calculator wrong somewhere. I will confirm it's correct. But it's the same thing they've got above. Do you mean exactly the same thing? All they've done is they've taken one of the sines, one of the coses, and make cot. Pi on 6. Set that as the answer. Minus 3. I've got a feeling I've done answer minus my thing. Of cos of answer over sine to the 4 of answer times by cos of 2 answer. I think that's what I missed off last time. Yeah. Cos of 2 answer one. Yes. Is that good? Minus root 40. 2 times too big. Oh, there's a 2. There's a 2. Yeah, there's a 2 down there. Okay, yep, that's good. So this is a no. That bit was okay, but that very last step was no. I just typed in the calculator wrong, doing everything is all good. But what we should have is 24 root 3, and it should be the negative of that. Lovely, jubbly, looks good to me. Let's keep going. We had a very similar one a second ago. I say second ago, so I don't know how many hours ago it was. So large tank, what flows in? It's a cuboid. All the sides are not thick. The base of the tank is 8 by 3, height is 5, blah, blah, blah. There's a tap down there, pouring water out. At time t, after the tap has been opened, the depth of water is h. Water is flowing into the tank at 0.48 per minute. So that's cubic meters per minute. So that tells us that dv dt is going to be equal to 48. Water is modeled leaving the tank through a tap at the rate of 0.1 h per minute. 0.1 h cubic meters again. So this is take away h on 10. H on 10. This is looking good with some of the numbers we're getting popping out there. That's good. Show according to the model that this is true. So again, same as earlier, we have here dv dt. Here they have dh dt. So we want to find a relationship between v and h. We have the cuboid. The base of the cuboid is 24. So the volume of the cuboid is 24h. So if we look at dv dh, that is just 24. If we look at thinking about dh dt, say, so what is dh dt? Well, it's going to be dh on the top and dt on the bottom there. What goes in the middle? Do you know the letter we have? dv and a dv. We had a dv dh. This is the reciprocal. So it's going to be equal to 1 over 24 of this thing, the dv dt. So 48 minus h on 10. That looks good to me. Are we going to times by something to get this on the bottom? Am I missing anything? I don't think so. Yeah, I don't think so. They've obviously just don't know what we're doing. So let's times by 24. Let's see what happens. So 24 dh dt is equal to 48 minus h on 10. Okay, yeah, and it's fine. We just times by 50. Yeah, we times by 50 and we're not there. Where's that doing things? 48 minus h on 10. 48. 0.48. So 48 on 100. Looks good. Looks good. So that's 48 on 100 still. We can make that on 100 and make that 10. Times by 100. So you got 2400. dh dt is 48 minus 10h. Then divide by 2. 1200 dh dt 24 minus a 5h. Looks good to me. Part B, given that when the tap was opened, the depth of the water tank was 2, so that is another coordinate. We have a coordinate of time and height, and they were 0 for the start of time, 2 for the meters. So find that stuff according to the model. So here we just want to integrate this, bring my h's to the left. So I'm going to have a dh over 24 minus 5h, and that will equal to 1 over 1200 dt. Integrate both sides. What we're going to get, well, the left is basically the log thing. I'd like to have a minus 5 up there, so I have to divide by minus 5 at the front. So doing that, what do we get? Minus a fifth of log 24 minus 5h, and that would be t over 1200 with a plus c. And now we'll take that point that we had alongside with the equation we've got and solve for the one unknown. So what we can do to make this a little bit easier, this is log of stuff, yeah? So I'm effectively going to call this c actually the negative of a fifth of the log of a constant. Reason being, as we go and plug in t as 0, this all goes away, and now we can cancel off the negative fifth log. So what we basically have is that c is equal to the inside part there when t is 2, so c is actually equal to 14 in that case. So yeah, this goes away, the fifths cancel. We take e's to both sides, so these all go away. All we've got is c, it's 24 minus 5h, h was 2, 5 times 2 is 10, 24 take 10, 14. So that looks good. We then want to rearrange this for h. So what we're going to want to do is go from this row and times it by negative 5. So I have log 24 minus 5h is equal to, if we do 5 on 1200, is that 240? 1 over 240. Yeah, 1 over 240. That's now negative. And then plus the log of 14. 14 just seems like a weird number. It doesn't seem like a number that should be appearing, but I think it seems fine. Seems okay. So we want h, don't we? So what we can do, we need to kind of combine the logs together, or just, yeah, we'll just take the e's at both sides. So 24 minus 5h. When you have powers, like we're going to do e of this entire side, but when we have like additions in the powers, we can separate them out. So it's e to the minus t on 240, and then e to the log 14 is just 14, so that's going to pop out the front. You can like do this rearrangement first, and this will just be the c. I mean, it could be like e to the c, and then if you didn't do the log bit of it, and then you just solve for this number. Both ways are fine. Absolutely, both ways are fine because it just cares where we end up. The order you do those two bits in, the rearranging and the finding c, doesn't really matter. Has c affected us? I mean, we have c, but if I just had written c here, would it have changed anything? No, not at all. So when you do it, those two things are kind of independent. The order you do them in doesn't really matter. I don't think, maybe there's a situation it does happen, but 99% of the time, no, it doesn't make a difference. Sometimes it can make it harder though. Do you know what I mean? Rearranging it, like how is it easier to plug stuff in? Which is why I like doing it this way around, because we can make this like be a bit nicer. And it's like straight away you've got numbers. It's a bit easier for you. So just want to rearrange the h. So if we add that over, take that away, divide by the 5. I'm going to have 24 minus 14 e to the minus t on 240. And then I need to divide that by a 5. It's not very good 5, is it? 5. The 14 just does not feel right, but everything else seems okay. So we will double check the mark scheme. What question number is this? Number 14. Where am I going? H is 24 on 5 minus 14 on 5 e to the minus 240. 1 on 240. 24 on 5, 14 on 5, 1 over minus 240. Lovely jubbly. Given that tap remains open, according to the model, tell me whether the tank will ever become full. Give a reason for your answer. Nope, it won't. It's going to be to 24 is the maximum it'll ever get to. I'm pretty sure, looking at it. Oh, no, 24. 24 on 5. Yeah, 24 on 5, so we get to 4.8. The way we can do that is look here. What we're going to have is, if this was equal to 0, this would be 24 on 5. So you can say dh dt equals 0 implies h is equal to 24 and 5. That is less than 25, less than 5, sorry. So therefore, no, it won't be full. Never going to become full. Is that fine? Is that what they want? Is that okay? Yeah, it should be fine. I think this is okay saying it. There's a few other ways you can do this as well. You can go through and like find the limit as this thing goes off to infinity. Do you know what I mean? So like as this goes to 0. So this is all 0. You have just 24 and 5. So a few ways you can do it here. Maybe that's not quite as exactly what they said was. So for my version, dHdt is equal to 0, which implies h is equal to 4 over 5 or 4.8, sorry, or 24 over 5. And then the equation can be solved when h equals 5. I think me writing that down shows that you can never have h equals 5. So maybe if we write that and then we say, so therefore h cannot be 5. Maybe that would be, just to make sure you've ticked all the boxes just in case. Is that good? Looks good. How many have we got? Still a few. I'm going to have a little break later and then charge up a little bit. Get some food in my belly. So I'll be back in who knows how long. Right, hello again. I'm back. We have 182 at 102, so 21 to go. Rightio, what have we got? Y is x times 2x plus 1 to the power of 4. So what we're going to do is the product rule. So if we have u, that can be x. We can have u dash will be 1. V, well, other way around, v at the top is going to be the 2x plus 1 to the 4. So as we differentiate that, what happens? The 4 will come out the front. We get the bracket with a 2x plus 1, but that has dropped down from a 4 to a 3. And then we need to think about the fact that the differential inside the bracket would be 2. So we times this all by 2, so it's actually 8 out the front. That looks good. And now we're going to cross multiply. So we're going to have one lot of these bits. So 2x plus 1 to the power of 4 plus the cross multiplication the other way. So 8x, lots of those bits. So 8x, lots of this bracket with a 3 for the power. And what do you need now? What we need to do now is to factorize out the 2x plus 1 cubed. So to do that, what do we get? 2x plus 1 cubed out the front. What we're left with on the first bracket, or the first term, we have 2x plus 1. On the second one, plus 8x. So altogether, that bit's going to be 10x plus 1. We also have this bit. Lovely jubbly. Let's check that's all good, but it looks fine by me. What number are we on? 3. 2x plus 1 and 10x plus 1. Lovely. Spot on. Oh, power of 3. Power of 3 as well. So this is good. A is a constant, so it's actually 2 possible values for A. So let's rewrite this thing first. This is 3x to the half. And then we want to integrate. So we're going to raise that power up to 3 over 2. We're going to divide by that power, i.e. 2/3. And we times by the 3. So that 2/3 of 3 is just going to be a 2. For the A, we're going to raise that up to AX. And now we want to sub in 4 and 1. So for the first bit, subbing in 4, what we're going to get, well, square root in it is 2, cube in it is 8, times by 2 is 16. For the second bit, we'll have 4 A's. And then for the 1s, we'll have 2 plus A. And what we know is that equals A squared. So this is a quadratic, effectively. Might not look like it to start with, but yeah, it's what it's going to be. So let's expand our brackets. We have 16. Take away the 2 is 14. 4a take a is 3a. And we can have that equal to a squared. So we've got a squared minus 3a minus 14 equals 0. Put this in the calculator, see what it tells us. So squared, and then minus 3, and then minus 14. What numbers do we get? Not very nice ones. We get that a is equal to 3 over 2 plus or minus root 65 on 2. Looks good to me. Let's see what the answer said. Number 5 was it? Oh, number 9, yeah, skip right through. Oh, I didn't get the right roots. Right process. What have we done? Did I just expand my brackets slightly wrong? So let's plug things in again. 4, when we square root it, is 2. Cube it is 8 times that by 2 is 16. And then 4a. That looks good. That's 2 and a 1. That makes 14. That does make 3. That does make 8 squared. Let's try everything again. Did I do the integration wrong? 3 over 2, 2/3 of that. Don't think I have done it wrong. What's gone wrong? 2 to the 1.5 plus a. Use limits. So it was 2 times 8, 16, plus 4a minus 2 plus a. That's right. It's 2a squared. So double that, double this, double that, get rid of that. What's going on instead? Whack that on the calculator. Let's see how that 2 changes things. The number itself didn't seem so nice, did it? The 64, or root 65 and stuff. So here, what do we get? Yeah, a is either minus 2 or 7 over 2. That seems a little bit nicer. So yeah, that's good. So always make sure you're double checking you've got the exact same thing. So what's going on now? They're manufacturing soft drinks with a capacity of 500 ml. Company models the height, the can is shaped of a right circular cylinder with radius r, height h. In the model, they assume that the can is made from metal of no thickness. Prove that the surface area can be moved with this thing. So in general, for a cylinder, a right circular cylinder, what we're going to have is the surface area is equal to the 2 circles, one on top, one on bottom. So we've got pi r squared for both, so it's going to be 2 pi r squared. And then if you think about the actual kind of shape of the container, you can unwrap it. Think you've got a tin of beans or something. You can take the label of tin of beans, big rectangle. How long is the rectangle? However wide that is. How tall is it? However tall this is. How wide is that? 2 pi r. How high is that? H. So 2 pi r h. And now, look at what we've got there. Look what we've got here. This bit is that bit, do you know what I mean? We're matched up. The only thing we've got is a h, and we don't want to have h over there. So we need some relationship that involves r and h. We know the volume is 500. So let's work out the volume of this thing. Now, yeah, that's h. That's r. So volume of a cylinder is the volume of the cross-sectional area, pi r squared, times by the height. We know that's 500. So rearrange for h. What do we get? 500 on pi r squared. And now let's take this thing, stick it in for that h. So pi's will cancel. 500 times 2 is 1,000. I've got an over r squared there and an r there. So I end up with a r on the bottom. And that is exactly what they have above. So that's always a good sign. Given that r can vary, find the dimensions that has a minimum surface area. So let's rewrite this ever so slightly. This is 1,000 r to the minus 1. So ds dr, sorry, is going to be the 2 pi r squared differentiated. So 2 pi stays there, 2 comes to the front to make 4 pi. So 4 pi r. And this negative 1 comes out. So negative 1,000 r to the power of minus 2. We want to solve that equal to 0. So if we times by r squared everywhere, we're going to get 4 pi r cubed. Minus 1,000 equals 0, so equals 1,000. So effectively, r, if we divide by 4, we get 250. Divide by the pi, we get 250 over pi. And we want the cube root of that. Looks good to me. Double check that is correct. What number are we on here? Number 14. So we want the dimensions of it. Okay, yeah, so dimensions. So we've got the r. So let's make sure we've got the h then. So using that, we can go back up here. If we know what r is, we can square and plug it in there. So h is going to be 500 on pi. That looks too much like an eat. 500 on pi, and then times by, well, divided by this thing squared. So we can flip it, stick it in there, making sure that we change this from 2 to 3. That looks good to me. Let me just double check that they are the right answers. So 250 on pi, we do the cube root of that. I get 4.3, which is good. For the height, I need to do 500 on pi times by pi on 250, all to the power of 2 on 3. I get 8.6. 8.6. Lovely, jubbly. Looks good to me. Part C. With reference to the shape of the can, it's just a reason why the company may not choose a metric can with a minimum surface area. So, shape of the can. Why would they not do it with a minimum surface area? I'm wondering if they're going to go so fancy thing like how cans break, what cans do to break. Like, is it because they have this kind of corner? You never see cans with corners; they have curved edges in it to make sure that they haven't got the weak points. Corners are the weak points, hence why their cans like circular, not cuboid shaped. Do you mean if any corners is where they could break more easily? Hence why they make like the tip is in as well to make the smaller bits on the top and bottom, doesn't it? Version of the shape of the can. Why are they not used to it with this minimum surface area? Mathematically, I'm trying to think of anything other reason for it. Not too sure. What have we got size-wise? Centimeters. So it's actually, oh, okay. So when you look at this, this is the radius, yeah, 4.3. And this is the height, 8.6. So if we doubled the radius, that's the diameter, yeah. So what they're saying, this can is as wide as it is tall, which is that's not really can shape. It is can shape, but that doesn't seem quite like drinking can shape to me, especially not if it's a 500ml one. So it's going to be like, imagine you take the 300ml ones and you've squashed it down a little bit and then expanded the entire thing. That's going to be big. That's going to be way too big to hold, really. Not too big, but yeah, it's going to be way too big. 8 centimeters, 8.6 centimeters is way too, that's actually quite big, yeah. That's going to be a hard thing to put your hand around and hold, Jim, if you've got something that big. So, yeah, wouldn't say it's too big. Too big to hold. What have they said on the mark scheme? Yeah, too big for the size of our hands. It's square in profile. All cans are taller than they are wide. Yeah, it's different than the other cans, so it would not be easy to stack with the other ones as well. So that looks good. Let's keep going. Guess we want to find that thing, don't we? Yep, 10 marks for it. What have we got up here? We need to find a tangent, find out where that hits the y-axis, and then do the difference between the curve and the tangent and integrate from 0 to that point. P is 415. That's good. So we need to first differentiate. So doing that, we'll do 5 times 3 on 2. That's 15 on 2. Drop that power from 3 on 2 to 1 on 2. Minus 9x becomes minus 9. So that is dy dx, because the 11 just goes away. Doesn't look very y-ish. If then we plug in the value of 4, what do we get? Well, square root of 4 is 2. Times by 2 is 1. Times by 15 is 15. Minus a 9 gives us a 6. So that's good. So we can find the equation of that line now. Y minus y1, the 15, is equal to m6, x minus 4. Spanning that out, we're going to have 6x on the right. We're going to have a takeaway to 24, but we're going to add 15 to it, so minus 9. Looks good to me. So we know that that point happens. We don't actually care about that point at all. We need to find the area, show it's 24. Okay, so what we need to do then, we're going to integrate from 0 to p, i.e. when x is 4, of the curvy part of it, so the bit we were given originally, the 5x to the 3 over 2, minus 9x plus 11. Take away that tangent we just found. So take away 6x, but plus 9. And hopefully then, this pops out to be exactly 24. So we need to raise the power. We're going to raise it to 5 over 2, and then times by 2/5. 2/5 of 5 is 2. This one, raise the power to x squared, and then divide by a 2. I'll actually undo that. I'm going to do it with 3. If you see here, we've got 9 and, sorry, with the 15. 9 and 6 makes a 15. So same process, raise the square up, or the power up to a square, 15 over 2. And same idea here, 20. That's going to become 20x. That all looks good to me. So make my 2 at the front look a bit more 2-ish. Lovely. Let's plug some stuff in. All the zeros are just going to go away. 4s then. So square root of 4 is 2. 2 to the power of 5 is 32. 64. This is going to be 4. So half of that is 2, so minus 30. And that's going to be plus, doesn't seem quite right, does it? Plus 80. That's definitely not 24. You can kind of see things going on here. This is 34, so should that be 10 somehow? Should that be 2.5 or something strange like that? Well, with the 11, that'd be minus 9. So let's check, is that correct? It was 4, wasn't it? Yeah, it was 15. Graded definitely 6. Did I type in some numbers wrong? That's 16, 8, yeah. 16 divided by 2 is 8. So I square rooted instead of squared. So yeah, 16 divided by 2 is 8. Times by 15 is going to give us 90. I think. Am I really wrong with that? 15 on 2. 16. 120. So that's good. You can see now that makes minus 40. Add them up. 24. Lovely. Jabbly. All looks good. Let's keep going. Got some partial fraction stuff to do. So what can this be written as? A over p plus b over the other bracket of 11 minus 2p. So we're effectively going to have that 1, the numerator on the left-hand side, is equal to a lots of 11 minus 2p plus b lots of p. So what we can do is we can first of all look at the constants. So if we look at p to the power 0, on the left hand we've got 1. On the right, I've got 11 a's, no b's though are constant. So straight away I know that a is equal to 1 over 11. Now if we look at the other powers, what we can do is we can say that we have 0 is equal to minus 2a, so minus 2 elevenths, plus a b, so b should be 2 elevenths. All looks good. We're studying meerkats. Populations by this differential equation. Can't be more than 5.5 of them though. P's in thousands, well, so 5.5 thousand. There's population of meerkats. T is measured in years. Give it 1,000 meerkats population when the study began. Sum the time taken in years for it to double. Okay, so we still need to solve this. Yeah, we've done the partial fractions for a reason. So it's a differential equation. What we're going to have a dp, and we're going to bring all the p's to the other side. So p and 11 minus 2p. That will equal to the 1 over 22 dt. So thinking about that, we just did it above. So to express this in partial fractions, let's actually write it down. So it's going to be 1/11 over p, and it's also going to have then plus 2/11 over 11 minus 2p. Looks good. So from there, yeah, what happens when we actually integrate this thing now? So for both of them, well, what we can say for this one, we'd like to have a 1 on top. So can we rewrite that with a 1 on top? Yeah, we just take the 1/11 out the front. So it's 1/11 of 1 on p. And for this one, we'd like a minus 2. So I'm going to leave the 2 there, take an 11th and make it negative. And that will be over the 11 minus 2p, like that. So now we integrate both those parts, which is just this left-hand side. What do we get? We get 1/11 of log p. Take away 1/11 of log 11 minus 2p. And that will all equal t over 22. And again, I'm going to use log c, or 11th of log c here, just matching what everyone else is doing, really. That looks good. Yep, that does look good. So from here, let's try and collect everything up. Do we have anything? Okay, yeah. There were 1,000 meerkats when it began. So we have 0, 1,000 as RTP. So we can plug that in here if we'd like to. There's no reason why we can't plug it in here. But what we can do is make it a little bit easier and just rearrange slightly. So if we times it by 11, doesn't seem too bad. So all of these 11s are just going to go. That's gone, that's gone, that's gone. And this over 22, this is 9 over 2. So maybe let's, yeah, we'll leave it like that. That's good. And then let's like kind of combine all of these logs together. So this on the left hand side would be log of p over 11 minus 2p. We would subtract this over, so it'd go on the bottom. Looks good to me. That equals 2 on t. We've got time taken in years, so let us do that. 2 is going to equal 2 log p on c over 11 minus 2p. So that's what we need to use, but obviously we've still got the c in there. So just somewhere along this line, we need to find the c. So again, you can see these are independent processes. Once you get to this point, you need c, and then you can work with it. But you could have found c earlier on doing it any way you wanted to. How do we find c? We plug in our 0,000. So if we kind of look at this point, what we can say is when t is 0, this whole side is 0. So you need to have log of 0, like log needs to equal 0, so this must be 1. So when we had p as 1,000, what are we going to have inside that? We're going to have 1,000 over c lots of 11 minus 2,000. Tell a lie? No, they're measured in thousands, so get rid of the thousands, it's just 1 and 2. That 11 and the 2,000 there made me feel like that was going to be the way. Simply because like 11 and 2,000 are they're too far apart really, Jimmy, to be normally dealing with each other. This is good. So like I said, yeah, we want to make sure that this is 0. So if we raise both sides to the power of e, what is this? It's 1. This stuff cancels out. You've got that must be equal to 1. So what that's saying is that the 9c on the bottom is equal to 1 as well. So c is 1 over 9. That looks good. So if it's 1 over 9, you can imagine that being then 9 on top instead. So we can cross out this c, whack a 9 up there. And now what we want to do is we want to find how long it takes to double. So thinking about that, we put it set up for time already, which is good. It started at 1,000, so doubling takes us to 2. So effectively, it's going to be 2 log 9 times 2 is 18. 2 times 2 is 4. 11 take that is 7. So 2 log 18 on 7. Let's double check that's correct. Number 16. What have we got? 2 log 2, 2 log 9, 2 log 7. Yeah, they're log 2 and log 9 together, aren't they? Lovely, jubbly, looks good to me. Next bit, we want to rearrange for p. Okie dokie. So this is t, well, not that bit, the row above is t equals, yeah. So we know e to the t, well, e to the half of t is going to equal to that bit inside the log, 9p over 11 minus 2p. The reason I said half of t, we've got a 2 there, yeah, so we need to divide that done by that first. Let's times across by the denominator. So 9p is going to be 11e to the t on 2. Take away 2p to the e t on 2. Add that p over, and then factorize. So we're going to have 11e to the t on 2. Adding that over, what bits do we have that aren't p's? Well, we've got that 9, and then we've got 2e to the t on 2. And I'm going to guess this is like a one I did earlier, where they're going to want to divide by this, so you'd have it like just down there by itself. Yeah, exactly that. So yeah, they get cancelled from here, and this one will get a negative version of it in the power. So 11 over 9e to the minus t on 2 plus 2. Is that correct? 11 over 2 plus 9e to the minus t on 2. Lovely, jubbly. Looks good to me. Next one then. That's one pass we've done. So what have we got? F of x is 8 minus x log x. It cuts it at these 2 points. Find a and b. Okay, do we actually need this? No, this isn't. This again, yeah, this is not calculus. So good. Bye. One less question to do, and we've got left now 86. That's what we're going to be 40 and 15. 15 to go. So big bowl. Bowl is a hemispherical shell. Inside the bowl, initially the bowl is empty, and water begins to flow into the bowl. When it's H, this is V. According to the model, it's given by this thing. Find the rate of change of the depth. So what are we looking for? The rate of change of depth, dH/dt. What do we have? Well, we don't have a h anywhere right now, but we do have a v, and that's the only other variable we have. So that's going to be the link. We can obviously find a dv/dh from that, so that's not such a bad thing to have. So dh/dv, which is going to be that bit. We must need a dv/dt as well. So that's good. They tell us down here the flow of water into the bowl at a constant rate of 160 pi. So that is volume per second. So that is that bit. We just then need to differentiate this thing. So let's do that. It is a product rule, but what we could do is just expand the brackets here. I think that's probably the easiest way. 75 on 3 is 25. You got 25. It's not 5. Funny looking 5 if it is. 25 pi h squared minus, just times an h out. 1/3 pi r pi h cubed. So if we differentiate this, what is dv dh? Well, the first bit, 2 comes down, gives us a 50 pi h. And the next bit, the 3 comes down, pi h squared. That looks good to me. So that is dv dh, the reciprocal of this thing. The dv dt is the 160 pi that we had there. So all together, 160 pi on the 50 pi h minus pi h squared. All our pi's can cancel. 160 on 50h minus h squared. That looks good to me. So we check it's correct. Number 8. What did we get? Oh, when h is 10. Okay, yeah, when h is 10. So 500, take away 100, it's 400. 16 on 400 is 4/10 or 2/5, which is, yeah, exactly what we have. Lovely, jubbly, looks good to me. Given that the flow of water into the bowl is increased to a constant rate of 300 for the next bit, find the rate of change of the depth of the water in when h is 20. So where did that, what changes this? It's that number, yeah, the 160. So you just have the same thing, but this is going to be 300 instead of 160. 300 instead of 160. So what's the difference? Well, we need to find the rate of change of the depth when h is 20. To do that, we're going to have 300 over 50 times 20. Take away 20 squared. That's 1,000, take 400, 600, 300 on 600 is a half. Does that look good? Yep, lovely, jubbly. Let's keep going. We've got some parametric stuff. State the domain of the values of x for the curve. So given here that t is bigger than -2 on 3, what we can say then is that if we add on 2 to that, so t plus 2 will be bigger than, that's -2/3, we'll have +4/3. So we know that x is going to be bigger than the log of that. Log is a monotonic function. It only ever increases. So what we have is that this is going to always increase as well. Like if the log is always increasing, the other thing is always increasing, basically. Like if it's if something's equal to log, they're both always increasing because log is always increasing. So if you get like the smaller value inside, the outside is still the same. And it's always going like up, do you mean? It never falls back down from itself. So find r from here then. That, that seems such a weird picture to add on. Why have you added that onto there? What have we got to do then? We need to integrate, but we have parametric. So you could either rearrange for get it in Cartesian form, or we can just do the integral normally. So we would want to find r. That is going to be the integral of y with respect to x from log 2 to log 4. Y, though, is in terms of t. It's not in terms of x. So what we need to do is change it so that this has, yeah, log 4 and log 2 still in the limits. These are actually in terms of x. So we need to note that they, over here it's fine, but now we're going to change the t. So we are going to have to note that these are actually in terms of t. So doing that, is that right? No. They're in terms of x, and we're going to change the t. The reason I thought something was wrong there, if we made t be log 4 or log 2, you can have log of log 2 plus 2. Very rarely do you see logs inside logs at A level. So this is good still. Yeah, we need to do y, but with respect to t. So it has to be a dt on the end. We still need the y, don't we? But if we put that dt in there, we must have divided by a dt. And that dx we've got, it's got to go somewhere. So you can kind of change this out for just a dx, effectively, thinking of the chain rule. So what do we need? We need to differentiate the x, which isn't too bad. So r should be the integral Again, x is log 2. We could change these limits over, like whenever you like, you can change them over. As long as you're clear, like if you're using the wrong letter, just be very clear about like you haven't changed them yet. So the y is still the same, 1 over t plus 1. The dx dt though is going to be 1 over t plus 2. And then we need to have a dt. Looks good to me, yeah? Yeah, I think that looks good to me. What we're going to do from here to solve it. Are we just going to do by parts? Is there any easier way that we could do this? Could we, what if we could like combine the bottom and complete the square? Would that be a better thing to do? We could not do partial fractions, that wouldn't work. Like we could do the, yeah, integration by parts. Would that be nicer? I don't know if it would be. Let's have a think. How could we actually do this? What would we want to do without doing it in the way that we used to do it, like with the sine and coses and tans? Is it just going to be substitution then, the same as I did it earlier? I think so. Yeah. What substitution should we use? Or do we choose partial fractions? Yeah, partial fractions is going to be a little bit easier. So I think substitution is going to be when you have like, you don't have a product there, but you've got kind of a lot of bits going on down there. Maybe with stuff on the top two, but generally like more going on. But with the product, it's going to push you more towards partial fractions. So if we look very quickly, this is going to be like a over t plus 1 plus b over t plus 2. And we can get that from the log as well. The fact we have log there, like we do need to get them individually to be integrated, and there's no other terms either. So this is good. Doing this then, what do we get? Ooh, stick with blue for a sec. A lots of t plus 2 plus b lots of t plus 1 is equal to the 1, the numerator we had originally over there. If we look at when t is minus 2, what do we get? We get minus b is 1, so b is minus 1. If we look at t as minus 1, what do we get? We get a is equal to 1. So this integral is the same as integrating, well, the a is positive, so it's over 1 plus t plus 1. And then we have negative 1 over t plus 2 dt. And I will change the limits now as well. So we want to find what t is going to be. Well, I think if x is log 4, t is 2, yeah. If x is log 2, t is 0. So 2 and 0. Let's perform this integral now. Each one is just the log. So log of t plus 1 minus the log of t plus 2 with 2 and 0. And then we want to combine them into one log. So log of t plus 1 over t plus 2. Do it now. We'll do them individually first. Do them individually. So plug everything in. 2 plus 1 is 3 minus 2 plus 2, which is 4. But I'm going to write that as 2 log 2. And then we're going to have the takeaway. Of we plug in 0, we get log 1, which is 0. And then the takeaway of log 2. So that adds another log 2. So it's effectively log 3, take away log 2, which is log of 3 over 2. Is that what they wanted? It is indeed. Lovely jubbly. Looks good to me. Let's keep going. Curve is given by this equation. Point P lies on C. Tangent to C is parallel to the x-axis. Okay, so we need to differentiate this thing. So the sine goes to cos. The cos goes to negative sine. But we used the wrong letter. We used a y. We should have used an x. And the half, that just goes away. So what is dy dx? Well, if we added that over, divided by sine, it is cot of x. No, tell a lie, because sine and cos have got different letters in there. So this is still just going to be cos x over sine y. You can do some things about like rearranging there, do you mean? So actually probably will do. Yeah, so the sine, no, we can't really, can we? Or is it going to be that idea of doing the 1 minus square root stuff? Yeah, I think it is, isn't it? So let's get it all in terms of x. No, we're not going to do that. We're going to be a bit fancy. So if something's parallel to the x-axis, moves in this direction, yeah? So its gradient is 0. So all we need to do is set this equal to 0. We don't need to care about the bottom at all. So what do we have? We have cos x is equal to 0. So x is going to be equal to, anytime cos x is 0 between there, if we go and draw it, we would normally have that bit of the curve, but we've also got this bit of it. So when is it 0? We did have this side, and we did have this side. So minus pi on 2 and pi on 2. Find the exact coordinates of all possible points, P, just for your answer. So they're the two possible values for x. If we rearrange then the original equation for y, we're going to have that cos y is equal to sine x plus a half. So when we look at the two different values, what do we end up having? Well, sine of pi on 2 is 1. So this is going to be 1 plus a half, i.e. 3 over 2. And if we do the negative, then it's going to be negative 1. So it's going to be minus a half. This one will have no solutions, the first one, with the 3 over 2, but the minus a half will do. So what we have, cos y is equal to minus a half. Again, we can go look at our graph to see when it gets there. This was 180 degrees. This should be 210, I think. So that's like 7 pi on 6. I will double check that to make sure that's fine. 7 pi on 6. Oh, we'll do cos inverse of minus 0.5. 2 pi on 3. Okay, ignore everything I said about that bit. 2 pi on 3. Did I do the other one right? It was the inverse of cos, wasn't it? Of 0. Yeah, it's pi on 2 minus pi on 2. That looks good to me. So this one happened with the negative version of it. So minus pi on 2 is the x coordinate, 2 pi on 3 as the y coordinate. Didn't have a picture, did we? No. Number 12, let's check the answer. We're allowed to have another answer here as well. We get also the minus, so it's plus or minus that. Yeah, this is symmetrical, and we did have enough bits to make you think about here. I think I've just drawn this completely wrong. Ignore what I've drawn there. Lovely. This is hopefully all looking good. The way we could probably be a little bit more formal there, and right, like the why is this not working? Because we have that sine x is never equal to 3 over 2. Looks good to me. Express this thing as a an integral. So what it is, it's going to be the integral from 1.44 to 2.89, 2 to the power of x to the negative half. I will just for the first step leave it as what they've got to be. So 2 over root x dx. That's good. Just like I say, this is 2x to the minus a half. So now we want to just do that, just perform that integral. So doing that, what do we get? X to the half, and divided by half will give us a 4. And now we've got 2.89 and 1.44. So 4 lots of, if we square root 2.89, what is that? Is it 13 squared? So 1.3, and then that's 1.2. So we have 0.1. So is it 0.4? I think so. These are the new ones. I don't actually have the mark schemes for these. So methods should all be okay here, but I might not have the right numbers. I can't double check that these are correct. We can just do it on the calculator, but I don't have like the mark scheme. Do you know what I mean, to double check that they are perfectly correct? But they should be pretty good still. So integrate 2 over root x from 1.44 to 2.89. They've chosen those numbers because they're squares. I mean, like 12 squared, and it's not that 17. 17 it is. Ignore me. It's not 13, is it? This is 17, the first one. So it should be 0.4 times 4. So it's going to be 1.6, I think, before my calculator tells me. 2. Have I done even sillier things? Yeah, what I've done is I've done 12 take 17 take 12 and got 4, which is actually 5, isn't it? So yeah, this is 2. So see, numbers sometimes will be wrong, but the process, the methods should be spot on. Let's keep going. What do we have? We've got this little quartic thing, is it? Yeah, quartic. Has minimums at there and there. Crosses there at minus 75, turning point at 2. Find the set of values for which it is increasing. So over here, It could be equal to 0 as well, so turning points are good. So we have that x can be less than or equal to -1, or we could be in this little section, so between 2 and 5. Looks good to me. Set notation. So this bit, you've got these. I don't know how strict they are. This would be allowed, like you'd have or inside it, but I'm going to do it in the kind of way I've always seen them written it online. So each one we're going to separate out. The or is going to go away for a second. So each one's going to make its own set effectively. Let's bring them up here actually. Yeah, each one's going to make its own set. So on the left, what numbers do we care about? What numbers do we need? They haven't told us anything about the domain or anything, but I'm assuming it's all the real numbers. So we just need to make sure that x is a real number. And then turn it into a set. That's a given that. Put the brackets around. So the way to think about it, type of number, rules of the numbers. It doesn't have to be type of number, type of object, type of element in the set. But you'll pretty much always deal with numbers. So here x is a real number, and we need to make sure x is less than -1. Do the same thing on this side. X again is a real number. Whack them in the curlies. And these two, we want it either or. So we need the union of the two. That looks good. Find the equation of C. You may leave it in factorized form. So the fact it's got repeated roots, we know we've got x plus 1, so that root on the left, squared, because it's repeated, and x minus 5 squared, because it's repeated. We just need to figure out what number goes at the front. So if we were to expand this all out, we'll have 1 squared is 1. That's 25, times together 25, but I need minus 75. So I'm going to have -3, lots of that. Looks good to me. The curve has equation y equals f of x plus k. Given that the curve is at exactly 4 places, find the range of values of k. So we can imagine what the line is just hold on. Curve C1 has equation y equals f of x plus k. Intersects the x-axis exactly 4 places. Oh yeah. Okay. So what we can imagine is that instead of moving the curve, you move the x-axis in the other direction. So we could be here. That would be fine. Or as we go down, if I can grab it. Yeah, as we go down, we've got 4 all the way, and then 3. And we're never going to get 3 again. We're only going to have 2 from down here. So we need to go to that point. That's the lowest point we could possibly go to. So that looks good. How can we find that point? We're going to take our thing and differentiate it. So we probably need to expand the brackets maybe. No, we're not going to do that. We're going to do quotient, the product rule. So we're going to have -3 is going to come. This is going to be, is it, they called it y? Yeah, dy dx. No, ignore me. We know that's a turning point already. We know it's at 2. My job there was to find 2, but we already know it's 2. We just need to plug the 2 in. Doing that, what do we get? 3. That's -3. So there's 5 3s, like 3 to the power 5 in there. How's the negative looking? Well, that's positive, so it must be negative, yes, underneath, isn't it? So that is 243, that line. That negative 243 going on there. So what we can say, like this is the idea of moving this down, yeah. We'd move it down 243. The question itself was asking about taking the curve and moving it up. Well, if we've just figured out this gap is 243, so I can move it up 243, and I could move it up 0, which I mean would be fine. I'm not actually allowed to do the 243 though, because that would get us to the 3 points with this being repeated. So we have k, and it's going to have 243 and 0. It can move up, but it can't hit the 243, but it can be the 0 because that has still, note to low, can't be the 0 either. Because that again has just repeated roots, so it doesn't have 4 of them as you go across. That looks good. All looks good for me. Let's keep going. Value of a car. Initial value is 20 grand. It was 12 grand when it was 2.5 years old. Find a complete equation. Okay. Well, the first thing to spot is like the initial values again. So that's going to be 0 and 20,000. And if we look at the one underneath, we're going to have 2.5 and 12,000. So plug in 0. E to the 0 is 1. So 1,500 plus A must be 20,000. So we know that A is going to be 18,500. Using the next one, plug in some of these bits in. What do we get? 12,000 equals 1,500 plus 18,500 e to the minus 5 over 2k. So as we do some subtractions and stuff, we get 10,500. We can divide 1,000, well, hundreds off. This is over 185 is equal to the e's. So that's what fraction is that coming down to be? Is it 21 on 37? I think it is. Yep, 21 on 37. We're going to take logs of both sides. That will give us the power over there, the minus 5 on 2. So we've got minus 2/5 of that. That is k. Find a complete equation, so let's just rewrite that. So we're going to have that v is 1,500 plus a, which was 18.5 grand, 18,500. And then that needs to be times by e to the power of this stuff. And it's actually e to the negative of that. Did I mess up my negative somehow? Somewhere, something. Yeah, we should have that k is positive. Yeah, k is positive. So I'm guessing this is correct. It's just we need the positive. But where did that go wrong? This is good. Taking that over. That would be positive. That would be positive. Log of it. That would bring that down. Oh, is it just going to be that this is positive? But yeah, this is okay. Yeah, this is negative. So this is fine. This is fine. 5 over 2 log of 37 on 21. Yeah, this is negative and these are negative, so it is positive altogether. That's good. So yeah, 5 over 2 log of 37/21. Looks good to me. You can rewrite this if you want, like this term. Think about you've got a product in your power, so you can do that as a power of a power. So we could have like the e bits, then the log bits, and then to the power of 5 on 2. But the e to the log bit cancels out. So what this ends up being is like 37 on 21 to the power of 5 on 2. This should have a t up there still, sorry. It should have always had a t up there. But these are equivalent. Both of these would be fine depending on like what form they want it in. So that's good. We want to find the rate of change of the value of the car. So as we go differentiate this thing, what's going to happen? Like, so I'm going to leave k out the front. So I'm actually going to start off with like v is equal to 1,500 plus a e to the minus kt. Just make it easier for you. Don't be dragging this around everywhere. You don't need to. It's a. You can just, it's a. We don't need to be like calling it all 18.5 grand all the time. Just call it the simplest thing you can. It'd be nice if we could do the same thing here, really. Just call this something else and have just a letter. But whatever works for you. So dv dt, 1,500 goes anyway, doesn't it? Minus a k e to the minus kt. And if we look at it, this, if we slightly rearrange that, put the k at the front, we then have a e to the minus kt, which is the same as this thing, yeah? So that whole bracket is just v minus 1,500, because you imagine taking that over, we're left with this bit. It is that bit, so that should all be good. Minus k, lot of v minus 1,500. Is that what they wanted? Looks good to me. State limitation of this model. The idea that the car is never worth less than 1,500 quid. This, the way you think about it, this is going towards 0, yeah, as it's decaying. So this whole thing is 0. So eventually it's going to settle down to 1,500 quid. So they're saying like after the heat death of the universe, this is still worth 1,500 quid. There's no upper limit on the time, and there's no, well, there's a low limit on the price, and that's the issue really. Lovely, that looks good to me. Right, show that this thing is true. So what do we want to do? It's going to be a substitution. As far as I've been dilly-dallying with today, it looks like it could maybe be a reverse chain rule, but you need to have just a constant on the top. So yeah, it's going to be a substitution. So let's let u equal 2x plus 1. So du dx is 2. So we can say that dx is going to be du on 2. This is good. We can also, from here, the x is going to be u minus 1 on 2. So, and the limits as well. So where do they take us? If x is 2, we double it and add 1, we get 5. Double it and add 1, we get 2. We get 1, sorry. So what we have, our entire integral, is from 1 to 5. X on the top is u minus 1 on 2. On the bottom, we've got u cubed. and the dx is a du on 2. So we can take those halves out. What do we have is a quarter. Again, 5, 1. We've got a u minus 1 over u cubed. So that's u to the minus 2, u to the minus 3, subtract in the middle, du. And as we do that then, quarter stays out the front. We're going to have u to the minus 2 becomes u to the minus 1. And then we need to divide by the 1, the minus 1. U to the minus 3 becomes u to the minus 2. Divide by that, we get positive a half. So let's go and plug some things into here. These are being having 5 and 1 put in there. So we've got a quarter of minus a fifth plus 1 on 50. And then that stuff is going to take away when we do it with a 1. So minus 1 plus a half. Let's whack that in the calculator, see what we get. So 1 on quarter at the front, minus 1 on 5, plus 1 on 50, plus 1 minus 0.5. And I get 2 on 25, which I think was the show that. Yep, lovely, jubbly. Looking good. Is this the last one? Nearly getting there, yeah, nearly there. How many more have I got to go? Oh, yeah, we are really there. We can see them all now. We've got what's that? 7, 8, 8. Oh, exciting. So what have we got? Some stage. The shape of stage consists of a sector and a circle joined by a little rectangle. Radiuses r, angles theta, length r and a tenth of r of that rectangle. Total area is 240. Find the perimeter. Okay, so if we think about the area to begin with, so area generally of a sector, you're going to have the circle and then just find out how much of the circle you have. But we've already got the shortcut for that, r squared theta on 2. And then we must add on this little rectangle, r squared on 10. That looks good to me. What we're going to do though, down here, there's no theta. Very common. It's the same process every time in these, do you mean? They're not connected rates of change, but they're the same sort of idea, but it's a little bit different in what you're going on. They're like connected somethings. I don't know what you'd call them. Connected measurements or something. I don't know. But yeah, it's kind of like that, but not. There's no rate. There's no time happening here. This thing is fixed, but like it's not changing over time. It's like our design that's changing of it. We're not having this stage and having things filling up the stage. So we need a relationship between r and theta. Area is 240. So that is the relationship between it. This is 240. So let's somehow rearrange for theta. Well, I'm going to times by 10. So I'm going to have, this is going to be 5r squared theta plus r squared is equal to times by 10. Sorry, times by, yeah, times by 10 is 2,400. So our theta is going to be 2,400 divided by 5, 480, divided by the r squared. And then we're also just going to have this like take away r squared over 5r squared to take away 1/5. That's good. Now we need the perimeter. So perimeter of this thing, what do we have? I've got an r, a tenth of r, an r, and a tenth of r. So an r, a tenth of r, an r, a tenth of r, and I've got the arc, which is r theta. All the r's then, I've got 1, 2, that's another fifth. So that altogether is 11/5 of r. And then r theta. Well, theta, I just worked out is all this stuff, yeah? So if I actually just times them bits by r, what do I get? Well, I get 480 on r. And I get minus r on 5. So putting that together, what do I get? It's 2r, because I've got 10/5 of r, plus 480 on r. Looks good to me. Wonderful. Use differentiation, find the stationary value. So let's just rewrite that second term. 480 r to the minus 1. So dp dr is going to be 2 minus 480 r to the minus 2. So 7 equal to 0. We can see that we're going to have, well, it's the same as having 2 is equal to 480 over r squared. So we know r is going to be the square root of 240. Does that simplify down at all? 4 root 15 is a bit nicer, and it's not too much nicer. 4 root 15. Prove that this is prove it's a minimum. So the second derivative, d2p dr squared, that 2 goes away. We're going to bring these two together to make a positive, and then times them together to make the 960. Drop the power down to -3. And you can show like the radius we have is positive, so we say this is positive for all r is positive. So therefore it is a minimum. You can also plug the value in, get the value, see what it is, but yeah, that should be fine. Is that the end? Was that the end? Yep. Lovely jubbly. This one over here then. So what's going on? We need to do some sort of substitution, don't we? Yeah, they told us x is 2 sine u to get that thing out of the end, and then solve it all. Okay. So first things first, x is 2 sine u. That means that dx du is 2 cos u. We do have limits, so we need to think about the fact that when we have x is 1, we're going to have, that would be a half. So sine inverse of a half is going to be that u is equal to pi on 6. I'll double check that. I feel like I can't do the trig stuff today. Inverse sine of 0.5 pi on 6. And similar sort of idea if we make it 3, root 3, sorry. Root 3 on 2, yeah. So if I just put in root 3 on 2, I'm going to not trust myself on that one. We get pi on 3. That looks good. So from here, what do we need to do? Well, looking down here, this is a bit messy, yeah? I don't really exactly want to try and plug it in like 2 sine u into this thing and do it. So what I'm going to do is just work separately. What is 4 minus x squared? So if I do x squared firstly, that's going to be 4 sine squared u. So if I do 4 take away that, it's 4 take away 4 sine squared u. That is just 4 cos squared u. So if I go to square root all of this stuff now, what do I have? I've got exactly 2 cos u. So this is good. This is good thing to line up. Let's plug everything in. We really want to have the integral to start with of 1 over x squared 4 minus x squared all square rooted dx from that 1 to that root 3. But let's start swapping things out. So 1 became pi on 6, and that becomes pi on 3 at the top. X squared on the bottom, what's that going to be? Well, that is 4 sine squared u. We've got that whole square root. Remember what we said? dx is going to be 2u, 2 cos u, du. That's 2 cos u. So effectively, like dx over this thing is just 2 du. So all we have left over, 2 du. And this is good. We wanted cosec. We're there. So this whole thing then is just equal to, well, the integral from pi on 6 to pi on 3. And we're going to have a half of cosec squared u. That all looks good to me. Now we want to find our, I think, oh, is cosec one of the ones that's not in the book? Is it in the book? It's not what I know off the top of my head, I don't think. Or is it? Yeah, it's minus cot, isn't it? Because it's like sec. When you differentiate tan, you do the quotient rules, u over v, so you end up with like a cos squared in the bottom and a bit disappears in the top. You do it with cot, same thing happens, but you get the sine squared down the bottom. Stuff disappears on the top, but it's the negative version of it, so it's negative cosec. So this integrates to negative cot. It's negative cot u, pi on 3, pi on 6. Looks good to me. So let's plug this stuff in. I'm going to have negative 1 on tan pi on 3 plus 1 on tan pi on 6. Let's see what this is. Pi on 6. Not inverse tan, normal tan. Shift for the pi. Oh, syntax error. Let's forget to close the tans and signs. 2 root 3 on 3. Again, that seems very nice. Does seem a very nice number. Yeah. I'll check it in here. I'll make sure that this does give the same one, just to see what it's saying. Make sure we're not giving you the wrong answers. So what do we need to do? We need to integrate 1 over x squared, and then the square root 4 minus x squared from 1 to root 3. Lovely. What does that give us? Did I type it incorrect? I did. We get 1 over 2 times by root 3 times top 1 by that. Root 3 goes to the top, 3 on the bottom. Lovely. Looks good to me. All right, then, last paper. Nearly there. This one's not too bad either. Simplest form. So 4, raise that to a 5, divide by the 5. A half, raise it to 3 over 2. 2/3 of 6 is 4. Minus 4. Raise that 3 up to with an x. Don't forget your plus c. That's fine. 4 marks. If I did that wrong, I don't think I've done it wrong. Let's double check just to make sure I haven't done it wrong somehow. I've done a lot of maths in the last 12 hours, however long it's been. 24 hours or so. X to the 4 minus 6x to the power of 1 over 2 minus 3. We've got x to the 5 on 5 minus 4x to 3 on 2 minus 3x. Yeah, looks good to me. Curve has this parametric stuff. Find the y coordinate of p. P has the x coordinate of minus 3. Okay, so we know x is minus 3. Use that to find what t is. So we have minus 3 equal to t minus 1 over 2. So that's going to make minus 6. Add a 1 is minus 5. Plugging that into here, then what are we going to get? This is going to make a negative 3 and then the power 4. So what we have there is 5 times 81. So it is 365. Find a Cartesian equation. Was that right? No, 405. 405. My brain told me something's wrong. Just double check that. 81 times 5. 405. Yep. Find a Cartesian equation for C, giving that to the form of blah, blah, blah. So we can do a few things. Let's just rearrange this for t, yeah? So if we take that, 2x will be t minus 1. So t is 2x plus 1. So we want t plus 2. So that's 2x plus 3. So this should be y is 5 lots of 2x plus 3 to the power of 4. That's good. Find the gradient then. So yeah, let's dy dx. 5 at the front. We need a 4 there as well. And the 2 from inside the brackets alongside the 2x plus 3 cubed. So this is going to be then 20 times 2 is 40. 2x plus 3 cubed. X was minus 3. Double that, minus 6. Add a 3, we have minus 3. Cube that, minus 27. This is 40 times by negative 27. So that negative 1080? Yeah, 25 of them are 1,000, isn't it? So yeah, negative 1080. Looks good. Let's keep going. So what have we got? This curve has a sketch, blah, 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 blah. Local maximum at minus a quarter. Show that a is equal to this. Okie dokie. Local maximum. So let's differentiate it. And then we'll set that value, x, like plug the value of x in, and it should be 0. So differentiating, what do we get? I'm going to have a 4 down the front. Lower that to a 3 at the top. 3 times a third is 1. Drop that power to 2. Minus 16x plus a. And that is f dash. And like I said, this is going to be, when we plug in the minus quarter, should equal 0. So doing that, what we're going to have here, well, if you cube root that, you get 1 on 64, but then you times it by 4, it's like we've got square on the bottom, so it's like minus 1 on 16. The next one is just positive 1 on 16, so that's good. And then we've got negative 16 and negative quarter, so positive 4 plus a equals 0. A is minus 4, because these two cancel out. That looks good. Yep, what they wanted. Find the exact coordinate of the local maximum. So, oh, okay, yeah, okay. Local maximum, we knew that that's the x is minus a quarter. So we just want to take that and plug it back into here. I'm not going to do that by hand. So minus 1 on 4, set that into the answer. Now I want answer to the power of 4 plus answer cubed on 3 minus 8 answer squared. The a was minus 4, wasn't it? So minus 4 answer and plus 17 on 3 at the end. I get a not very nice number. I think this is, I've done this one before. I've done this recently, so I feel like that's the right, that ring, like that's 10. My brain feels that was the right number. That was the correct one. So what we have is the minus a quarter was the x, yeah, and then the y is 4735 over 768. All that is, this thing is just taking the original function and plugging in the minus a quarter. That's all I've done there. So if it's wrong, I've just got the wrong number from the calculator. Do you know what I mean? Fx equals k has 4 distinct solutions. Find all of the ranges of k's. So 4 distinct solutions. Let's draw just a horizontal line, because that's what we really want in there. If we have fx equals k equals some constant, having 4 solutions, you can see here we don't have them. I've got one there and one there. That's not enough though. I need to go up until I get to this point. And you can see anywhere above that point is good. I've got 4, but below that point is not good. So I want to be at least at that point, at least there. Then if I keep going up, eventually, if I keep going up, I've got 4, 4, 4, 4, 4 until I hit this point and I have to stop. So I have this point. That's what I just worked out is the 4735 on 768. 4735 on 768. I need to find then this gap, and then k needs to be less than that, more than that. Where is this? Well, let's go and solve the second derivative equal to 0. The first derivative equal to 0. Let's just quickly write it down. It's 4x cubed plus x squared minus 16x minus 4. We knew that we had a x is minus a quarter as a solution. So what we do have then is that we're going to have 4x plus 1 as one of the brackets. So let's think about all the parts. This has to be times by some quadratic. How are we going to get 4x cubed? Well, we've already got 4x, so we need an x squared. Same at the end. How do we get the minus 4? We need to have a minus 4 times that 1. And now let's look. We've got 1x squared. We need to have just one of them. So I need to make sure that these times to 0. So that's plus 0x. So I've got 4x plus 1. And that's x squared minus 4. So x minus 2. X plus 2. So what's our solution? The one that we had on the left is whenever x is minus 2. So that tells us x equals minus 2 if that equals 0. Lovely, that's good. We need to find then, plug in the 2 back in. So if I, minus 2, sorry, minus 2. So minus 2, scroll up, press equals. I get, again, not very nice. I'm going to double check I typed this in correctly. So answer to the 4 plus answer cubed on 3 minus 8 answer squared minus 4 answer plus 17 on 3. Does seem okay. Let me just do it again. So I've got minus 2, save, up to the answer thing. Okay, yeah, I must have done something slightly wrong then. So this gives us that y is minus 5. So yeah, this is minus 5. What was it saying? We need to have our function equal to k. So k needs to be between these two numbers to have us having 4 distinct solutions. So yeah, we couldn't actually be equal to either of them. So final answer, k is bigger than minus 5, but less than 4735 on 768. I'm just going to check that I didn't do this one slightly wrong again. So if we do minus 1 on 4, minus 1 on 4, scroll back up to this stuff, press answer. No, it's there. But like that being minus 5, that seems so nice compared to that one. But I think this one was correct. It like this 768 is why I feel like that's right, and this doesn't feel wrong. I mean, it's not, my brain's not saying, oh, that's the wrong one from last time. Because it was like a week ago I did this or something. That's good. Is this the last one? No, 3 more. Listen, 3. So a new type of car is released for sale. Total number of this type of car sold N in a particular region. T months after its sales by this. Find the total number of cars sold in the first 3 months. So this is one thing that the language of here, I was thinking like it didn't specify whether it meant like accumulatively or just like for individual months. But if we think about the shape of the graph, what is it doing? This thing tends down to 0 like that. So if you make it negative, it just does the same thing going up. So this is going to tend towards 5,000. Does that make sense? So it's going to stop at 5,000. I'm not thinking that's going to be like, okay, they're going to settle at selling exactly 5,000 per day. But it means that they've sold 5,000 altogether by the end. So if we want to find the total number of cars sold in the first 3 months, we're just going to plug in TS3. Simple as that. And I will, won't factorize them. We'll have 5,000 then. Take away 5,000, lots of E. To the, this is 3 on 40, isn't it? Minus 3t on 40. So minus 9t on 40. Minus 9 on 40, sorry, no t anymore. What does that give us? 107. 107? 1007. And that does ring a bell of being spot on. That's good. Given that n equals 3000 when t is t, find t. Okay. So we just want to rearrange this for t if you can. I don't think we even need to though, so we can just plug it in and rearrange it in. So 3000 will equal this. So it's like 2000 equals the minus 5000 stuff. E to the minus 0. Well, minus 3t on 40. Let's get rid of all my thousands. This is going to be like 2/5, yeah, negative 2/5. But I'm going to flip it with that negative. So it's going to be e to the 3 over 2 at 3t on 40 is equal to 5 over 2, but negative. Does that seem right? No, we shouldn't have a negative, should we? So what's gone wrong? The issue is when we did a takeaway there, this would have been negative. So that one would have gone as well. So that one goes. So as in like, yeah, when we did like the 3,000 on this side, take the 5,000. So now what's t going to be? Well, it's going to be equal to 40 thirds of log 512, whatever number that is. I will work it out for you because you guys probably want to use that to check. Log 2.5, 12.2, something like that. Find the rate of increase when t is 3. Okay, so we need to differentiate this thing. Goodbye. 5,000 times 3 on 40 is 375. The negative there and the negative there will disappear with each other. So dn dt is going to be 375 times by that power still, minus t over 40. We want to plug in when t is 3. So dn dt when t is 3 is going to be this thing with t being 3. This should have a 3t. So that's going to be 375. Why can I not do 3s? Why have I forgotten how to draw 3s? E to the minus 9 on 40. Lovely. Looks good to me. Again, these all seem right in my head from what I was doing the other day. Nothing seems wrong. If they are wrong, whack them in the comments, Jimmy, let me know. Hopefully they are all fine. So after market campaign, total number of cars sold is expected to rise and have an upper limit of 6,500. One refinement. So what I said earlier, this is going to come and like settle towards 5,000. So just both those 5,000s, change them up to 6,500. So replace 5k with 6,500. Looks good. 2 more. We've got 1 rates of change one then. Water's flowing into a container. There's a tap at the bottom. Tap was opened. The volume of water in the tap is V. So went into the container at this much rate and leaving the container at the tap at this rate. So that's all volume per hour. So dV dt. Coming in at constant rate, 0.45, so 9 on 20. And it's leaving at a rate of 0.3V, so that's 6 on 20V. That's good. You can see why doing fractions is nice, because now look, we've just done it, haven't we? We just times by 20 and then we're good. So 20 dv dt is equal to 9 minus 6v. Looks good to me. Given when the tap was opened, so when t is 0, there's a quarter, and that they are values for t and v. We can take those, use that to solve this thing. So we need to integrate this. It is a differential equation. You only know one way. We've got dv over 9 minus 6v is equal to 1 over 20 dt. I really want a minus 6 at the top on the left-hand side, so they can combine together. But to do that, I have to divide by a negative 6. What do we have then? Negative a sixth of log of the thing on the bottom is equal to t on 20 plus, and again, I'm going to do the same thing with the logs, doing like 1/6 of log c. So just matching like one of these bits. I could make it negative, but I'm going to add that bit over there. This looks good. I want to find c. Yeah, I need to find all these things. So let's find c, but I know 0 1/4. So plugging it in, that's gone. What we're left with then, we're going to have the 6 will go. This is just negative log. So actually what I'll do is I will make that negative, and then the negative's gone as well. So 9 minus 6 times v. Well, v is a quarter, so 6 quarters. That's 3.5, so 7.5, 15 on 2. T's gone, and that's equal to log c. So c is 15 on 2. Looks good to me. So now we just want to plug it back in and rearrange for v. So as we do that, what's going to happen? We have minus a sixth of 9 minus 6v is equal to t on 20. Take away 1/6 of log 15 on 2. Let's bring this way and that over there. So what we're going to have is adding that over, and we'll times by 6 as well. So 6 on 20, 3 on 10, t, but negative, is equal to, this should have a log still, sorry, this 6 over here. Yeah, adding this one across to the right hand side, we can take a factor of a 6 out. We've done that by times them by 6 already. And then what we're going to do is have the log of this one over the log of that one. So it's the log of 9 minus 6v over 15 over 2. Let's see if they divide down quite nicely. So 9 divided by 15 on 2. What does that give us? 6 on 5. And then also, if we do 6 divided by that, what do we get? 4/5 as well. Not 4/5, but 4/5 this time. So let's do it all as 5. 4 minus... No, 6 minus 4v. 6 minus 4v. On 5. Looks good to me. We want to get v though. So it's going to be that thing inside the log. 6 minus 4v over 5 is equal to e to the minus 3t on 10. This looks good. Times by 5. So you get 5e to the minus 3 on 10. That would be equal to the top row there. So if we add the 4 and take this thing over, it'll be 6, take away that, and we want this to be over 4. That should be v. Looks good to me. Make this be more of a 3. I need to learn how to write 3s again. I seem to have forgotten. So that's good. Do everything else going on. Will it ever become full? If we let this run forever, what's going to happen? Well, this thing is like a decay, yeah, but this is a negative, so it's kind of doing that and settling, same as the last one. But this eventually will go to 0. But we've shown that it's negative before, like it's underneath before that, before the settling value. I mean, it's rising up to a value, and then we'll plateau there. As that plateau happens, this has gone to 0, so this has gone to 0. 6 over 4. So what we can say is that like t tends to infinity implies that v tends to 6 on 4, which is less than 2. So therefore, never full. Looks good to me. Now the last one, we've got lots of stuff going on down there. We've got a -1, we've got a 1. We got a p, we got a q. Find p. Okay, so we want to differentiate this thing. Quotient rule. uv minus uv dash is on the outside, v squared on the bottom. What is u? It's the thing on top, 1 minus x squared. So differentiating it, minus 2x. Looking at the v, we have 1 plus x squared squared. So differentiating it, 2 comes out the front, alongside a 2x from the middle, and the bracket from above, but with a lower power. Stick these all together, u dash minus 2x times by v, so times by the bracket squared. Notice the bracket's always the same. I'm just going to call it bracket for a sec. And then u, what we're doing? Yeah, u, sorry, 1 minus x squared times by v dash. So that's 4x times by that bracket. Notice that this bracket is different in that it's not the same. All of this over v squared. And v squared is the bracket to the 4. So this is what I'm saying, like you can also have a lot of, this is everywhere, so you can cancel it all out. But we don't need to really care about cancelling it all out, we just need to care about cancelling like 1 from everywhere. So minus 2 lots of, I will put that bracket now, 1 plus x squared, and then take away 4x times the other bracket I had above, 1 minus x squared. This all over bracket cubed, and then if we expand the top, what do we get? Well, how many cubes have we got? I've got there minus 2, there positive 4, so I've got 2x cubed. How many x's do I have? Minus 2, minus 4 is minus 6. And then what we have is still bracket cubed. So thinking about that, we want to set this equal to 0. That's going to tell us then that 2x lots of, this is the top row, x squared minus 3 is equal to 0. So x is either 0 or plus or minus square root of 3. And if we look up, we have our 0, and this graph is symmetrical, so that's nice. So I'm pretty sure that this is minus root 3. Did we need the y coordinate? Yep, we did. So we want to plug that value into there. So it's minus root 3. Does make a difference though, because it's just going to get squared and disappear. See, this is an even function. All powers of x are even. So we end up where this is always, if it's negative, it doesn't make a difference. Do you know what I mean? Because we square it and it goes away. So all we want to do is plug these values in basically. Root 3 squared is 3. So 1 minus 3 or 1 plus 3. So 1 minus 3 is minus 2. 1 plus 3 is 4, but that's squared down the bottom. 2 on 16. 1 and 8. Minus 1 and 8. All looks good to me. And again, that does ring a bell as being correct. I will have a look at the end and make sure this is all good. So use a substitution, x equals tan, to show that this is true. Okay. So if x is tan, what do we know about some things? Well, first of all, the limits. If x is tan, if x is 1, or if x is plus or minus 1, then what we have is that theta is plus or minus pi on 4. And now then, let's have a look at the x part as well. So doing dx d theta, what do we get? We get sec squared theta. If we look inside what we actually need to start with, there's lots of like 1 minus x squared and 1 plus x squared. So let's just work out what that is. X squared is tan squared theta. We know from the standard one, cos squared plus sine squared is 1. So if you want to get tan squared, we need to divide by cos squared everywhere. So tan squared, no, well, same idea, 1 plus tan squared is going to be sec squared. So that's good. 1 minus tan squared isn't anything, or tan squared 1, yeah, 1 minus tan squared isn't anything. Nothing special anyway. So what do we have? Let's start to stick all of these bits together. We're going to have the integral of minus 1 to 1, which is now minus pi on 4 to pi on 4, of 1 minus x squared on the top. What did, oh, that's tan squared plus 1, x squared, that's x squared plus 1. So x squared plus 1 is sec squared. So on the top is nothing useful. It's just going to be 1 minus tan squared. Theta. On the bottom though, let me move this over a little bit. 1 plus x squared, sec squared. So we want that to the power 4. So we've got sec to the power 4 theta. And then the dx is going to be sec squared d theta. So combining those together, pi on 4 minus pi on 4, and then sec squared down here, and sec squared, well, sec to the 4 there, cancel that a little bit. So 1 minus tan squared theta over sec squared theta. Hopefully that was all good. What we're going to do, is that what they wanted here? No, we've still got a few more to do, haven't we? Let's split this up into individual ones. Individual fractions, I mean. Where 1 on sec squared, what's that? Cos squared. And if you think, what is tan? Tan sine on cos. So we've got that squared over cos squared. So if we expand the brackets, does that help us? I don't know if it does. We'll have sine squared on cos to the 4, which isn't very useful. 1 minus tan squared, that wasn't anything, was it? That's definitely right on the top. Yep, x is definitely just that. That's definitely just that. That's definitely just that. Sec squared is tan squared plus 1. Might be really silly. Can we just work backwards from here, maybe? So what ideally would happen, let's think what could have gone wrong. Cos 2 theta is cos squared minus sine squared, yeah? So this should be minus sine squared, ideally, is what's going to pop out. So how could that be? Yeah, I've just written it here wrong. It's not cos, it's this. So they do have both of them, like, this is sine squared over cos squared, this is 1 over cos squared. You can cancel out those bits. We're left with just a sine squared on top. So yeah, that's good. So that's minus sine squared theta d theta. Like I say, that is the double angle formula. So pi on 4 minus pi on 4 cos 2 theta d theta. Looks good to me. Find it now. So when we've got cos 2 theta, what do? Well, we go back to sine. That stays as 2 theta. We have to divide by the derivative of 2 theta, which is 2. And then we have to plug in our different values. What we have then is pi on 4 and minus pi on 4. So doing this, we get a half sine of 2 theta, so sine of pi on 2. Take away a half sine of negative pi on 2. The sine is an odd function, so this negative can come out the bracket. So it's going to go away there, and this will make a plus. So we have half of sine pi on 2 plus half of pi and sine of pi on 2. So it's sine of pi on 2, which is sine of 90. So it is 1. So after all of this, 100, how many questions was it? 101? 101 questions. The last answer was 1. Thank you very much if you've watched all of this. Thank you very much if you've watched all of it. Hopefully it's been helpful. If I've got anything wrong, write in the comments. There's so many, I can't sit and watch and make sure that I've got 100% right in like 6 hours, how long this is going to be, doing hours of it. I can't double check every single part of it. There might be 1 or 2 that is wrong. I tried to check as I'm going, but I think this is all good. This stuff on the page I think is all correct as well. I did this last week or so. Yeah, thank you very much. Any questions, give me a shout below. If not, good luck on your exams coming up.